All right, so we are going to begin with some review for calculus. We're going to do a number of videos on pre-calculus review, starting with a quick review of the set of real numbers. Okay, so this notation, this sort of bold-faced R, you've probably seen before to denote this set of real numbers. And you've probably seen in high school some discussion of different ways that you can interpret the real numbers, right? So one of the interpretations that you might have seen is, well, okay, so first of all, your natural numbers are in there, right? Your natural numbers, your integers, so you include the negatives, those are also in there, right? Your rational numbers, those are in there. And by the way, these sets, they also have symbols, just like R, right? The natural numbers. The integers are typically denoted with a Z. Rational numbers, R is already taken, so we use Q for quotient. Okay, so we have all of these, but that's not everything, right? So we know that there are irrational numbers like pi and e and the square root of 2, right? So you throw in all the irrational numbers as well, and so basically we can think of, you start with all these numbers, and then you also sort of throw in, any sort of number that you can write with a decimal expansion, right? So it might be like a natural or number or an integer where there is nothing after the decimal place. It might be a rational number where you have either a terminating or a repeating decimal expansion. But it might be something like an irrational number like square root of 2 or pi, where the decimal expansion goes on forever, never terminates, never repeats. This is one way that people will think about rational numbers, is just in terms of decimal expansions. Another interpretation that you've probably seen is this sort of idea of a number line, right? So we think of the real numbers as this, the set of all points on this number line that goes on forever in either direction. Somewhere in the middle is 0 with positive numbers on this side, negative numbers on this side, right? And we think of this as this sort of continuous line. There's no gaps or breaks or anything in it, and every point on the line gives you a real number. Okay, so that's fine. That's one way to think about it. The way that mathematicians actually think about the real numbers is we usually think of real numbers in terms of properties, okay? And I'm not going to list all of the properties, but there are quite a few of them. There are the algebraic properties. Properties. So these are specifying all the rules for how addition and multiplication behave, right? So these are all the rules, like, the commutative property, which says that a plus b is the same thing as b plus a, right? The distributive property, so as an example, we would have the fact that if you do a times b plus c, that's the same thing as ab plus ac, right? That's known as the distributive property. It's key to doing things like factoring and multiplying out polynomials, right? The FOIL rule that you probably know comes from this distributive property. So there are all these algebraic properties telling you how, basically, how to manipulate real numbers, how to solve equations. That's the algebraic side of things. But there are also order properties. Now, the ordering has to do with this number line picture, right? Real numbers are ordered from left to right, right? There's this idea of increasing order. And there's sort of built in here, there's sort of a notion of size. This idea that we can talk about one real number being bigger than another, right? And in fact, mathematicians would say that the real numbers are totally ordered, right? So given any two real numbers, you can decide which one is bigger than the other, right? Given any three, you can put them in order, right? Small, medium, big, right? So any set of real numbers, you can always put them in order, right? They're there isn't anything kind of different tracks that things might go on. There's just one single straight line, right? Increasing size. So we have all those order properties which come up when you're trying to, let's say, solve inequalities, things like that. So this is going to pop up again later, so we won't spell everything out now. The last one is, I think, the hardest one. It's kind of the key property of the real numbers, because the rational numbers, for example, have all the same algebraic properties that the real numbers have. They have all the same order properties that the real numbers have, okay? But they don't have this continuum property. And there are a number of different ways of saying what the continuum property is. All of them kind of go beyond what we would do in a first calculus course, though, and they get more into what you might see in an upper division analysis course. So one way to think about what the continuum property means is that it kind of gets back to this decimal idea. So every possible decimal expansion produces a real number. The precise statement of this would be stated in terms of sequences in series, something you probably won't see until your second or third course in calculus. But we know that this is not true for rational numbers, right? So there are lots of decimal expansions that don't correspond to rational numbers, because if the expansion doesn't terminate and it doesn't repeat, you don't have a rational number. Another way to phrase this continuum property is there's also something, you could put it in terms of what are called least upper bounds. But that's not something that we want to get into. Okay? So there's another way to describe it in terms of least upper bounds. So these are all things to keep in mind when you're studying the real numbers. And maybe the main thing to keep in mind is that truly understanding the real numbers, actually having a definition of what it means for something to be a real number, is beyond what we do in a calculus course. Despite the fact that everything we do in calculus depends on the real number system, right? The playground for calculus is the set of real numbers, and yet we don't actually have a solid definition of what a real number is. And the reason is that the real numbers are actually pretty hard to define, and it's not something that we're going to try to do in this course, right? Once you've got some comfort, with functions, with limits, with calculus, then you're in a position where you can actually start talking about what a real number is. How would you define one? What are the properties? It turns out that this is actually a fairly advanced topic. So don't worry if you never quite feel like you know exactly what a real number is, because that's something that will come later on in your mathematical career. Okay, so I know what you're thinking. These videos are for calculus, right? What do we do to talk about order of operations? This is basic stuff. This is, well, maybe not elementary school, maybe middle school. But despite the fact that this is basic material, you're going to be wrestling with derivatives and integrals and understanding the meaning of continuity. You still have to do arithmetic. You still have to be able to add up numbers. You still have to be able to solve equations. These things are still going to come up. Order of operations messes people up more often than you'd think, right? So people have their various acronyms that they like for remembering this. One of them you've probably seen is PEDMAS or BEDMAS, depending on whether you call these things brackets or parentheses. We'll call them parentheses. So these rules say that, well, parentheses come first. Okay, simple enough. Or maybe not so simple, because you got to watch out for things like nested parentheses. You might have parentheses within parentheses within parentheses. So, you got to pay some attention there. Okay, the E there is for exponents. Right? You sort of basic principle here is you should start with the most complicated operations and work your way down in the order that you carry them out, right? So exponents are more complicated than, say, multiplication or division. So those come next. Okay, and last of all, the A and the S is addition and subtraction. Okay, fair enough. But even spelling it out like that, things are not quite as simple as it might seem. Let's do a quick example. Let's say I give you something like 2 plus 3 to the 4 times 6 minus 8 divided by 3 times 5. Okay, so there's an expression you can write down. It involves, well, there's no parentheses yet, but it involves all the other arithmetic operations. And so I guess if you were going to carry things out in order, then this exponent, that should be the thing that you do first. Now there's one of the things that trips people up. D then M. Does that mean we should do division before multiplication? Is this second? Well, some people will say, yeah, do division first. Other people will say, division and multiplication, they kind of come as a group, and you should just kind of carry things out working from left to right in the order that you see them. There's actually no agreement on that. Some people will say one, some will say the other. You can find calculators that are programmed in one or the other of those two ways. And so you really should not write down an expression like this with an ambiguity like this. 8 divided by 3 times 5. Which one do you do first? Probably you should put some brackets in here, right? Put some parentheses in, then it's clear. So if I do this, let's say like that. Now I understand what I'm doing, right? So I should do the 3 to the 4th, 81. I should multiply by the 6, right? So I'm going to, in my next step, I'm going to have an 81 times 6 there. 2. Here I'm going to do the 8 divided by 3. Well, it's not a whole number. I guess we just have 8/3, right? Times 5. Next we do those two multiplications. Then we do the addition and the subtraction, and we get our answer, right? I'm not going to actually work out the number. You can do that on your calculator if you want. So you got to be careful with things like that. As much as this seems really basic, there are a few things that tend to trip people up. One of the things that trip people up is negatives. So be careful of negatives, right? So for example, let's say I'm doing something like 3 minus 2 times 1 minus 4. Okay? A lot of people will say, okay, that's equal to 3. And they know, okay, I guess if you're doing order of operations, I suppose you should do the 1 minus 4 first, right? So really what we should do is we should say 3 minus 2 times minus 3. Then we remember, negative times a negative, that's a positive, right? So 2 times 3, 6. So 3 plus 6, and we get our 9. But more often than not, what people are going to do is they're going to distribute the 2, right? They're going to use the distributive property, and they're going to say, minus 2, and then they're going to say minus 8. Okay, so they'll write it like that. That's not right, is it? No. 3 minus 2 minus 8, that's not going to give me 9, right? And the reason it's wrong is that when you distribute that 2, right, it's minus 2 times 1 and then minus 2 times minus 4. A lot of people forget that there's actually 2 negatives there, and that should be a positive, right? That's an easy one to forget. Another one that's easy to forget is you have this notion of implied parentheses. Okay, so you might have something like this. 3 minus 2 divided by 5 plus 1, right? So if you're doing something like that, you got to remember that, hey, actually, you got to do the 3 minus 2 first. You got to do the 5 plus 1 first, right? Really what you have here is 1 over 6, right? So where people tend to mess this up is there's a lot of people, and I think this is kind of a keyboarding thing, right? You get into the habit of writing fractions, and so instead of writing a fraction like this, you write your fraction like that. Yeah, it saves a little space, right? Fits on one line instead of two. But then what happens is you're doing a problem. Maybe you're doing like an online homework problem. You're entering your answer into the computer. You wanted to check. It's telling you you're wrong. And it's telling you you're wrong because, you know, you typed in something like this. You typed in 3 minus 2 divide 5 plus 1. That's what you typed into the keyboard. And you assumed that somehow the computer was going to know that it should do this subtraction first, and it should do the addition first, and then it should do the division, right? Computer doesn't know that. Computers are stupid. Computers are going to do exactly what you tell them to do, and they're going to use the order of operations. So you have to explicitly tell the computer by putting in the brackets that it needs to do those operations first, then do the division, or you'll get the wrong answer. You got to be careful about these things. Okay. Next up, we're going to talk interval notation. Okay, so intervals are kind of standard subsets of the real numbers, and they pop up all over the place in calculus. Right? Maybe you're writing down an interval because it's the solution to an inequality. Maybe you're writing down an interval because it's the domain of a function. Right? Probably the most common scenario where you're going to be writing down intervals is you're getting towards the material on, let's say, curve sketching. Right? You're looking at how derivatives shape the graph, and you want to know things like, where is the derivative increasing? Where's the derivative positive? Where is it negative? That tells you where a function is increasing or decreasing, right? And the way you specify this is using intervals. So you'll give an interval, say, well, it's positive on this interval, it's negative on this other interval, right? So basically you break the real number line into these pieces. Each of those pieces is going to be an interval, and on those intervals, something interesting is happening to your function, okay? So there are a number of different types of intervals, and there's different notation used for each, and that might be some of what throws people off. So the basic types are the open interval, which is written like this. And the closed interval. And instead of using parentheses, we use square brackets. Okay? So what are these numbers, right? So in all of these here, assume that A is a smaller number than B, right? These are referred to as the left endpoint and the right endpoint of the interval. The left endpoint is always smaller than the right endpoint, right? Because we always kind of increase as we move from left to right in the real numbers. So an open interval is, as an inequality, if you like, we could write it like this as a set. So it would be the set of all real numbers x that satisfy the following inequality. X has to be bigger than A, but smaller than B. Okay? For the closed interval, it's almost the same. There's one small but important difference, which is that the less than signs become less than or equal. Okay? So the difference between the two is that the closed interval, as a set, it includes these two endpoints, right? A and B are elements of this set. They belong to the set. Whereas for the open interval, they don't, right? So every number that's in between, no matter how close you get to A, anything that's bigger than A, no matter how close, is in the set. Anything that's smaller than B, no matter how close to B, is in the set. But A and B themselves are not. Okay? You can also depict this using a number line. So if we have our real numbers here, and let's say A is there, and B is there. So we want to indicate that we've got everything in between. So we might color that part in. Actually, let's get some better contrast. So maybe we color it in, like so, okay? And then we use these kind of hollow circles at those 2 points to indicate that the A and B are not included, okay? For a closed interval, you kind of start the same. Mark off A, you mark off B. But this time, to indicate that you're including those points, you put a solid dot. So you fill it in. And you fill in all the points in between, okay? So those are the two most basic types of intervals, open and closed. But you can also kind of mash these up, right? There are several ones that you might refer to as the half open intervals, okay? So these are going to be ones that look like, say, AB. So that would mean that you're including the left endpoint, but not the right endpoint. Or you could do it the other way. A and then B, right? So you're including the right endpoint, but not the left, okay? So these are the half-open intervals. These four together are the four types of bounded intervals, okay? These are the ones that they don't go on forever. In either direction, at some point, you stop, right? And once you go beyond that point, you're not in the interval anymore. But there are also a number of so-called infinite intervals, okay? And there's a number of these. So we could do like this, A to infinity with a closed bracket on the A. We can do A to infinity with a round bracket on the A, okay? As you might expect, these are going to be all the real numbers x, which are, so just like here, we want x to be bigger than or equal to a, but there's no upper limit, right? There's no restriction here on how big x can get. So we are just going to say that x has to be bigger than or equal to a. Similarly here, we can just say that x is strictly greater than a, right? So here, it's bigger than a or possibly equal. Here, just strictly bigger, right? Not including, right? We also want to include the possibility that x might be less than a certain number. So we could also have, and here we use minus infinity, right? So we always think of kind of minus infinities at this end of the number line, plus infinities at the other end. So we can go from infinity to, say, b, or minus infinity rather, up to b. And again, we can do either closed or open for those. You know exactly what's coming here. All right, so that's going to be all the real numbers x, where x is less than or equal to b, or strictly less than b. Okay. There's one last type of interval that you might see, which is that you don't put any limits at all. So you just go from minus infinity all the way to infinity. And a simpler way to write that down is to simply say, well, you know what? That's all the real numbers. So let's just write r. Okay. So in the last video, we introduced these 9 types of interval that you can have, right? The open, the closed, the 2 types of half open, all the ones that involve infinity. For the most part, that's going to do the job for any sorts of sets of real numbers that you need to describe. It's probably going to be described using one of these. But there are times where you might need to also combine intervals, right? So you might need to combine more than one type of interval. And an example might be something like this. So maybe somebody says, all right, what I want you to do is I want you to solve an inequality like x squared is bigger than 4. Okay? And you think about this for a bit. You go, okay, so what numbers can I write down whose square is bigger than 4? We're going to introduce formal techniques for doing this later on once we talk about polynomials and solving polynomial inequalities. We'll see that there is an approach, a sort of a systematic way of doing this. But for now, let's just think about it. What are some numbers I know whose square is bigger than 4? Well, maybe we start with thinking about what are the numbers whose square is equal to 4? 2 squared is 4, right? So the square of 2 is 4. Anything that's bigger than 2, if I square it, I'm going to get something that's bigger than 4. So certainly, if x is bigger than 2, its square will be bigger than 4. Is that the only possibility? Well, there's one other solution to the equation, right? What's the other value of x whose square is equal to 4? The other one is minus 2. Okay? So let's think about it. Do we want x to be bigger than minus 2 or smaller than minus 2 if we want the square to be bigger than 4? Well, when you square, the negative goes away. So what we really care about here is the magnitude, right? And as the magnitude of a negative number increases, the actual size of that number as a real number goes down. So we would want x to be less than minus 2, right? So numbers less than minus 2, right? Minus 3, minus 4, right? Minus 7.5, you know, those are all in there, right? So we could have one of those two possibilities. And now you think about how do you write those as intervals? Well, so we would say that we could have the interval from 2 to infinity, or we could have the interval from minus infinity up to minus 2. One of the ways that you might write this is you might use this union notation. So you might write this as, so we might say like this, minus infinity to minus 2. Most people tend to write the smaller numbers first, although this doesn't actually matter. You can put it in either order. Union to infinity, okay? So this is just sort of it's a stylized U, and it stands for union, okay? On the number line, what this would look like on a number line if you were going to write things out is you would be saying, well, what I'm doing is I'm including all the numbers starting at 2 and heading off to infinity, as well as all the numbers that are less than minus 2, so heading off that way, right? So you have two pieces like that. Another way you can combine two intervals, right? You might be familiar with union as one of two set operations that gets used, right? Another operation that gets used is intersection. You'll find intersection a little bit less common in calculus texts when you're dealing with unions, and there's a simple reason for that. Intersection gives you all the things that are common to two sets. So let's say somebody asks you to simplify the intersection of the interval from 1 to 3 with the interval from minus 1 to 2. Okay? So if you think about that on a number line, okay, minus 1, 0, 1, 2, 3. We have two intervals. One interval is here. Let me just kind of offset things so we can see them. One of them is there. Okay? The other one is there. Okay? And you want to, when you're doing intersection, you're keeping all the numbers that belong to both. And all the numbers that belong to both are between here and there, right? It's all the numbers which are bigger than or equal to 1, but smaller than 2. So this would be 1, 2. And you'll notice that when you intersect two intervals, you get another interval. It might be an interval of a different type, but it's still an interval, right? So you usually don't see intersection notation used very often in calculus textbooks because if most of the sets you're working with are intervals. If you intersect two intervals, you get another interval. And most people are going to choose to just write this rather than the more complicated expression you see on the left. All right, in this video we're going to briefly talk about absolute value. So most people encounter this notion of absolute value at some point in high school, right? So the absolute value, the notation, is a couple of vertical bars, right? So we write this as absolute value of x, where x is some real number. Okay? So what does that mean? Well, there's a number of ways of interpreting absolute value. One of the simplest ways is to think of this as distance, right? We can think of this as the distance from 0. 0 is kind of this touchstone on the real number line, right? It's in the middle. It's this reference point. It's the distance from 0 to x. That's one way of describing it. Okay, so let's think of that number line, right? Here's our number line. Okay. There it is. We've got to mark 0. Where is 0? Somewhere here in the middle. Okay. So you choose any other number, and you think about how far away from 0 it is. So let's say I choose a number out here, like, I don't know, 29. Okay? That's my number. So what's the distance from 0 to 29, right? Well, we measured distance using real numbers, right? The distance from 0 to 29 is simply 29. Fair enough, right? And in fact, in general, if x is bigger than 0, then the absolute value of x is just x, right? Actually, we can do one better. What's the distance from 0 to 0? Well, 0 is a distance of 0 from itself, right? Any number is a distance of 0 from itself. So we can actually say that if x is bigger than or equal to 0, the absolute value of x is just x. Okay. Now, what if we wanted the distance from 0 to, I don't know, minus 17? Okay? Minus 17.5, why not? Throw a decimal in. How far away are they? Well, the distance is going to be, again, it's going to be the number, right? The distance from 0 to any number is that number. Except we never want distance to be negative, right? So if we throw a negative number in and we want to give the distance, just remove the minus sign, okay? So absolute value of negative 17.5 is positive 17.5, right? So what that tells me is that if x is less than 0, the absolute value of x is... Now, this will throw some people off, right? How do I get 17.5 from minus 17.5? Well, I throw away the minus sign. How do I get rid of the minus sign? Well, one of these basic algebra rules that you learn somewhere along the way is that if you take the negative of a negative, it becomes positive, right? So the way to get a positive number from a negative number is to put a minus sign out front. Okay. Some people get thrown off by this because they see that minus sign, and every time you see a minus sign, you think negative. So like, wait a sec, absolute value is supposed to be positive, but over here this looks like a negative number. But it's not, right? Because x here is just some variable, right? It could be any real number. And real numbers can be negative. So if this happens to be a negative real number and you put a minus sign out front, it's going to become positive. So even though there's a minus sign there, the number might still be positive if the number you started with is negative. Okay? So this is a simple way of thinking about it, right? It's just distance, right? And you can generalize this, you know, if you wanted to talk about the distance from, let's say, A to B, where A and B are just real numbers, well, what's that going to be? So if you want to think about how far apart two numbers are, you should take their difference, right? The difference of two numbers tells you how far apart they are. The problem is I didn't say here that A was, you know, bigger or smaller than B, right? I don't know. A might be bigger than B, might be smaller than B. Depending on which of these two numbers is bigger, this difference could be positive or negative. And the way you get around that is you just slap absolute values on it, right? As long as you take the absolute value, it's going to be a positive number. Okay? So that's the basic idea of absolute value, is it just guarantees that everything is positive, right? You can think in terms of the graph, if you like. We'll be doing a lot of graphing as we move forward. Okay? So what these two tell me here is that for positive values of x, absolute value of x is just x, right? So if I'm graphing, if I'm doing the graph y equals absolute value of x, when x is bigger than 0, we just graph y equals x. When x is smaller than 0, we graph y equals minus x, right? And you can see from the graph that it never drops below the y-axis or below the x-axis, right? It's always positive. So which of course we understood because we defined this thing as a distance. It should never be negative. Distances aren't negative. So this is these are some basic ideas around absolute value. By the way, this type of function that is given by one formula in one region and a different formula in another region, this is what's known as a piecewise function, right? So what this tells me is that absolute value of x is so-called, it's piecewise, right? Or you might see this as piecewise defined. Sometimes to shorten things we just say piecewise, or we might be more precise and say piecewise defined, right? So it's defined in pieces, right? This piece is defined one way, this piece is defined another way, okay? So of course if you wanted to graph something like that, well, you just draw the graphs of the appropriate pieces on the appropriate intervals, right? Bigger than 0 or less than 0 in this case, and you've got your picture. We'll be seeing plenty of piecewise defined functions later on once we move to talking about limits and continuity. So before we move on from absolute value, let's say a few words about inequalities. Okay? So the simplest type of inequality that you encounter in the calculus course are the linear inequalities, right? So something like minus 3x plus 4 is less than, let's say, 2. Okay? So there's a typical linear inequality. So basic rules for inequalities say, well, you can always add something to both sides of the inequality that doesn't affect things, right? So the first thing that you might do here, add or subtract, right? It's nice to get all the numbers on one side. So you might decide, hey, let's subtract 4. Subtract 4 from both sides, right? 4 minus 4, they cancel out. Minus 3x is less than. So 2 subtract 4, minus 2. Okay. Now the one mistake you got to watch out for, right? The mistake that people tend to make here is in division. Now you are also allowed to multiply and divide both sides of an inequality by any number except 0, right? You can never divide by 0, but also multiplying both sides by 0 destroys the inequality. And also it would lead you with nonsense, right? If you multiply both sides by 0, you just get 0 is less than 0. That's not true, right? but any other number you can throw in. In particular, you might decide that you want to divide both sides by -3 to get rid of that -3 and solve for x. But you got to watch out, right? Because if you divide or multiply by a negative number, it flips that thing around. So you got to be careful. One way to see that is you know, you can divide by -3, divide by -3, as long as you remember that that's going to flip the sign. And that's going to leave you with x bigger than those negatives cancel, 2/3. Okay, so that's one way to do it. Another way to do it is you could, you know, rather than doing it like that, you could say, hey, let's move the 2 to that side, move the 3x to that side, right? Because you never have to worry about, you know, negatives when you're adding and subtracting. So if I add 2 to both sides, now I've got a 2 on the left. If I add 3x to both sides, 3x on the right, and I'm allowed to divide by 3. 3 is a positive number, and I get 2/3 less than x. Okay, fine. Those are the same thing, right? 2/3 less than x is the same statement as x is bigger than 2/3. Those are equivalent. Now, you might find yourself having to deal with absolute value inequalities. Okay. You'll especially find yourself having to deal with absolute value inequalities if you're in a calculus course that covers the precise definition of the limit. Okay? There are lots of inequalities involving absolute values because they're part of the definition of the limit. If you're going through that formal epsilon delta definition of the limit, you're going to see a lot of inequalities with absolute values. So there are two basic rules. Okay. And remember that we're thinking of absolute value in terms of distance, right? So if I say that absolute value of A is less than B, okay? Where B here is a positive real number. What does that mean? Well, remember that absolute value is distance from 0 to x, right? So if I say something like the absolute value of x is less than, let's say, 4, what am I telling you? Well, I'm telling you that x is, you know, the distance from 0 to x is no bigger than 4. And that means that all the numbers, 1, 2, 3, 4 units, right? It's not to scale, right? So all the numbers from here to there, but not including 4, those are included. Those all have a distance from 0 that's less than 4. But that's not all the numbers, right? Because I could also go 4 units to the left and get to -4, right? That would also work, right? So this turns out to be the same thing as saying that x is between -4 and 4. And it turns out that this is true in general. This is the same thing as saying minus b is less than a is less than b, okay? So a is somewhere between minus b and b. And of course, this remains true if you replace less than by less than or equal, okay? The other one is, well, what if it's the other way around? What if we have absolute value of a bigger than b? What does that mean? Well, that means, you know, let's come back to this example, right? What if I turned it around and said, okay, I want all the values of x where the absolute value is bigger than 4, right? That means the distance from 0 has to be more than 4, right? So I'm not including these numbers. In fact, I'm including everything else. So it's everything outside that interval. So that would mean everything that's bigger than 4 or smaller than -4, right? So this would be the same as saying that A is bigger than B, or A is less than minus B. Okay? And again, if you have equals there, right? In terms of intervals, that means that you're doing, here you'd be going from minus b to b. Here, this is one of these places where you need union, right? This is going to be from b to infinity, but also from minus infinity to minus b, okay? The context that you're probably going to see a lot is you're going to be measuring the distance between two numbers. So you're going to have a lot of things where you have to rewrite something like absolute value of x minus 3 is less than 2. Okay, that's going to come up. Something like this comes up quite a bit. So first step, apply this rule, right? Think of this x minus 3 as your a. Think of this as a single unit. 2 is your b. So we're going to get minus 2 less than x minus 3 less than 2. Okay, so now you've got one of these compound inequalities. That's fine. You can add something to each part of a compound inequality. And in particular, the thing that we want to add, we want to get rid of that minus 3. So we add a 3. So minus 2 plus 3 becomes 1 less than x less than 2 plus 3, which is 5, right? So those are the two steps for solving this sort of inequality. The other thing that might complicate things is there might be a coefficient out front, right? But you handle that the same way you handled it in the linear case. All right, so now we come to everyone's favorite middle school stumbling block, arithmetic with fractions. So we're going to start with addition, which tends to be the trickier part. Or, you know, subtract. So subtraction is the same thing, right? Subtraction is just addition where the numbers have opposite signs, right? One of the numbers happens to be negative. So if you understand addition, you understand a subtraction. A lot of people, when they're telling you about fraction addition, they're going to give you some formula, right? They're going to say something like, well, here, I'm going to be one of those people that gives it to you. Maybe I won't. A over b plus c over d. And then they say, oh yeah, so there's this thing, right? Oh, here, why not? I'll give it to you. They'll say, oh, it's a times d plus b times c over b times... No, nobody sits down and memorizes this formula and applies it every time they want to add a couple of fractions, right? The key to adding fractions is this bit right here, right? It's the so-called common denominator. All right, so how does this work? So the idea is that when you're adding things, you can really only add things that are of the same type. Think of the denominator in a fraction as being something like a unit, right? So really, when you when you write down a fraction like say 3/5, right? Well, some of this comes back to just how do you interpret fractions? How do you visualize fractions? Maybe you have this kind of like pie picture, right? Probably one of the better ways to think about it is start with the unit interval, right? All the real numbers going from 0 to 1. Okay? And of course, if you want to do improper fractions or negative fractions, you're going to have to modify this slightly. But for fractions between 0 and 1, right? The denominator tells you how many pieces you should cut your interval into. Those are supposed to be 5 equal pieces. Not my best effort. The numerator tells you how many of those pieces you should keep, right? So we should keep 3 of them, right? So we can kind of have this sort of picture of our fraction where we shade 3 out of 5 boxes. Okay? So it always makes sense to add things that are the same, right? You can add like things. So if somebody says, I want you to do, 2/5 plus 1/5, you say, okay, I'm adding 2 fractions of the same type. They're both fifths, right? So if I had 2 of these, right, and then I added 1 more, I'd have 3 of them. That's fine, right? Where things get more complicated is when somebody says, okay, I've got 2/5 and I want you to add, let's say 3/10. Okay. Now these are fractions that are different types, right? So this is now, rather than saying, okay, I want you to like take 2 apples and add 1 more apple, sort of like, well, it's not quite apples and oranges. Maybe it's something like, okay, somebody says, I want you to take 2 feet and add on 3 inches, right? The answer is not going to be 5 feet. It's not going to be 5 inches, right? It's somewhere in between, because you need to do a conversion. You need to do a unit conversion. And so the key is that, if I have something that's divided into 5 pieces, well, there's an easy way to get 10 pieces. I take each of the 5 pieces that I have and I divide it in half. Now I have 10 pieces, right? And so then my 3/5 that I had before becomes 1, 2, 3, 4, 5, 6 pieces, or in this case 2/5 would become 1, 2, 3, 4 of the 10 pieces, right? So 2/5, this is the same as 4/10, right? And the way you do the conversion, this notion of equivalent fractions, is that you can always multiply the numerator and the denominator by the same thing without changing it. So we go 2 over 2, right? So we have 2 times 2, 2 times 5. So 2 times 2 gives me the 4, 2 times 5 gives me the 10. We add the 3/10, and now that we have 2 fractions of the same type, right, we can add them. Okay. The most complicated scenario when you're adding numbers, right, is when you've got 2 different denominators and neither one is a multiple of the other. So you're adding something like 1/3, and you're going to add, I don't know, let's do 1/3 plus 1/4. Okay. So if you want to, you can think about this visually, right? You can think about that you've got one piece and you've divided it into 3 pieces. You've got another one that you've divided into 4 pieces. And you're taking one of them and one of them, and you're just kind of going to stick them together, right? You take that piece and that piece, and you're going to stick them together. Now you're wondering, like, how long is that piece, right? As a fraction of the whole, how much do I actually have? Well, you do the same equivalent fractions idea, but now you're going to have to adjust both denominators until you get one that matches, right? And that's where this rule comes in, right? That one way that you can always get a common denominator is just to multiply the 2 denominators that you have, right? 3 times 4 gives me 12, right? So I can write both of these as fractions over 12. I just have to think about, what do I need to multiply each one by, top and bottom, to get to the 12. Well, 12 is 3 times 4. So here I need 3 times 4. But anything you do to the bottom, you should also do to the top, right? Here I need 4 times 3. Okay? And again, do the same thing top and bottom. So what I get is now 4/12 plus 3/12, leaving me with 7/12. Okay? And then you've got it done. Again, if you wanted to kind of, use this sort of picture to visualize, what you're doing is each of these 3 pieces you're dividing into 4. Each of these 4 pieces you're dividing into 3. And now each of these bars has been divided into 12 equal pieces, right? And there are 1, 2, 3, 4 pieces here, 1, 2, 3 pieces here, and so you'd have 7 pieces there out of the 12 in total, right? That's the idea with addition. Again, subtraction, if I was doing, let's say, 1/3 minus 1/4, well, this would be 4/12 minus 3/12. I get 1/12, right? Subtraction is not any harder. We're going to pause there. We're going to come back. We're going to do one example with some variables in it, and then we'll talk multiplication. All right, so one more video on fraction arithmetic. This time we're going to look at multiplication. Right? Of the two, multiplication is actually a little bit easier than addition, right? Because when you're multiplying, there's no need to worry about common denominators or anything like this. It's simply a matter of multiplying across. So again, if I were going to give you a formula, it might look something like this. A over B multiplied by C over D. I'm just going to do A times C divided by B times D. Okay, that's the rule for multiplication. I guess maybe some people tend to get these two rules mixed up, and maybe one of the reasons that you might tend to get them mixed up is that the denominator ends up the same in both cases, which is maybe yet another reason why you just shouldn't try to remember these formulas in the first place, right? Don't rely on the formulas. Maybe I shouldn't even give them to you. Better to just think about what's going on, right? So think about doing something like, say, 2/3 times, I don't know, 3/4, okay? Something like that. Now there's a few different ways that you can do this, right? We could blindly apply the rule. So if we apply the rule, we can get 2 times 3 is 6. 3 times 4 is 12. It's like 6 over 12, that's our answer, right? But that's an unnecessarily complicated fraction because 6 over 12, we know that this can reduce down to 1/2, right? And then you might be left wondering, like, oh, maybe I did more work than I needed to. Was there a way to save myself some trouble? And the answer is yes, right? You can reduce after like this if you want, but you can actually reduce ahead of time, right? You know that you're going to be combining these into a single fraction, okay? You know that you can reduce. You know that you can cancel factors, right? If things are factored out top and bottom, you can cancel them. And so when you see that there's a 3 here and a 3 here, we can say 3 over 3 is just 1 over 1, right? 2 over 4. 2 over 4 is the same as 1 over 2. So I can do, rather than doing 2/3 times 3/4, I can just do 1 times 1/2. I get to my answer of 1/2, right? So we can clean things up like that. This certainly becomes relevant if you're getting to the point where you're multiplying algebraic expressions, right? You've got x squared over x plus 2, and you need to multiply by x squared plus 4x plus 4 over x squared plus 3x, something like that. You can multiply it all out if you want, right? Multiply everything on the top by x squared. Multiply those two binomials on the bottom. FOIL it out. Then think about simplifying, right? But once you've multiplied those things out, right? Once you got this like degree 4 polynomial up top, right? Degree 3 on the bottom, those are going to be hard. It's going to be hard to see how to simplify, right? It's easier now. Well, things are already sort of factored. And so rather than multiplying first and then seeing if you can simplify, factor first, see if you can cancel, then move on. With the standard note of caution, you can only cancel things that have been factored out as common multiples, right? If you have the same multiple on the top that you do on the bottom, you can cancel them. If they're terms, right? Factors can be canceled, terms cannot. So just because there's an x squared here and here, I can't cancel them out, right? That would be like if I had, I don't know, 3 over 4, and I said, oh, well, 3 is 1 plus 2, and 4 is 2 plus 2, right? I can't cancel the 2's and say that's a half, right? 3/4 is not the same thing as a half, right? So I can't cancel things that are being added, right? If there's a plus sign in front of it or behind it, you can't cancel, right? On the other hand, if I had something like 6/8, right, and I said, oh, well, that's 3 times 2 over 4 times 2. And I said, okay, now that 2, right, if it's being multiplied, same thing top and bottom was multiplying, then I can cancel. So what I have to do in something like this is, first thing I have to do is say, okay, can I factor? And I can. So x squared. So maybe what we do, we can combine them if you like, but rather than multiplying through, think about factoring. This is the square of x plus 2, right? On the bottom, x plus 2, and then I have x times x plus 3 when I factor that, okay? And so then I look to see what is some of the common stuff that I can take out from the top and the bottom. Both the top and the bottom have an x, and they both have an x plus 2, right? So I can do x times x plus 2, x times x plus 2, and then write down everything that's left over. There's another x and another x plus 2 on the top, and on the bottom, there's an x plus 3, right? So I can do that, and then realize that yes, these x's, these can be canceled. Those x plus 2's, those can be canceled because I'm multiplying, right? And then I've got my simplified answer. X plus 2 over x plus 3. Okay? One more fraction video before we wrap. We do have to talk about division, because division, it's not quite the same as subtraction. Once you understand addition, you understand subtraction. They're basically the same thing. Division adds in one further wrinkle, so we should address that in a separate video. Okay, so we're ready to wrap up fraction arithmetic. The last topic to tackle is division. Okay? Now, you've probably learned the rule of this mantra at some point, right? That division is the same thing as multiplying by the reciprocal. All right, so you flip and multiply. Some people like to say it, right? So if you're giving a formula, and again, I'm questioning whether we really should, but here we go. A over B divided by C over D. You flip the second and you multiply. Okay? That's the rule. So for example, if I was going to do something like 2/3 and I wanted to divide by, let's say, I don't know, 4/9. Okay. How do we do that? Well, maybe we should spend some time. If we had more time, we might try to think a little bit conceptually about how this makes sense, right? There are lots of ways to understand why this rule works, okay? If you think of division as canceling a multiplication, right, then this kind of makes sense, right? C over D and D over C, they're opposites of each other in the sense that if you multiply them, you get 1, okay? More basic than that, you can go into thinking of a division as counting like how many times does one number go into another, things like that, right? But these kind of basic, kind of getting into these core concepts of fractions and fraction addition is I think maybe a little lower than we can go in a calculus review. There's lots of good material out there on the web if you wanted to do it. But I think this is a good one to look at, because you'll notice that you kind of, when you're doing division, the way we tend to write things in like calculus, you get these compound fractions, right? Fractions within a fraction, right? The numerator and the denominator of this fraction are themselves fractions. And you have to think about how do you simplify. When you write this out, what goes where? So the rule says, well, what you should do is multiply by the reciprocal of the one on the bottom. Okay? So instead of dividing by 4 over 9, you multiply by 9 over 4. Okay? Now you can multiply that out, or you can again notice that, hey, there's a bit of simplifying I can do here. 9 over 3 is just 3. 2 over 4 is a half. Okay? And so the result is 3 over 2. Okay, that's not so bad. If you remember the rule, this is probably one of these cases where it's nice if you have a deeper conceptual understanding of what's going on here. It might help you later on if you're studying algebra, something like that. But if you're just trying to get the calculation done, remember the rule. Where this is going to come up with, say, with calculus, is you might be dealing with an expression like the following. You might be dealing with something like this. 1 over x plus a minus 1 over x divided by a. Okay? And you want to simplify this thing. And this really tends to trip people up. It messes people up because they're like, wait, that's a fraction. Wait, but it's inside this bigger fraction, and I don't know where that a is supposed to go. Like, where the hell does it go? So if you remember that division is multiplying by the reciprocal, and if you remember that, now this might be a real number. It might not even be a fraction anymore. But the rules still work. And so for any real number, you can still write down the reciprocal of a real number, right? If you have some number x and you want to take its reciprocal, it's just 1 over that number. So what we do here is say, okay, rather than dividing by a, we'll multiply by 1 over a. Okay? Now it becomes a little bit more clear how to proceed if we wanted to simplify. Okay? And this is the sort of thing you're going to have to do. This is going to come up when you're using limits to calculate derivatives. This is actually a fairly standard example that I'm doing for you. So the next thing we do, well, we'd have to combine these, right? Again, common denominator. In this case, that common denominator is going to have to be the product. So I'm going to have to multiply this one, top and bottom, by x. I have to multiply this one, top and bottom, by x plus a. And coming all the way back to one of our very early videos, we talked about order of operations, and you probably thought I was being silly because, hey, you learned order of operations like way back in elementary school, right? You don't need to cover that. Here's another place where people are going to screw up, because a lot of people are going to apply this minus sign to the x, but not to the a, because they don't realize that there's actually, again, these implied parentheses there. We often don't bother to write those parentheses, but they're there. And it becomes relevant when we go to the next step, because in the next step, and now we can kind of, the whole denominator is going to be the a times the x plus a. So we have a times x plus a, and we have x subtract x plus a, right? So that minus sign hits both of them, right? Minus x minus a, right? It gets distributed to both of those terms. And if you're not careful, you might miss the minus sign on the a. X minus x cancels. You just get negative a over a times x plus a. And the last thing you might choose to do is realize that this is just minus 1 times a, and then say, hey, I've got an a on the top, I've got an a on the bottom. So why don't I cancel and get down to a final answer of -1 over x times x plus a. Okay? You'll definitely be seeing like calculations like that. Once you move on to limits, derivatives, you're going to be seeing these sorts of things. As long as you're careful, right, and as long as you remember that when you're dividing, that really means multiplying by the reciprocal, you'll get things in the right place and you'll be okay, right? A lot of people, the two most common pitfalls here might be that the a ends up in the numerator when it should have been in the denominator, and you might forget something simple like order of operations, distributive property, forgetting that there are really brackets there. Okay, all right, that's it for fractions. We're going to move on. All right, so in the next few videos, we're going to talk about rules for manipulating exponents. I've thrown up a reference here to a blog I like to read sometimes, Math with Bad Drawings. It's not a bad little blog. But he has a really great post from a year or two ago titled The Exponential Bait and Switch. If you search Google on this title, you'll find the blog. It's good reading. And it's interesting because it points out something that's, I think, kind of fundamental to a lot of mathematics and development of mathematics, which is, when you're starting with exponents, how did you first learn exponents, right? Think way back. Actually, think all the way back to like multiplication, right? You might have first learned that, multiplication is a repeated addition. And then you learn, it's not quite so simple, because what if the numbers you're multiplying are not whole numbers? What if one of them is negative? What if one of them is a fraction? What if you're multiplying by the square root of 2? How do you make sense of that, right? And the same thing happens with exponents, right? Somebody says, exponents are repeated multiplication, right? So they say, well, a cubed just means, a times a times a, right? And a to the 4 just means a times a times a times a. And so it stands to reason that, all right, you want to do a cubed times a to the 4. Well, that's a times a times a times a times a times a times a. And now basic algebraic properties of real numbers take hold, right? We know that multiplication is associative. These brackets are somehow unnecessary, right? And commutative, I can, a cubed times a to the 4 is the same as a to the 4 times a cubed, right? I'm just multiplying by a. The order in which I multiply by a doesn't matter. The only thing that matters is how many times did I multiply by a, and how many times did I multiply by a? Well, 1, 2, 3, 4, 5, 6, 7 times, right? A to the 7, right? And so then you generalize this, and you say, okay, well, in general, right, if I wanted to do, a to the m times a to the n, that should be a to the m plus n. Similar thinking leads to a rule for division, right? If I did a cubed divide by a4, right, I had 3 in the numerator, 4 in the denominator, I would start canceling off common factors until I had just 1 left in the bottom. And so you kind of, it's however many you had on top minus however many you had on the bottom. And so, well, that gets you to this rule, right? You subtract the exponents. But then, of course, that leads you to a possibility, right? If I was doing a cubed divided by a to the 4, right? I've got more a's on the bottom than I do on the top. This might be negative. So then you say, what if I have a negative exponent, right? What if I have like a to the minus n? Well, there's a simple rule for that too, right? Negative exponents are just reciprocals, right? And so you start with this idea that exponentiation is repeated multiplication. And it leads you to these rules. And then eventually you say, actually, the rules are all that matters, right? You should probably remember where it came from, but ultimately it's the rules that matter, right? And you say, well, exponents are just the things that follow these rules. And then that lets you extend things to scenarios where maybe this exponent is not an integer. Maybe it's a real number, right? Maybe it's a fraction, right? Maybe we're working with our favorite base, right? E. We might be doing that. So we're gonna be looking at situations where maybe the base and the exponent are real numbers. They might be irrational numbers. We still need to make sense of this. And you make sense of it through the properties, right? Through the rules. There's one that I've missed, right? Which is, well, there's a couple, but another one is that if I had a to the m, and I was going to raise it to a further power, n, in this case, you multiply the exponents. And I guess that comes down to the whole, multiplication is repeated addition, right? Because this means I multiply a to the m by itself n times. I apply this rule, which is that I should add m to itself n times, which really means I should multiply m by n. Right? So you can kind of put all those together. There's another one that comes up maybe less often for calculus. Well, I suppose it still comes up. You might be dealing with cases where you have either a product or a quotient that you want to raise to a power. And in this case, you can distribute the exponent to both terms, right? A to the n over b to the n. Okay? Those rules work. Those rules are highly dependent on the fact that the order of multiplication doesn't matter for real numbers, right? Because on this side, you're doing a times b times a times b times a times b times a times b times a times b. On that side, you're doing a times a times a times a times a, and then b times b times b times b, right? You had to move all the a's to the beginning and all the b's to the end, right? You had to rearrange. If you were doing another course, let's say like linear algebra, where you're dealing with, say, matrices, where the order of multiplication does matter, you've got to be careful about these things. But we're doing calculus, we're working with real numbers, so it's okay. We have these rules, they work. All right, so we can play with those. Probably the last one to point out is fractional exponents, right? What the other one is to note that if I had a to, say, the 1 over n, right? That means the same thing as the nth root of a, right? And that kind of, in a way that makes sense. Kind of thinking about this rule, thinking about that rule, that the nth root of a should be the thing that if you multiply, it by itself n times, or if you do nth root of a times nth root of a n times, I should end up with a, right? But if I do a to the 1 over n times 1 over n times 1 over n, right, n of those, right, I should get, if I add 1 over n times, I get 1. I get back a. It makes sense, right? And the last one is if I have a rational exponent, so not just something where the numerator is 1, but a general rational exponent, you can write this as either you do a to the m, and then you take the nth root, or you could take the nth root and then raise it to the power m, and you'll get the same result either way. Okay? Those are the basic rules for exponents. We'll look at some examples in the next video. All right, so in the last video we went over these rules for working with exponents. Now we should see how these work in practice. Okay. So in the first example, we're just going to point out some basic principles here. This is coming all the way back again to the stuff that you thought you were too old for, right? Order of operations, brackets, exponents, things like that. Because again, it's, we think we know it, but we mess it up all the time. So one is to think about, if I had like 2 plus 3 squared, right? Versus, say, 2 plus 3 squared. These are not the same thing, right? Because order of operations says that we should always do the exponent first, right? This one is 2 plus 9, right? Which is 11, right? Because you apply the square first, and then you add 2. Whereas here, the parentheses say, well, I should really first do 2 plus 3. I do the thing inside the bracket first. I do the 5. Then I square it. And I get 25, right? Maybe the other one we should throw in here, right? Because this is one that again, is a common mistake. Maybe not when there's numbers in, but definitely this is once there's an x in there, it's going to happen. 2 squared plus 3 squared, right? So there's always this tendency, there's this, this wishful thinking. We want to just apply the exponent to both things, right? But we know that this is not, right? What does that give me? 2 squared is 4, 3 squared is 9, 4 plus 9 is 13, right? All very different answers, right? Of course, the reason that these ones don't agree is that when you're doing 2 plus 3 squared, right? Again, think in terms of, if you like, repeated multiplication. This really means 2 plus 3 times 2 plus 3. And if you wanted to, you could distribute that out, right? Nobody would ever bother when it's just numbers. But say this was x plus 3, right? If it's x plus 3, well, then we know what to do, right? X plus 3. We want to square it. X plus 3 times x plus 3. And we multiply that out. Now, most of you probably kind of internalized this. You've remembered your FOIL rule. You might have even memorized the formula for a square, right? You can just write down the answer without even thinking about it. Certainly saves time. But one thing to remember is, really what you're doing is you're doing the first term here, right? X times the bracket, x plus 3. Then you're doing the 3 times that bracket, x plus 3. And then you're expanding again, x times x, x squared, x times 3, 3x, 3 times x, 3x, 3 times 3, 9, right? Lots of people say, oh yeah, this is FOIL rule, right? First, outside, inside, last, they get straight to that answer. That's fine too. The only downside with kind of, relying on something like FOIL is what if there was another term here? What if there was another x plus 3? What if this was x squared plus 2x plus 3, right? What if one of these had 3 terms in instead of 2? FOIL's nice, but it only deals with one situation among many. It's a common situation, that's why we have an acronym. But there are lots of other situations that can come up, so it's nice to remember, you can do this even if you forget FOIL. Last step, of course, combine the middle terms. A lot of you probably can write down that answer in one step. That's fine if you can. But if you've forgotten, you're out of practice, you can always get there by relying on fundamentals, right? Okay, so it's important to remember things like this. It's not just x squared plus 9. There's that term in the middle, right? It's easy to forget it. The other one where you might forget it is, what if I'm doing something like square root of 1 plus 3? This is another one of these cases where you have this idea that there are implied parentheses, right? The 1 plus 3 is inside the square root, right? It's inside this, if you like, a square root function. We haven't quite talked about functions yet. But you got to do the addition before you do the square root, right? This is the square root of 4. It's 2, right? It's not square root of 1 plus the square root of 3, right? 1 plus root 3, it's definitely not the same thing as 2. One is an integer, the other one's not even rational. Okay? So be careful about that. Everyone says, oh yeah, of course, I know, I'd never do that. Yeah, you say you'd never do that now, and then I give you something like the square root of x squared plus 4, and I know somebody is going to tell me that's x plus 2. It's not, right? This is just something that does not simplify. Okay? Sometimes we just want to simplify things. We want our answers to be as simple as possible. And sometimes they can't be as simple as we'd like it to be, and that's okay. That's something you just kind of have to live with. Okay. Some basic examples with exponents. I think we're gonna pause here. We're gonna come back. We're gonna do some slightly more complicated examples before we move on. All right. So as promised, here are a few examples working with laws of exponents. I've left the laws up here in case we need to refer to them. We'll start simple. We'll work our way up. You might think that the one at the end with numbers should be the simplest, everything else has variables, but that's an example that messes people up all the time. People really struggle with that one. So let's have a look. First one, x cubed times x to the 6. Well, that's a straightforward application of this first rule, right? We're multiplying two powers with the same base, so we simply add the exponents. 3 plus 6 is 9. That's x to the 9. Now, I've thrown the other one in because people tend to get mixed up on these, right? When do I use that rule, right? The rule applies for multiplication. There is no corresponding rule for addition, right? So there's nothing you can do really to combine those two terms. So you leave them as is, right? The only thing you could possibly do to simplify this is to kind of use this rule backwards. You could say, well, x to the 6, that's x cubed times x cubed, which might come in handy because you might want to factor this, right? So you might want to say, oh, that's x cubed times, so x cubed is x cubed times 1, right? And then x to the 6 is x cubed times x cubed, right? So you might be able to factor, but you can't combine, right? You can't, there's nothing you can do to get rid of that plus sign. It's going to be there, whatever form you write it in, that plus sign is going to stick around, okay? Let's look at these ones. All right, so this one here, we need two different rules. It's a combination of this rule here for raising a power to a power, as well as what to do when you have two different numbers in the base, all right? So let's apply this rule first, right? So we're going to distribute the 4 to the two different bases. So this is going to be x cubed to the 4th power times y squared to the 4th power. And now we multiply the exponents. So 3 times 4 is 12. 2 times 4 is 8. And again, I don't know what x and y are, so there's nothing I can do to combine those. I have to leave it as is. Now, the next one, I've got a square root. How do you deal with that? Well, the key to dealing with this one and simplifying, if you can, is remembering that square roots can be written as fractional powers. Okay? So I could write this as x cubed y squared, okay, to the power 1/2. All right. Now I can distribute the power the same as before. X cubed to the 1/2 y squared to the 1/2. Okay, there's actually something subtle here when you're simplifying, okay? Here, we want to apply the rule, right? We want to apply this rule. So we say, okay, x cubed to the 1/2, well, that's x to the 3/2. And that's fine. You're more or less using this rule here when you do that, right? You're saying the square root of x cubed, I can write as x to the 3/2, right? It doesn't matter whether I do the square root first or the cube first, I'm going to get that answer, okay? Y squared to the 1/2. Now here, there's something that you have to watch out for. The temptation is to just write y, right? The square root of a square doesn't always give you back the thing that you started with, right? Because what if the thing you started with was a negative number, right? Let's say y is -3. What happens when you square -3? I square minus 3, I get plus 9. What's the square root of 9? It's 3, not minus 3, it's 3. So I don't actually get back the thing I started with. Turns out, what you get is the absolute value. So there's a general rule here which says that the square root of a square is the absolute value, okay? Right. So you have to be a little bit careful with that, right? I'm being slightly lazy when I write down this rule here. Really, I should be careful because m and n, if they're, let's say, fractional powers, there's not always going to be necessarily this agreement on this on both sides. Really, what I should say here probably is that either a has to be positive or m and n have to be integer exponents. So you've got to be a little bit careful about some of these things. All right, how about this one? Well, there's two ways to think about it. One is to just sort of apply the rule here directly, right? X squared, so it's 2 minus 3. X to the 5th. Okay? It's fine. The other thing you might do if you wanted to is to say, well, that's the same thing, right? If the double negative is throwing you off, is to remember that what you've got here is x squared times. So if you've got a negative exponent, you can bring it upstairs, right? So this rule here could be rewritten, and if I put minus here, I'd have the minus there, right? So I could move that minus to the other side. 1 over x to the minus 3 is the same thing as x to the 3, okay? So a negative exponent on the bottom becomes a positive exponent on top. All right, this one here, what do? Well, there's two choices, right? And again, this is one of these it's an order of operations question, and it's one where, in this case, it doesn't matter. You'll get the same result either way. We can either first apply the outside power to everything, so cube all 4 terms, then see if we can simplify. Or we might want to simplify inside first and then apply the power. Generally speaking, it's easier to simplify first, right? You want to simplify and then apply powers, right? Expanding and then trying to simplify is usually a little bit trickier. So x over root x, that's x to the 1. Remember that this is x to the 1/2. 1 minus 1/2 gives me 1/2, right? X over root x is just root x. And same as up here, y squared over y to the minus 1. I bring that up, 2 plus 1 gives me y cubed. I still have to cube. So x to the 3/2. 3 times 3 gives me y to the 9. Okay, how about this last one? So this one is tricky. We've got the fractional power, negative exponent, numbers inside. How do we deal? Well, the first thing is we might notice that 8 and 27 are themselves cubes. We can write them as powers. One thing we might want to do maybe before we do anything, let's get rid of that negative. So the negative exponent means reciprocal, right? So I can get rid of the negative exponent by flipping my fraction. That gets rid of the minus sign, but still the 2/3. Be careful, you don't flip that fraction, you're flipping that fraction. Okay? Then I might realize that 27 is 3 cubed. 8 is 2 cubed. Okay? And I can apply that power to both of them. 2/3. 2/3. Now we use this rule, right? 3 times 2/3, 3 times 2 over 3 just leaves me with 2. So 3 squared over, same logic, 2 squared. So my result is 9 over 4. All All right, so in this video, we're going to talk about lines, right? So this is a very elementary thing that you've been seeing for years. And it seems really, really basic, but one of the reasons that lines seem really, really basic is that in your school career, this is something that was developed over several grades. You didn't learn about lines all at once, believe it or not. It took some time to develop the idea of just simply a straight line. So how do we think about lines? How is a line defined? Well, the idea of a line goes all the way back to basic kind of Euclidean geometry, right? Going all the way back to the ancient Greeks. So one of the things we can do is we can talk about a line segment, right? So between any 2 points, we can connect them by a line segment, right? Something like that. It's not yet a line. A line is what you get if you take a line segment, and this is one of the basic kind of axioms of Euclidean geometry, that if you have such a segment, you can extend it off to infinity in either direction, and then you've got yourself a line. Okay? So there's a line. So what is it that makes lines special? What is it that sets a line apart from other curves that we could draw in the plane? Well, one of the defining characteristics of a line is slope, right? So you've probably thought of slope as this idea of rise over run, right? So as a formula, we might give it as change in y over change in x, right? So for these 2 points I've indicated on my line, we might write this slope as, what's the change in y? Well, we can kind of draw a little right-angled triangle here. Okay. The height, right, is this change. So here, this point here that I've drawn, I've changed the x-coordinate but not the y-coordinate, right? So the x-coordinate has changed to c, the y-coordinate is still b. So the change in y, right, is this change between b and d. d minus b, okay? That's the change in y. The change in x you can see along here, right? The difference in x is c minus a, right? There's the slope for our line. Okay. That's fine, but I could do this for any 2 points on any curve, right? I could draw a parabola, circle, I can choose 2 points. I can calculate delta y over delta x, right, for any curve that I want. What's special about a line? Well, the thing that's special about a line, what makes lines different from other curves, is that this number is constant. I will get the same slope for any 2 points on the line that I choose, right? So if I were to pick some other point, let's say here, and call it xy, if I calculate delta y over delta x using these 2 points, or using these 2 points, I'll get the same number that I got when I did those 2 points, right? So that means that my slope could also be written as y minus b, right, over x minus a. And it could also be written as y minus d over x minus c, right? Those should give me the same points. And with a bit of manipulating here, you can actually get the equation of the line, right? If I multiply both sides by x minus a, what I get is y minus b is equal to m times x minus a. Or if you like, y minus d equals m times x minus c, right? And you might be concerned that those appear to be different, right? I've got an a and a b here, I've got a c and a d there. So I've got 2 different equations for my line, right? Because essentially I've written down these equations using 1 point or another point. And the point, if you like, is that it doesn't matter. You will get the same answer either way. because in this case, if I were to simplify, let's say I solve for y. So y is going to be, so there's this m times x. Let's put that in. And then I've got minus m a plus b. Okay. Over here, y is m times x minus mc, right, plus d. Okay. So we want to believe that these are the same numbers, but that comes up to, here was, I had this equation to begin with, right? So m times c minus a is equal to d minus b. So mc minus ma is equal to d minus b. Okay? Or, if you like, moving that over and moving that over, b minus ma is equal to d minus mc. b minus ma equals d minus mc, right? So it's the same line, right? Doesn't matter which point you use. This form here, this equation, by the way, this is usually called the point slope form of a line. A lot of you are probably more used to seeing it in this form here, right? So mx plus, and then let's just put that all, b minus ma. This is sometimes called the slope-intercept form, right? Because this number here, this b minus ma, right? That's the y-intercept for your line, right? I know you're probably a little bit concerned because I'm using this b, and this b is not the intercept, right? You use mx plus b. B is the intercept, right? B is not set in stone as being anything, right? We can use letters interchangeably. So most of you are probably used to writing it in this slope-intercept form, and a lot of you are probably going to insist on writing it in this slope-intercept form. But it turns out, for most purposes in calculus, this is the more useful form, okay? And it's the easier one to get to, because what's going to happen most of the time, most of the lines that you're going to encounter in calculus are going to be tangent lines. They're going to be tangents to curves. The information that you get for constructing those lines, well, there's going to be a slope. That slope is going to come from the derivative of some function. The derivative is going to tell us about slope. The other thing you're going to have is going to be a point, because you're constructing that tangent at some point on a curve, right? So the point and the slope are going to be information that you have. You can immediately just plug it into this version of the line and you have your answer, right? There's no need to go to the trouble of figuring out the y-intercept so that you can do slope-intercept. Just go with point-slope. The other reason that this is more useful, later on in calculus, you'll find that this is exactly what you need if you want to talk about linear approximations, right? One of the reasons that we construct tangent lines, one of the reasons we talk about derivatives is we use them to do approximations. This is going to be the more useful form to talk about that. All right, so in the next couple of videos, we're going to look at some basic algebra. We're going to look at expanding and factoring when you have variables involved. So, basic example, the one that a lot of people learn is this FOIL rule, right? When you've got something like 2x minus 1, you want to multiply by x plus 4. So the FOIL stands for first, outside, inside, last, right? So you multiply the first term, so you do the 2x times x, 2x squared. The outside terms, the 2x and the 4. 4 times 2 gives you 8x minus 1 times x. Those are the inside ones. So minus x, and then finally minus 1 times 4, the last terms. Okay. You can simplify in the middle. And you're done. Now, that's fine if your problem involves multiplying a couple of binomials. Then FOIL works just great. But this is not going to be the only situation that you run into, right? There's going to be other types of multiplication that you have to do. So what's probably better to do is to realize that what you're doing when you're doing FOIL, right, is you're relying on this distributive property. The fact that you can take this x plus 4, multiply it through these brackets, so you can do the x plus 4 multiplied by 2x, and then do the x plus 4 multiplied by minus 1. So when you take this and you multiply by 2x, right, that's going to give you this term and that term, the first two terms. When you take this and you multiply by minus 1, it's giving you the other two terms, right? So these ones here, right, come from multiplying by 2x, and that produces this term and that term. When you multiply by the minus 1, it's going to produce this term and that term. And if you remember this in terms of this basic distributive property, then you can extend from FOIL to other situations. So you might be dealing with a problem where you've got x minus 2, and instead of having to multiply by another binomial, maybe you've got something like 3x squared minus 2x plus 4, right? Suddenly FOIL doesn't work because this is not a binomial. So you can't rely on FOIL, but you can still rely on the distributive property. You can take this bracket here, multiply first by the x, then by the minus 2. So we can do x times 3x squared minus 2x plus 4 minus 2 times 3x squared minus 2x plus 4. And then distributive property again, push the x through the brackets, push the minus 2 through the brackets. Don't lose the minus sign. So we're going to get 3x cubed minus 2x squared plus 4x, and then minus 2 times 3 minus 6x squared. Right? Minus 2 times minus 2, double negative gives you positive, plus 4x, minus 2 times 4, minus 8. Right? And if you want, you can group terms, right? So there's only one degree 3 term, x cubed. There are two degree 2 terms. We can group those together. Minus 8x squared, two 4x's, so plus 8x minus 8, and you're done. Okay? You can also expand if you have 3 or more factors that you need to multiply out. So maybe you have to do something like x minus 2, 2x plus 1, 3x minus 4. You want to multiply that out. Now, this is one of these situations where, again, you're relying on these basic algebraic properties of the real numbers that we don't necessarily always explicitly state, but we use frequently. One of the multiplication properties for the real numbers is this associative property for multiplication, which says if you need to multiply 3 or more things, it doesn't matter how you group. You could choose to group these two together, so do the product of the first two and then multiply by the third, or you could decide that you want to do these ones here, multiply the last two, and then multiply by the first. You can group it either way, you'll get the same answer. So why don't we decide that we want to group the first ones together, right? So then we're going to do the multiplication inside the larger brackets first, then we're going to deal with that last term. So then what we get is, so x times 2x, 2x squared, x times 1, you'll notice I'm guilty of actually using FOIL here. Minus 2 times 2x minus 4x minus 2 times 1 minus 2 times 3x minus 4. Probably you want to simplify this before you multiply it all out. So 2x squared minus 3x minus 2 times 3x minus 4. And again, you multiply it all out, and we're now in this sort of scenario here, right? There are 3 terms, so again, we can't fall back on FOIL. But with a bit of practice, you can kind of, you can do this step in your head just like you kind of do with FOIL, right? So you can say, okay, I'm going to take each term in the first bracket. First, I'm going to multiply by the 3x. So 2x squared times 3x, I get 6x cubed minus 3x times 3x minus 9x squared minus 2 times 3x minus 6x. Okay, now I'm going to take those 3 terms, I'm going to multiply them all by minus 4. So 2x squared times minus 4 minus 8x squared minus 3x times minus 4 minus minus gives me plus 12x. And then finally minus 2 times minus 4 plus 8. So now we group, right? 6x cubed minus 9 minus 8 minus 17x squared minus 6 plus 12 plus 6x. And then finally plus 8, and you're all done. So before we move on to factoring, we're going to spend a few more minutes on expanding. There's our last example from the previous video. We're going to look at some basic formulas. Okay. And in particular, what we're going to look at is the so-called binomial formula. All right. So there are a few instances of the binomial formula that you're probably familiar with. Okay. In general, the binomial formula has to do with expanding. All right. So in the last video, we mentioned this binomial formula, right? So this result here is called the binomial theorem, or the binomial formula, whichever you like. And it tells you how to multiply out powers of binomials, so things, let's say, of the form x plus a to the n. These show up fairly frequently in calculus, so it's nice to know how to do this. These coefficients, these numbers that show up in front of each term, these are called binomial coefficients. You sometimes read these as n choose k, and they come up in a number of contexts. One of the contexts where these numbers come up, and the reason that we read this as n choose k, is that these numbers tell us the number of different ways that it is possible to choose k items out of a set of n items, right, where you don't care about the order in which you choose them. So these sometimes go by the name of, you might have heard of permutations and combinations. This is the combination side of things. Now, a lot of people, when they're some practice, they probably don't necessarily use the definition here to work out the coefficients when they're expanding. A lot of people remember this result called Pascal's triangle. And Pascal's triangle gives you a way of organizing these binomial coefficients. So Pascal's triangle starts with a 1 at the top, and actually it's going to have 1s down the sides. So 1, so the next row is a couple of 1s. The way you proceed for each successive row is you add a 1 on the outside, and in between you look at the 2 terms that are immediately above and you add them together. 1 plus 1 is 2, right? To get to the next row, 1 on the outside, 1 plus 2 is 3, 2 plus 1 is 3, 1 on the outside, right? Next row, 1 on the outside, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and a 1 on the outside, right? Do one more row. So 1 on the outside, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, 1 on the outside, right? And this goes on, you can add as many rows as you want, right? This goes on forever. Okay, now, one of the things that you'll notice is that these numbers that you get, they are exactly the binomial coefficients, right? So going across this top level is kind of k equals 0, if you like, or n equals 0, right? So this is 0, 1, right? Because if you just do x plus a to the 1, you just get x plus a, 1, 1, right? The coefficients are 1. In the last video, we saw how to do x plus a squared, right? X squared plus 2ax plus a squared, right? So that's what you get for squaring. Here we recognize the coefficients. We did this one, right, for a cube, 1, 3, 3, 1. And the next row is 4th power, 5th power, and so on. Okay? So for example, let's say somebody asks you to do, let's say they want you to do x plus 2, and they want it to the 6th power. Okay, well, we didn't go as far as 6, right? So we'd have to do one more row. 1 plus 5, 6, 15, 10 plus 10, 20, 15. You'll notice there's symmetry. So once I've got up to here, I can just repeat going back the other way, right? I have those coefficients. So once I have those coefficients, I can just write this out. I can say, okay, it's going to be x to the 6 plus 6 times 2 times x to the 5th plus 15 times 2 squared times x to the 4 plus 20 times 2 cubed times x cubed, right? Plus 15 times 2 to the 4 times x squared plus 6 times 2 to the 5th times x. And finally, the last term is going to be 2 to the 6th. Okay? And I suppose if you were so inclined, you could try to clean up these coefficients. I don't know if we want to be that energetic, but let's give it a shot. X to the 6th, 12x to the 5th, plus 60 x to the 4 plus 160x cubed. Here's the tough one, right? 16 times 15. Well, let's see, we just double 4 times. So double once, 30, 60, 120, 240. Check my math on these. X squared. 6 times 32. That's going to be 192, I think. Again, check on that. Times x. Finally, 2 to the 6, 64. Okay, and you're done. All right. So, I mean, there's a bit of work involved. You gotta remember the formula. Maybe remember the triangle. A bit of arithmetic here, simplifying those coefficients. But compare that to if you had to do x plus 2 times 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 x plus, six factors of x plus 2, and you had to expand the whole thing out, you'd be at it for a very long time, right? There's a reason we like the binomial theorem. Okay, so we're working through some material on expanding and factoring this basic algebra, right, that you deal with when you're multiplying out products of binomials, things like this. We looked at binomial theorem. All of this falls under this general umbrella of polynomials, right? So a polynomial expression is something that basically consists of, well, there are two ingredients, right? Powers of some variable and coefficients, right? Plus addition. You're going to add, you're going to have more than one term, right? So polynomial with a single term is called a monomial with two terms. Binomial, we've encountered those, right? And then trinomial and so on, right? You can have as many terms as you want in a polynomial. And when we are talking polynomials, we need to specify that the powers we're looking at here are integer powers, positive integer powers, right? We're not looking at negative powers. We're not looking at fractional powers, okay? So things that are not polynomial include anything with, say, like a 1 over x, 1 over x squared, things like that, okay? These are examples of what are called rational functions. We'll talk about them later. Root functions, so like square root of t, right? Cube root of s. These are not polynomial functions. Also, any of your more complicated functions, like your trig functions, your exponential functions, your logarithms, certainly not polynomial, okay? So in a polynomial expression, we're just looking at positive integer powers of some variable with coefficients. And that means you're looking at things that look like this. So there might be some x to the n, and there might be some number out front. And so the way we tend to write this is we put a subscript, okay? Now, some people will get thrown off by that subscript because, we're used to writing superscripts for powers. They're like, what is that? What is that thing down there? What does that mean? Is that some kind of power, or is it like a secret power? What is it doing? It's not a power, it's just an index. It's just a way of keeping track of the coefficients, saying this is the coefficient corresponding to the power n, okay? The issue is I don't know how big this power is, right? I could use like a, b, c, d, e for my coefficients, but maybe I want to talk about a polynomial of degree 500. I'm going to run out of letters, but we never run out of numbers, so we can index the coefficients, right? So there'll be an, maybe an minus 1, x to the n minus 1, so on, down to an a2, x squared, a1 times x, and finally a sub 0, okay? So this is a polynomial expression. Now, later on we might want to talk about this as, say, a polynomial function. So we might give it a name. We might call this, say, p of x. Think of it as a function. But we're not yet at the point where we necessarily need to think in terms of functions. We just want to think of these as expressions with a variable because we want to talk about how to manipulate them, do things like factoring. And we want to introduce some terminology. So this a sub n, this is sometimes called the leading coefficient. Okay. A sub 0, this is called the constant term, right? It's the only one that doesn't have the variable in it. This number here, n, assuming that this leading coefficient is non-zero, this number n is called the degree of your polynomial. Okay? So those are some basic terms that you'll see associated with polynomials. So let's do a few examples. So we could write down something like 5x cubed minus 6x plus 8. This is an example of a degree 3 polynomial, right? Because the highest power of x that I see is 3, right? There is no x squared term, that's fine. You don't need to have every single power of x showing up in a polynomial. The terms that don't appear are just ones where the coefficient happens to be 0, which can happen, right? But notice that everything is just a power of x or a constant. There's no negative powers, there's no fractional powers, nothing like that, right? Let's do another one. Minus 4/3 x to the 7 plus 2√2 x to the 6th minus, I don't know, pi squared x to the 4 minus 2x plus 1. Okay, that's a polynomial. It's a polynomial whose degree is 7. Constant term is 1. Now, you'll notice that, well, there are some kind of, questionable looking things here, but these are coefficients, right? Root 2 is a real number, right? It's okay to have square root of a number, right? Pi, it's irrational, that's okay. You can have irrational coefficients. You just don't want to have square root of x. Square root of 2 is okay, square root of x is not, okay? So these are examples of polynomials, right? Again, something like, and sometimes there are ones that you want to treat as polynomials, but they're not quite. So let's say we do something like x squared minus 1 over x plus 1. Now it happens that the top is a so-called difference of squares, right? I can factor. And then you might say, hey, look, we've got the same factor, top and bottom, x plus 1. Let's cancel that thing, right? And so you cancel it out, and you say, that gets me to x minus 1. That's a polynomial, right? Well, not exactly, because a polynomial is defined for every possible real number value that you want to substitute for x, okay? If we're thinking of it as a function with the domain is all real numbers. Here there's a restriction. These are only equal if x is not equal to minus 1, okay? Because this over here technically is not defined at minus 1. If I plug in x equals minus 1, I get 0 divided by 0, which doesn't make any sense. Okay? So looks like a polynomial. It's not quite. Right? It's actually a rational function. Okay? So there's some basics on polynomials. We're going to pause here. We're going to come back. We're going to give you 2 fundamental results about polynomials, and then we're going to move on to some other topics. Okay, so in the last video we introduced some basic terminology about polynomials. In this video we're going to give you 2 fundamental theorems, basic facts about polynomial functions. So if I have a function, p of x, that is in this polynomial form, there are 2 things that I can tell you about such a function. The first is the factor theorem. The factor theorem says the following. It says that you take any number, so any real number, say a, and you plug it in to your polynomial. If you get 0, right? So this means you're doing, an times a to the n, an minus 1, you're plugging in this number. If p of a equals 0, then x minus a is a factor of p of x. Okay? So in other words, that means that you can write P of x as x minus a times some other polynomial q of x. So q would be a polynomial whose degree is one less than the polynomial you started with. In fact, this statement is what a mathematician might call an if and only if statement, right? If you have this factor, then certainly plugging in x equal to a gives you 0, because a minus a gives you 0, right? So if you have the factor, p of a will be 0. But the more useful direction is this one, that if you plug in the number and you get 0, well, then you know you have a factor, right? So you can get started on factoring, right? This is, if you're trying to factor a polynomial, this is a key result. But it still leaves you with one question. How do you know which numbers to plug in, right? There's lots of possibilities. There are some other kind of more advanced results that tell you something about where to look for possible numbers you could plug in. These numbers they give you 0, by the way, they have a name, right? So this a, if p of a gives you 0, you would say that a is a root of your polynomial. Okay, so rational roots means you're looking for roots that are rational numbers, numbers that can be expressed as fractions, right? Integer over integer. So there's some other results that kind of can narrow down your search somewhat, but the rational roots theorem tells you that if you're looking for, nice roots, so rational or even better integer roots for your polynomial, there are only certain possibilities, right? So the rational roots says that if a is a root of p of x with a equal to, let's say, maybe I shouldn't use p, m, say, actually m is not great either. I was running out of letters. U over v. So u and v here are integers. What can I say about these integers u and v? Well, it turns out that at least, I guess we should probably say that we're in lowest terms here because we could multiply and make u and v really big. If u and v are in lowest terms, let's specify that. Then you can say something. You can say that this a0, the constant term, is divisible by u, and an is divisible by v. It's one way to say it, okay? Maybe there's nicer ways of saying it, but this is one way of saying it, okay? So the way this works in practice is you're looking for rational roots. So what you do is you look for all the numbers that divide evenly into the constant term. You look for all the numbers that divide evenly into the leading term, the leading coefficient, and you use those to form fractions, okay? And only fractions of that form are possible roots for your polynomial. You don't have to consider any other possibilities. So let's try a quick example. And if I just kind of write down a polynomial at random, there's always a chance that it doesn't have any rational roots at all, okay? So let's go with this example. So let's say 3x plus, 4. Okay? So possible rational roots, what are they? Well, we know that 4 4 is divisible by plus or minus 1, plus or minus 2, plus or minus 4, right? 2 divisible by plus or minus 1, plus or minus 2. So that means that the possible roots, the ones that you would consider, are going to be, well, I could take plus or minus 1 divided by plus or minus 2. So I could have plus or minus 1/2. I could have plus or minus 1 over plus or minus 1, right? So plus 1, minus 1, those are possibilities. I could do plus or minus 2 over plus, so that would be plus or minus 2. If I do 2 over 2, that gives me 1, already got it. 4 over 2 gives me 2, already got it. So the other options would be plus or minus 4. So that's a total of 8 numbers to consider, right? Which is still a fair amount of work, but it's better than, just randomly guessing, right? At least you've narrowed it down to 8 possibilities. So how do you figure out if any of those actually work? Well, now you come back to the factor theorem. You take each of those numbers, you plug them into the polynomial. So for example, if I wanted to try 1, I'd come in, I'd say, okay, so 2 times 1, right? So I could do p of 1. P of 1 would be 2 minus 1 plus 3 plus 4. And I'd say, okay, so that works out to 8. Definitely not 0, okay? So 1's not going to work. Then I might try p of minus 1, see where that gets me, right? And then I might try p of 2, p of minus 2, p of 1/2, p of minus 1/2. See if any of them work. If none of them work, then there aren't any rational roots, and that means that, well, if I was asking you to factor this polynomial, I have not given you a fair problem, right? It doesn't mean there isn't a root. It just means that that root is irrational, and that means you're not going to be able to find it by elementary methods. Using factoring, anything like that, you're not going to be able to find it, right? It's going to be some ugly, irrational thing involving cube roots and square roots, and probably the way you would find that is using some numerical techniques that you learn later on in calculus, something like Newton's method for kind of approximating the value of the root, right? It would not be fair to ask you to find the exact value for an irrational root. Yes, there is a formula for finding roots of cubes, just like the quadratic formula, but nobody remembers it, nobody uses it. You'd try these possibilities. If none of them worked, you'd move on to something else. All right, so the next few videos, we're going to look at techniques for factoring, okay? So the ability to factor is fairly important in calculus. There are going to be a number of situations where you need to figure out where a function or its derivative or its second derivative is equal to 0, right? Those points where a derivative is equal to 0 are very important. They have a name. They're called critical points. They come up quite frequently in a lot of optimization and applied problems involving calculus. So you need to be able to figure out where functions are equal to 0. If they're polynomial or rational functions, that's going to involve a certain amount of factoring. So basic step is you're looking at quadratics, okay? So you're looking at something that looks like ax squared plus bx plus c, and you want to factor this thing, right? And we know from the factor theorem, if we find those factors, that's the same thing as finding zeros, right? So in some sense, we're trying to figure out where this thing is equal to 0. Of course, the quadratic formula gives us one answer, right? So the quadratic formula says, oh yeah, we know exactly when this thing's going to be equal to 0. It's going to happen when x is equal to plus or minus, sorry. It's the trouble with quadratic formula. Sometimes you forget it. Minus b plus or minus square root b squared minus 4ac over 2a, right? So some people just say, oh yeah, remember the quadratic formula. It'll give you the answer. It's not a nice formula, right? It's not great. But it is a fail-safe. It's going to work in situations where you can't figure out the factors, probably because, well, there's a couple of possibilities. Quadratic might be irreducible, right? It might not have any roots. It might not have factors. It might be that that's as simplified as you can make it. It might be that there are factors, but they're irrational, and you're probably not going to be able to find those just by staring at it. In those cases, the quadratic formula can bail you out, right? So for example, like if I were to just kind of write down some quadratic equation without thinking too hard about it, and say, okay, I want to solve that. Probably don't come up with factors right away, yeah? Right? Maybe there aren't any nice factors. So if we needed to, we can fall back on the quadratic formula. We can say, oh yeah, so the roots are going to be, if they exist, minus b, so minus b is minus 5, plus or minus square root minus 5 squared minus 4 times 2 times 4 over 2 times 2. All right. And actually this gives you the answer right away, because the first thing you do before you bother with any other simplifying is you look under that square root and you say, okay, what do I have under that square root? Under that square root, 5 squared is 25. Subtract. 4 times 4 is 16 times 2 is 32. 25 minus 32 is less than 0. Okay? So I've got a negative number under the square root. That tells me there are no real number solutions. Right? You can't take the square root of a negative number. So quadratic formula tells you there are no solutions to this equation, so there won't be any factors. Right? Factor theorem tells you that. If there's no solutions, there's no factors. Okay. So that's one case where you might need the quadratic formula. Another one might be, well, let's say that this plus 4 was actually a minus 4, right? Minus 4. Well, now you're doing 25 plus 32. So now you'd say, okay, so I've got 5 plus or minus the square root of 25 plus 32 over 4. And this is a case where, yeah, there's not a lot of simplifying you're going to be able to do. So your answers are that x is equal to 5 plus the square root of 57 over 4 and 5 minus the square root of 57 over 4. And so if we think of those as our values of a in the factor theorem, that tells me that I could write 2x squared minus 5x minus 4. If I bring the 2 out front, I could write that as 2 times x minus 5 plus root 57 over 4, x minus 5 minus root 57 over 4, and okay, I factored my polynomial. That's not where we want to go, right? Nobody likes doing this, right? Occasionally you got to do it. You got to use quadratic formula because there are solutions, but they're gross. That's probably not where you want to go. You're hoping that you've got rational or even better integer roots for your polynomial. So how do you work backwards? So let's say somebody gives you a polynomial like x squared minus 5x plus 6, and they say, okay, I want you to factor this thing. Okay. Well, one of the things we could do is we could fall back on rational roots theorem. Rational roots theorem says that, possible factors, I could have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So I could have x plus or minus any of those numbers. and you can just try them and see if they work, right? You could use the factor theorem, plug each of those numbers in, see if you get 0, trial and error. But another way to do it is to say, well, let's suppose that this, let's say I could factor it. So let's say I can factor this as x plus a times x plus b, right? Or maybe you want to do x minus a, x minus b. Okay, so, well then I can say, well, what do I get if I multiply that out? So x times x, x squared, x times a, x times b. So I have a x plus bx, I can write it like that, and then a times b, right? So if you compare the two, well, then you realize that there's two things that have to happen. I need a times b to equal 6. I need a plus b to equal minus 5. So now you got to come up with two numbers that multiply to give you 6, and they add to give you minus 5, all right? So possibilities are going to be either 1 times 6 or 2 times 3. And, well, or minus 2 times minus 3, minus 1 times minus 6, right? And of those possibilities, the only one that adds up to give you minus 5 would be a is minus 2, b is minus 3, right? Or I guess this could be minus 3, that could be minus 2, that doesn't matter. So then we can say, oh yeah, so that means that I've got x squared minus 5x plus 6, and that's going to be equal to x minus 2 times x minus 3, right? That's your sort of typical factoring scenario that you might be dealing with. The only thing that might be a little bit more complicated is if you've got a coefficient in front of the x squared. We're running a little long on time for this one, so let's try to do this one quickly. So let's say I have something like 2x squared plus 3x plus 1, and I want to factor that, okay? Okay, so let's give this one a try. What are we going to do? Well, one of the things that you might try is first factor out that coefficient, right? Reduce it to a problem like the one that we just solved. The only catch is now there are some fractions in there. 3/2 plus 1/2, right? Which makes things maybe a little bit trickier. But we already know from the rational roots theorem that the only factors we'll be looking for could be plus or minus 1 or plus or minus 1/2, right? So we kind of have things narrowed down a little bit. So we think about, okay, we want to multiply to give 1/2, add to give 3/2. 1 times 1/2 gives me 1/2. 1 plus 1/2 gives me 3/2, right? So you do that kind of, again, you're thinking about solving these equations. And so we say, okay, so x, so 1 times 1/2, right? So we can factor like that. If you don't like that 1/2 in there, you could always take this 2. If you want to, you could take this 2 and you could put it back with that second factor, and you could write it as x plus 1 times 2x plus 1, if you don't like having the 1/2. The nice thing about having it this way, though, is now you know what the zeros are. Minus 1 and minus 1/2. Those are your roots. So in our last video, we looked at factoring quadratics, right? And of course, among all the various factoring formulas that you know, quadratic formula made an appearance, right? This is probably our most famous formula for factoring. But there are a few other formulas that pop up from time to time, okay? One of the ones that comes up more often than you might think is the difference of squares formula. So the difference of squares formula says that if you have x squared minus a squared, you can factor that as x minus a times x plus a. Okay, that's your difference of squares. Let me clean up that a little bit. There we go. Okay, so difference of squares comes up fairly often, sometimes just simply in factoring, right? So for example, somebody gives you x squared minus 4, and you say, oh yeah, I know what that is. It's x minus 2 times x plus 2, right? Or maybe they give you something like x squared minus 3, and you're like, well, hang on a sec, 3 is not a square. Well, true, it's not a perfect square, but it's the square of something, right? We're working over the real numbers. We can have irrational values, right? 3 is the square of something. It's the square of root 3. So we can factor that as x minus root 3 times x plus root 3, right? So we can do difference of squares. One of the other places where you might run into this is actually using it sort of in reverse to get rid of something like, say, a x minus root 3 or a root x. So you might do it in something like, say you have the following. Let's say you have x minus, let's say 4 over root x minus 2. And you don't like having that root x in the bottom. You want to get rid of it, right? So how do you get rid of that root x? Well, one of the things you can do is say, hey, you know, I just saw this example here. Sure, the root was on the 3 here rather than on the x, but I have this difference of squares thing going on. So if I multiply by the same thing, but the opposite sign, I'm going to square both of the terms, right? So if I take this and I multiply by root x plus 2, that's gonna get rid of the square root. Of course, I can't do it on the bottom without also doing it on the top. Okay, let's put extra parentheses in there just to make sure we don't mess it up. And what do we get? We get x minus 4 root x plus 2. And on the bottom, root x times root x becomes simply x, right? And you'll notice that the whole point here is the cross terms cancel. 2 times root x minus 2 times root x, add those up, you get 0. They disappear. Minus 2 times 2, x minus 4, right? Probably at this point you're gonna cancel those and simplify down to root x plus 2. Okay, good. So we have that. One note of caution. A sum of squares is always irreducible. So x squared plus a squared, there's nothing you can do. You can't factor. This is irreducible. Common mistake that a lot of students will make, again, one of these ones that's sort of born of wishful thinking, is they really want to be able to sort of factor things so they can cancel and simplify, and there's going to be a sum of squares in there somewhere, right? X squared plus something positive. You can't do anything about it. Okay, you just got to leave it alone. There's nothing you can do to simplify, right? Because if this is a positive number, you're adding a square. We know that squares are never negative, right? So this can never be 0. And if it can't be 0, it can't have a factor. Okay? Now, what about difference of cubes? Turns out you can do a difference of cubes, and you can also do sum of cubes. Okay, so unlike sum of squares, right? You can't factor sum of squares. You can factor a sum of cubes, right? The reason is that you can take this cube root of a negative number, right? If I set this equal to 0, tried to solve, I'd have a negative on the other side. I can't take the square root. I can take the cube root of a negative though. So difference of cubes looks like the following. X cubed minus a cubed is x minus a. We know that's a factor because if I put in x equal to a, I get 0. All right? And the other term, you square the first term, then you multiply with the opposite sign, a times x, and then you square the last term, a squared. Okay? For sum of cubes, same thing with the sign change. This will be x plus a. Right now, minus a is your root. And this becomes minus ax, right? So you just interchange these two signs between sum of cubes and difference of cubes. One important thing to point out is that these quadratic factors that you get from a difference or sum of cubes, these are also always irreducible. Okay? So if you're doing a factoring problem, once you've applied a difference of cubes or sum of cubes formula, you're done. Okay? There's no further factoring that you can do. You stop there. Okay? So as a quick example, somebody gives you something like 27 y cubed minus 1 over 8. We say, what do I know about those coefficients? 27 is 3 cubed. 1 over 8 is a half cubed. Okay? So this is a difference of cubes. So it's going to be, so this is 3y and then I cube it. So it's 3y minus a half. Now I square the first term, 9y squared, opposite sign in the product. So it's going to be plus 3 over 2y, and then plus a half squared, so plus 1/4. Okay, and you factored. All right, in this video, we're going to quickly point out another strategy that sometimes works for factoring, in this case for cubics. This is probably something you're most likely to apply in the case of a cubic polynomial. So what you do here when you're factoring by grouping is you pair the first two and the last two terms. You kind of set those aside. And in the first two terms, there's a u that's common to both. In fact, there's a u squared that's common to both. And so what you do is you factor that out. So you say, okay, in those first two terms, if I factor out a u squared, okay. In fact, I even factor out a 2u squared, right? There's a 2 that's common to both. So I factored a 2u squared, and I'm left with, well, here, to get 2u cubed, I have to take 2u squared and multiply by u, right? And here, for 4u squared, well, I've got 2u squared, I have to multiply by minus 2 to get minus 4u squared. Okay? So you factor that out. Then you come to the last two and you say, okay, what can I factor out from the last two terms? Well, there's a 3 that's common to both. So I factor out the 3. Okay? And in this case, I get kind of lucky because you'll notice that once I've done that, I have the same factor here and here. So think now about reversing sort of distributive property, if you like. I can pull that out as a common factor. So I factor out the u minus 2. Okay? And then I'm left with 2u squared plus 3. Okay? And that's as far as I go. I can't factor any further, right? This is a sum of squares, right? 3 is the square of root 3. And as we pointed out, a sum of squares is irreducible. So you can't factor this any further. You stop there. If you're looking for roots, there's exactly 1. When u is equal to 2, the polynomial is 0. Okay? So that's factoring by grouping. It's something you can always consider, but it doesn't always work. Okay? We'll do a couple of examples in later videos where this fails, and we have to look at other techniques. I'll mention one more option before we move on to sort of some more general methods. You might run into what you might call a quadratic in disguise. And these typically show up in degree 4 polynomials, sometimes higher, where you might have something like the following. You might have, say, x to the 4, okay, plus 3x squared plus 2. Okay, so that's a degree 4 polynomial. In general, degree 4 polynomials are quite difficult to factor. They take a lot of work. But one of the things that you might notice is that there are no odd powers in here. There's only even powers, right? And in fact, x to the 4 is really, we could write that as x squared squared, right? And then 3x squared plus 2. So if we wanted to, we could think of this as like y squared plus 3y plus 2, where y equals x squared. And we know how to factor this. This is going to be y plus 1 times y plus 2. But we should end in the variable we started with, x squared plus 1 times x squared plus 2, right? And because those are both sums of squares, you can't factor any further. Both of those are irreducible quadratics, right? If we had gone with, say, a minus sign here, we'd have minus signs there, and then we could factor each of those as a difference of squares, but that's not the example that we had. So finally, with this issue of trying to factor polynomials, we'll come to long division. So this is the most difficult of the various factoring techniques, or at least the most time-consuming. It's also the most reliable. This is, if there's a method that's going to work every time, it's going to be long division. It's always going to do the job, right? So here's a cubic polynomial that we might want to try to factor. You might say, hey, grouping is pretty easy. Let's see what we can get away with if we do grouping, right? But you'll notice right away that grouping is going to fail in this case. If I take out an x squared, I'm left with an x plus 8. Over here, best I can do is a 3, right? I could factor out a 3, and I'd be left with 7x plus 9. It's not going to work, right? So grouping is not an option. So we're like, okay, that's out. What else are we going to try? Well, we can go to rational roots theorem, right? What are the possible factors here? We could try, so possible integer roots. Well, the possible integer roots are going to be the numbers that divide evenly into 18. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9. All right, our last topic related to polynomials is solving inequalities involving polynomials. This, again, is something that you're going to have to do fairly frequently once you get into calculus when you're trying to figure out things like where is a derivative positive, where is a derivative negative. This is going to be key to solving a lot of optimization problems, curve sketching problems, things like that. So it's something that's going to come up fairly frequently. We'll start simple, we'll work our way up. The first one is linear, right? So linear inequalities you learn going back to high school. I'm not sure what grade you see them in, but certainly this is a basic thing that you would have seen in school. And linear inequalities are fairly straightforward. So here you can rely on the fact that, well, you can always add something to both sides of an inequality, right? So we can add minus 4, and we get, so 4 minus 4, of course, is 0. 3 minus 4, I get negative 1. So 2x bigger than negative 1 is equivalent, right? I can divide by 2. And because 2 is positive, I don't change the inequality, and I'm done. I've solved. X has to be bigger than minus 1/2, right? So I might also want to give an interval of solution. So we can write it as minus 1/2 to infinity, okay? So we've solved that inequality. Now, where people get themselves into trouble is you move from linear to things like quadratic, and you want to apply similar techniques, right? And one of the things you might do, so here notice you've got x's on both sides. And you might have this tendency to say, oh, let's move the x over, let's isolate the x's, right? It doesn't get you anywhere. Once you go past linear to quadratic, cubic, anything else other than linear, there's really only one thing that works, which is going to be to basically isolate for 0. So you got to bring everything to one side, okay? So if I bring the 5x over and the minus 6 over, this is the same thing as saying x squared minus 5x plus 6 is bigger than 0, okay? So this is useful because now this boils down to deciding where is the polynomial positive and where is the polynomial negative. And we know how to solve that problem because we know that the only possible places where a polynomial can change from positive to negative are at the roots, right? So once we find the roots, we know where the possible sign changes are, and then we just have to determine signs on either side of the root. In this case, I mean, we kind of know, right, what things look like here. We can graph this. It's a quadratic. Okay, it's a quadratic opening up. It's going to have a couple of roots, right? It's going to look something like this, right? There are going to be 2 roots. So we know it's going to be positive on the outside, negative in between, right? We know that just by looking at the leading coefficient, right? So either this is positive everywhere, okay, or it has an intercept, 1 or 2 intercepts, in which case it's going to be positive outside the intercepts, negative between. We know that because the leading term has positive coefficients, so we know that this is a quadratic that's opening upwards. So how do we find those roots? Well, we factor. We've done this one before. In fact, we know this factors as x minus 2 times x minus 3, right? So solving the original inequality amounts to figuring out where is x minus 2 times x minus 3, where is that bigger than 0? So what you might do now is you might write down what we call a sign diagram. So in a sign diagram, you just draw yourself a little number line. On that number line, you mark off the roots. So there are only 2 roots, 2, 3. And then you put down the signs between each root. So we know, as we said, they're going to be positive outside the roots, negative in between, right? The other way to realize that is you can always choose some test value like x equals 4, right? If I plug in 4, I get 2 times 1 is positive, so I know it's positive out here. I know that when I cross 3, this x minus 3 factor, right, it's positive here, but it's negative here. So this is going to change sign. This one hasn't yet, so now I have 1 minus sign, right? And then once I cross 2, this one becomes negative as well. Now I have 2 negatives, gives me that positive. There are a few ways to work that out. You could always do test values in each interval if you're not sure. There's our sign diagram. And we want to know where is this thing positive, so we just look for plus signs, right? Plus sign for positive. So we know that our solution is going to be that x belongs to either everything from minus infinity up to 2 or from 3 to infinity. Okay? All right. One last one, cubic inequality, right? So maybe there's a bit more work involved here, but the initial strategy, still the same. Bring everything over, x cubed plus 2x squared minus x minus 2. We want that to be bigger than 0, right? Okay, so let's see if we can factor. Maybe we check to see, can we actually group, right? Because if we can factor by grouping, that saves us from having to do long division. That's always nice. Take out the x squared, leaves me with x plus 2. Here, if I take out a minus sign, I'm in luck, x plus 2. That minus sign, of course, is just minus 1. Okay, factor one more time. X squared minus 1 times x plus 2. We want that to be bigger than 0. And that's a difference of squares. X minus 1, x plus 1. Okay, so we need x minus 1 times x plus 1 times x plus 2. We want that to be bigger than 0. So we draw our number line. We mark off the 3 roots. So there are roots at minus 2, minus 1, plus 1. And now we have to work out the sign in each interval. So if we choose something bigger than 1, 2 for example, we can quickly see that all 3 factors are positive. So the whole thing is positive. If we choose something between minus 1 and 1, this first factor is going to become negative. The other 2 remain positive. 1 minus sign means the whole thing is negative. Between minus 2 and minus 1, now this factor and this factor, they're both negative. But that one's positive. 2 negatives gives me a positive. And then finally, once we're less than minus 2, all 3 factors are negative. 3 minus signs gives me an overall negative. And that means that if I want this thing to be positive, I look for the intervals with the plus signs. I want x to be between minus 2 and minus 1, or from 1 to infinity, right? Of course, if this had been bigger than or equal to, we could have done that. The only difference is now we include the zeros, and so the round brackets would become square brackets, except on the infinity, right? We never include infinity. Okay, in the next few videos, we're going to look at rational expressions, or more generally, well, rational functions, right? So we've gone over polynomials, so we have a good idea of what a polynomial looks like. A rational expression is just a ratio of 2 polynomials, okay? So we're looking at a ratio of polynomials. So something that looks like, say, p of x over q of x. Okay? So, for example, we might have something like x cubed plus x squared, okay, over 4x squared minus 8x. Okay, that's a rational expression. Okay, if I were to assign a function to this, so it'd have a rational function. If I said f of x equals, okay, then it's a function. So it's a ratio of 2 polynomials, right? So maybe we do want to think of this as a function. The first thing we might ask for such a function is, what's the domain, right? Here's a function. What's the domain of our function, right? Now, we have this convention in calculus that if the domain is not specified, and it usually isn't, then the domain of our function is just going to be the largest set of real numbers for which our function is defined. So for a rational expression, rational function, when is it defined? Well, it's defined for all x for which q of x is non-zero, right? That's the only real restriction here. We can't divide by 0. Otherwise, we know that polynomials are defined everywhere, right? They always give us a real number output, and a ratio of two real numbers is always defined as long as the one on the bottom is not 0. Okay? So we can do this. So if we want to know where this thing is defined, we got to factor it. Okay? And so up top, we notice, hey, there's actually x squared is common to both. I can take out x squared. Please move to x plus 1. On the bottom, there's a 4 that's common and x. 4x times x minus 2. Okay? There's our fully factored version of this rational function. Now, from here we want to say, well, where is it defined, right? Yes, there's an x that can be canceled, and we're going to cancel it. But we really only want to cancel if it's non-zero, right? So if x is 0, this is undefined. This expression is undefined if x is 0, because I get 0 over 0. So I don't want x to be 0. The other place where I don't want is I don't want x to be equal to 2. Because if x is equal to 2, then x minus 2 is 0. Okay? So I have those two zeros in the denominator. I want to avoid both of those. Now, as long as I stay away from those two, then yes, I can simplify. I can cancel this x with one of the two upstairs. Okay? And I'm going to get x times x plus 1 over 4 times x minus 2. All right. There we go. So now I've simplified, right? One of the things you want to be very careful with when you're simplifying rational expressions is that you can only simplify once you've factored. Don't try to cancel things if you haven't factored top and bottom, right? It would not be valid for me to cancel an x squared here with an x squared down here. That doesn't work. I can only cancel once I've fully factored. Fully factored, I can look to cancel, but again, I should keep track of the fact that I canceled that x because that does affect the domain for my function. Okay? So you should keep track of that domain, and you've simplified. We're going to pause here. We're going to come back. We're going to look at some other information that we can get out of this thing once we've got it down to here. Okay, so this is, at least for now, our last video on rational expressions and functions. Here we're going to look at rational inequalities. Right? We looked at solving polynomial inequalities earlier. And your first temptation when you see a rational inequality is to turn it into a polynomial inequality by just clearing denominators. You say, hey, let's just multiply everything by x plus 2. Then it's polynomial, and I solve. There's just one problem with doing that, right? We know from some of the examples we've looked at that we might have a sign change at x plus 2, right? When x is equal to minus 2, there's a sign change. We know that. And so that means that if we wanted to clear the denominator, we'd have to do two separate cases. When x is less than minus 2 and when x is bigger than minus 2. Because when x is less than minus 2, you'd be multiplying everything by a negative number, and we know that if you multiply by a negative, that reverses the inequality. Okay, so how do you proceed if you can't just cross-multiply, get rid of the denominators, turn it into a polynomial inequality? Well, first step is the same as it was when we were doing polynomial inequalities, which is you get everything on one side. So we say, okay, so this is the same thing as saying x plus 6 over x plus 2 minus 3 less than or equal to 0. Okay? Now we're dealing with the problem of figuring out where is a function less than or equal to 0. Right? And that's something that we know how to solve. But the first thing we got to do is we've got to rewrite this function, right? Because we want to get it in the form of a rational expression. We want it in that form, polynomial over polynomial. And so we're adding up these terms. One of them has a denominator, so we know what we need. We need a common denominator. So these two terms that are missing that denominator, we put it in. X times x plus 2 over x plus 2 plus 6 over x plus 2. All right, so we're going to do several review videos now on functions. So functions are something that everyone sees in high school, and you spend a lot of time on them. And still it remains one of those areas where even at the end of a calculus course, it can be clear that a lot of people still don't quite understand what a function is, how a function works, how do you manipulate functions, how do you work with function notation, these sorts of things. It's something that can be a bit of a challenge for people. So let's just start with some basic examples. So functions you might have seen, right? The ones that are familiar from high school. So you probably saw things written, you know, like this, say f of x equals, say, 3x minus 2, for example, okay? Or g of x equals, well, let's say x squared minus 4x plus 3, something like that, right? So these are your the sorts of functions that you've probably encountered a number of times. You've seen this notation, f of x. In subsequent videos, we're going to expand on this notation. We're going to explain the meaning a little bit. For now, we'll just use it, hoping that it's somewhat familiar to most of you as you're watching these. And you're probably used to using x as the variable in your function, but there's no reason why you necessarily have to use x, right? You might have something like maybe velocity as a function of time, something like that, right? So you might have something like, you know, minus 9.8 times t plus, I don't know, some initial speed, something like that. So these are all examples of functions that you've encountered, right? And some of these functions, they have names, right? So special types of functions, they have names to describe them, right? This one here is an example of a linear function. This is an example of a quadratic function. And of course, both of them are special cases of the more general idea of a polynomial function. But you can go well beyond polynomials. We can look at things like, you know, let's say we do something like f of theta equals sine 2 theta, right? Some sort of trig function. We might do something like that. Exponential functions, logarithms. We'll look at all of these as we proceed through the videos. And of course, the name linear here, why do we call this a linear function? Well, it's a linear function because if you were to graph it, if you were to set y equal to f of x, so y equals 3x minus 2, then of course we know that this here is just a straight line, hence linear, right? You see the word line in linear right there. Okay, so we'll talk about graphs, we'll talk about different types of functions, we'll go over the function notation, we're going to look at all these different elements of understanding functions and working with functions over the next several videos. Okay, so I've put a definition for what it means for something to be a function up here on the board. This is, let's say, an informal definition of what it means to be a function, but it works for our purposes. In other courses, you might see more careful, more precise definitions of functions, perhaps in a course on discrete math, or a course on introduction to proofs or something like this. You might see something more careful, more precise. But the main ingredients in what it means to be a function, and here our function is f, okay? The main ingredients are, well, you need to have some sets, okay? So A, B, these are sets. What does a function do? A function takes every element, and we should probably underline the word each here. A function has to go through every single element in the set A, okay? And it has to assign it to some element in the set B. And one of the rules for what it means for a function to be a function is that any particular element of the set A can only be sent to one particular element in B. So if you have a function where, let's say 4 is an element of your set, you can't decide that you want to assign the number 4 to 3 different things. You can only assign it to one particular value. Okay? This is the defining property of a function. If you relax this rule, if you allow for something in the set A to be associated with more than one element in the set B, you no longer have a function. You have a more general object called a relation. And relations, again, are interesting mathematical objects and something that you might study, but it's unlikely that you will see that in your calculus course. Relations, again, are something you might see in a proofs course, a discrete math course, probably not in your calculus course. Now, there are a few other things that we can add. One of the ways that you might denote the fact that this function goes from a set A to a set B, you might write this by saying, we'll write F for the letter that represents your function, and a colon, and then A, arrow, B. So you'd read that as, F goes from A to B, or F is a function from A to B. So there's this sort of dynamic point of view when you have a function that there's inputs that are being transformed into outputs, right? So in these basic examples that we had here, right, the x that you see here, that's your input, right? That comes from some set A, and over here is your output, right? So this whole thing here, that's going to be your output. Now, in these examples here, these ones which are coming from sort of, high school pre-calculus, if you like, chances are your input and your output are both real numbers. In calculus, inputs, outputs, they're always going to be real numbers, right? And for functions like these, any real number will do, right? This expression makes sense for any number. X can be any number, right? Doesn't matter what that number is, it always makes sense to multiply it by 3. Whatever that output happens to be, it always makes sense to subtract 2, right? Any number can go, right? The rule in this case is this instruction, right? A lot of people think of the formula as the rule, right? But really the formula there is the output. The rule is this instruction saying that whatever the input was, you should multiply by 3 and then subtract 2, right? But we don't want to have to actually say that every time. This is why we develop mathematical notation. It's a lot simpler to just write down the formula than it is to express that rule in words. Okay, a few other bits of terminology before we move on. The set A, so the set from which the inputs come, this is known as the domain for your function. The set B is known as the codomain. Okay. Another way that you might represent this function process is you might have a little diagram that's something like this. Here's my A, here's my B, and again we draw an arrow to represent the fact that things are coming from A and going to B, and if we want to say that F is the rule that's doing that, we can write something like that. So this is another notation that you might see. Unfortunately, in calculus, we tend to kind of gloss over some of this. We don't necessarily use this notation. We usually don't specify the sets A and B because those sets are always going to be subsets of the real numbers. And so in calculus, we get into this habit of letting the formula define the function, right? But the formula is really only part of the definition. The domain, the codomain, those are parts of the definition. This is something that will come up later when we talk about inverse functions, right? When we talk about inverses, we need functions to be one-to-one. Something like this function here, it's not one-to-one, not everywhere. But if I shrunk the domain, if if I went with a smaller domain, if I didn't use all real numbers, I could shrink this down to something that is a one-to-one function, right? We know that the graph of this is a parabola. If you just took half the parabola, you'd have a one-to-one function. So there are concerns like that that do come up from time to time in calculus, but most of the time we're a little bit lazy about this. And again, we'll talk in another video about how we make sense of domain in the context of calculus, where we never explicitly write down these sets A and B. All right, we're going to look at a few simple examples of functions in this video, just to kind of expand on this definition, get a little bit better feel for what this definition is saying. What does it mean for something to be a function? So here's an example, and here's one where we're just going to explicitly construct a function. So we're going to say A is going to be the set containing the letters 1, 2, 3. B is going to be the set containing letters, let's say A and B. And I'm just going to define my function like this. And there's a few ways that we could do this. So one of the ways we could do it is we could just visually represent this by saying, okay, here's A, here's B. Okay, so we just kind of draw those two sets. And we're going to mark off 1, 2, 3. We're going to mark off A, B, and we're going to specify the function by just saying, you know, what goes where, right? So we could do something like this. We could send 1 to A, okay? We could do that. I could send 2. Maybe 2 goes to B. Okay, we could do something like that. Now, if I stop here, I haven't actually defined a function, because one of the conditions for a function is that every element of the domain has to be assigned. So until I send this 3 somewhere, I don't have a function. So maybe we send 3, maybe we send that to A as well. Okay, so we have a function, right? Now, you might be concerned that there are 2 different elements of the domain that both get sent to A. This is okay. All right, you're allowed to have this in a function. What you can't have is if I had 2 different arrows coming out. So if 1 went to both A and B, I would not have a function. So for any element in the domain, you can only have 1 outgoing arrow. But in the codomain, you can have more than 1 incoming arrow, right? So it's okay that I have 2 arrows going into A. It would only be a problem if I had 2 arrows coming out from one of these elements. Okay? So this has a function, right? This defines a function. This property, if you are concerned about this is where this notion of a function being one-to-one comes in, and we might talk about that later on, right? Now, another notation you're probably familiar with is that if you have an element A assigned to an element B, then usually what you do is you would write this, you would express this by saying that B is equal to f of A, right? So over here in this context, one of the ways I could define my function, I can completely define my function by just, again, saying what happens to every input, right? Once every possible input has been assigned to an output, my function is defined. So I could say f of 1 equals A, f of 2 equals B, f of 3 equals A. So if I simply gave you that information, that again would be enough to define a function. Okay, this is fine. All right. Now, of course, a lot of the time we're dealing with examples like the ones that we had up here a second ago, where A is going to be the set of all real numbers. Maybe B is, well, it could, let's say B is going to be the numbers from 0 to infinity. Could be all real numbers. And let's say I define f from a to b is going to be defined with the following formula. We say simply f of x equals x squared, right? So this notation, right, is being used here. So what it's saying is that x in this case, this x, right, this is my input. It's what I called a over there, right? So this is an element of R, of a, right? This x squared, that's my output. So that's an element of b, right? We know that if you square a real number, the result is never negative. So this is indeed an element of that set b, right? Okay, so again, that's another example of a function. But you know, there are many more examples. We could go with something like the following. We could say, so we might write down, so here's something you might see in like a third or fourth course in calculus. You might see something like f of xy equals x squared plus y squared, right? So you have, it looks like you have two inputs, right? There's an x and a y. This is, in calculus, we usually refer to this as a function of several variables. But we can always think of the input here as the ordered pair, which is an element of the plane of R2, right? And the output would be this number, x squared plus y squared, which is an element of R, right? Of course, it's also an element, you know, again, this is never negative, so we could go with 0 to infinity if you want. There's no requirement, though, that your function hits every element of the codomain, right? So you can always you can talk about this distinction between range versus codomain, right? The range is the set of all outputs that your function has, right? So here we might say, well, so the codomain is R, but the range is the set of real numbers from 0 to infinity. You can make this distinction between range and codomain. When the range equals the codomain, there's a word for that. You can talk about a function being onto. Onto functions are usually not discussed in calculus. The only place where you might have to think about it a little bit is when you talk about inverse functions, and even there you can usually kind of gloss around. Generally what you do is you just kind of assume that the codomain is the same as the range. This is something you can usually get away with in calculus. Okay, so there's a few simple examples of functions. We'll look at some more calculus-focused ones in later videos. But you know, just to press home this fact that, or this idea that, you know, this definition of function, it's very broad. You can look at all kinds of different scenarios. You could look at something where maybe you take A and B to be something like, I don't know, the set of all, let's say, female humans, and the relationship is mother to daughter. And you could ask, is that a function? Well, that's not necessarily going to be a function because there are some mothers who have more than one daughter, right? So you might have two, well, I don't know, it seems crude to call this an output now, but two outputs for a given input. On the other hand, any given daughter has only one biological mother. I guess, well, you know, I don't know, these days. So you could go in the other way and say that is indeed a function, going in the other direction. So there's lots of different scenarios like that you could consider, but we'll typically be looking at, you know, objects like this most of the time when we talk about functions. All right, continue with our discussion of functions. We'll say a little bit more about notation. Okay? So a lot of people, I think, will get tripped up a little bit on the notation, sometimes get mixed up on necessarily what are you actually meaning when you write down something. So let's say you write down something like f of x equals 3x squared minus 2x plus 1, right? You write that down. What does that actually mean? What are you telling me when you write down an expression like this? Well, again, you haven't quite necessarily told me everything there is to tell me about this function, because you haven't said anything about domain or codomain. You've just written down a formula, right? But this x that's in brackets here, right? This is your variable, right? So this is your input, or we might think of this as a variable. If you've done any, let's say, computer programming or something like this, you might have encountered this sort of scenario, right? Where you have various functions that are defined in your program, and they take some input, right? And probably you even put that input in parentheses like this. And you run the function, right? You run the program, and something happens to it. So that's exactly what you're doing here, right? You're thinking of, well, you're going to take a program, you're going to feed it some input, it's going to do something to that input, it's going to give you an output. That's what's going on when you're working with the function, okay? So if we wanted to be more precise, we could say something like, we could say, well, f, it's a function from, well, in this case, maybe we want to say that it's defined for any real number, right? It goes from R to R, right? And if we want to talk about this relationship between inputs and outputs, we could say something, like, we could say that A, we might write something like this, A goes to B. We might say B is equal to f of A. We might even write down our formula and say, well, what is f of A? Well, f of A is, and again, the fact that I'm using a different letter doesn't matter. It's 3a squared minus 2a plus 1, right? There's nothing special about x. You can use whatever letter you feel like using, right? You want to use A, use A. You want to use x, use x. Just make sure it's clear from the context what you're talking about. And of course, just like in a computer program, you can take that variable, you can substitute it for a value, see what happens. So we might say something like, well, what do I get if I do f of 2? Okay. Well, f of 2, we're just going to replace, right? You look at the formula, you say, okay, well, on this side, right, in this expression, I've taken a, I've replaced it by 2. So what I do is I look for everywhere I see an a, and I replace it by 2. 3 times 2 squared minus 2 times 2 plus 1. And if you're so inclined, you can do that calculation, get an answer. In this case, it happens to be 9. Right? And it doesn't matter what number you choose. Let's say I want to do f of minus 1. I can do that as well, right? 3 times minus 1 squared, subtract 2 times minus 1 plus 1. Okay. Notice I'm using parentheses around my input into the function. This is good practice, especially once you get into negatives, because you don't want to miss something like the square of a negative, right? You don't want to make sign errors because you're being careless. So minus 1, if I square that, I get plus 1. So this is positive 3, right? Minus 2 times minus 1, again, right? Double negative becomes positive. So 3 plus 2 plus 1. I get an outcome of 6. Okay, that's all well and good. What if I asked you for something like f of y? All right, this really throws people off, right? Because we're so used to writing y as equal to f of x when you talk about graphs, right? When you want to graph a function, and we'll talk about graphs in some later videos, you set y equal to f of x, where x and y are the coordinates in your Cartesian plane, and you plot your function. But here, y is just some other variable name. So what's f of y? F of y, I haven't told you anything about y. So all I can really tell you right now is that f of y is 3y squared minus 2y plus 1, right? That's all you can do. And that's the correct answer. If I now went ahead and told you something about y, if I said, oh, by the way, y is equal to f of x, or y is equal to x plus 3, or something like that, right? If I told you that y had some particular value, well then, and again, this is the whole point of function notation, you can plug that value in. But if you do it on one side, you must do it on the other side. So if I told you, for example, that y was equal to, say, something like x plus h, I could say, well, what is f of x plus h? That's something you'll be calculating quite a bit. And this is something where a lot of people will get messed up, right, when they see the plus h, x plus h. Some of them are going to want to do f of x plus f of h. Some people are going to just take f of x and put a plus h on the end. None of these are going to work out correctly, because what function notation is telling you to do is it's telling you to take your input, right? And this tells you what should happen to the input. You should square the input, multiply by 3. Then you should take the input, multiply by -2. And then you should add those two together, add one more, and you get the result. So when you say f of x plus h, what you mean is 3 times x plus h, whole thing squared, minus 2 times x plus h. Again, leave it in parentheses, plus 1. Okay? And from there you can, if you're so inclined, you can expand, right? We know how to do FOIL. In fact, we might even remember the formula for the square of a binomial from a previous video. Write that out. We can put the constants through the brackets. 3x squared, 6xh, 3h squared, minus 2x minus 2h plus 1, right? Expand it out. There's not much more you can do with that. You could try to group things together or something, but yeah, pretty much you leave it at that. So the key is to remember that when you're working with functions, when you have expressions like this, right, this kind of notation that's common in calculus, right, remember that this is an instruction. Think of it as running a program. It's telling you what to do with an input, right? So whatever the input happens to be, you need to take your variable as it appears in the expression, replace it everywhere by that input, simplify if necessary to figure out what your output is going to be. Okay, so we've mentioned now a few times that in calculus we have these conventions around domains, right? We don't usually specify domain and codomain when we write down a function. Generally what we do is we just write down a formula like this one here, right? And so in a sense we're being a little bit careless when we do that, but we get ourselves out of trouble because in calculus there's a convention that we're all working with, so we all agree on domain, okay? And so the assumption that you make is that your domain is the set of all real numbers. Unless, well, there's a couple of scenarios. One is you might be in some actual practical applied context where it doesn't make sense for a function to be defined for all real numbers, right? You might be doing some sort of applied problem. Maybe you're trying to optimize a length, let's say, right? So we know that length is a quantity which can't be negative. It doesn't make sense to talk about a length of like -5 meters. So we wouldn't talk about negative length, so we would be in a context where we're only looking at positive numbers for input, right? So sometimes there is a domain like that that's stated. You have this applied domain, which you deal with. But most of the time the domain is left implicit. And if the domain is not specified, then you check to see if there are any values where your function is undefined, right? So if you've got something like a polynomial function, like this quadratic, it's defined for every possible value of x. So the domain is indeed truly R. It's all real numbers. But maybe you're dealing with like a rational function, right? Maybe you're dealing with something like 1 over x squared minus 3x plus 2. And you realize, oh, wait, I can factor that denominator, right? And I can factor that as x minus 1 times x minus 2. So in this case, if I wanted to specify the domain, and one of the notations that people will use for that is DOM for domain of f. And if you like, you can think of this as itself, it's a type of function, right? It's a function that takes a function as an input and gives you a set as an output, that set being the domain, okay? So the domain of f is, well, there's two ways you could do this. You could use this set builder notation and say, well, it's a set of all real numbers x such that, well, what do we have to avoid? We have to avoid dividing by 0. So I can't divide by 0. So that means x can't be 1, because 1 minus 1 would be 0. X can't be 2, because 2 minus 2 is 0, right? So there are two values of x that are not allowed. So I could write it like that. If you want, you could also write it as an interval. You could say, well, it's everything from minus infinity up to 1, open bracket, because we don't want to include 1, union, everything from 1 to 2, again, open brackets, and then everything from 2 to infinity. Right? That's another way that you could write that set. Okay? Another example, we could do something like this. We could do, let's say, g of x is the square root of 4 minus x squared. Okay? Now, again, we're working over the real numbers when we're doing calculus. We're not looking at scenarios where we might allow for complex numbers. Imaginary numbers are not part of the equation here. We know that if you want to stick to real numbers, you can't take the square root of a negative, right? Because we know that for any real number, if you square it, the output is going to be 0 if you're squaring 0. Otherwise, the output is positive, right? So, if you think about what a square root is doing, a square root is asking, which real number, when squared, will give me this result? And of course, it might be that there are no numbers. So we ask ourselves, okay, we want this square root to make sense. Well, that means you need 4 minus x squared to be bigger than or equal to 0, right? You want it to be positive. Maybe you like having the x squared out front. We've looked at inequalities already. If you switch the order, right, you're multiplying both of these by minus 1, right? You're flipping the sign. Remember that when you change the sign, the inequality reverses. This can factor x minus 2, x plus 2. We want it to be less than or equal to 0. So we draw ourselves our little number line. We know that there are two places where this is equal to 0. It's equal to 0 at 2 and minus 2. And in each of these three intervals that results, we can do test values and we can check, and we find that it's positive here, it's positive here, and it's negative in between. And we want the outcome to be less than or equal to 0. So that means we're looking for the minus sign, right? We want it to be negative. So the domain of G in this case. So again, we could write it in set notation. Set of all real numbers x, such that x is between minus 2 and 2. But of course, that can also be easily written as a closed interval from minus 2 to 2. Okay? So this is typically how we handle domain in calculus, right? Somebody gives you an expression like this. The first thing you want to ask yourself is, okay, are there any values of x? Are there any real numbers for which the function is going to be undefined, right? Are there any inputs that will not produce an output? I want to know what those are because I don't want to consider them. They're not going to be part of my domain. All right, so we're going to look briefly at graphs in the next couple of videos. Later on, once we do get to calculus, we will be looking at techniques for producing graphs of functions. The nice thing about graphs, it gives you a very concrete visual way of understanding what's going on with the function, right? Sometimes when we write down something like, even something as simple as a quadratic, we write down this sort of expression. So y equals f of x, right? This is the sort of equation that you see, which usually signifies we're dealing with graphs. And let's say that function is something like, let's say it's a quadratic, right? X squared minus 3x plus 2, something like that, okay? So just looking at this function, maybe you can't immediately tell me everything there is to know about that function, right? We might want to know things like, over which intervals is the function sort of, increasing, getting bigger as x goes up? Where is it decreasing? Where is it going down, right? So we want to know things like that. We want to know, is there a place where it kind of bottoms out? Does it reach a maximum? There are lots of things like this that we might want to know about a function, right? And all this behavior is relevant, right? Because we're using these functions to model things. We want to, model, let's say, phenomena that vary over time, right? So we might be interested in things like, maybe even something like a value of a stock. We want to know, is it increasing over time? Is it decreasing over time? Probably it's increasing some weeks, decreasing other weeks, right? Things tend to fluctuate, go up and down. We want to know what's happening. And sometimes the easiest way to see what's going on is to look at a graph. Now, somehow as soon as you put this y in there, there's this understanding that, okay, if you just have f of x, in the formula, now we're talking about a function, right? But if instead of putting f of x, I put y, now it's a graph. So why do we have this context? Why do we, as soon as there's a y in there, we're talking about graphs? Well, really what the graph is, and we can talk about this for any function, let's say f from a to b, really what it is it's the set of all ordered pairs a comma b. So this belongs to a set called the Cartesian product. You may not have seen this notation before, but don't worry about it because it's not going to come up that often. But this is just a way of denoting the fact that we want A to be an element of A, we want B to be an element of B. So it's a set of all ordered pairs where the first element in that pair comes from A, the second one comes from B, with the property that B is the element of B, of big B, that little a is assigned to by f, right? So it's a set of all B such that B equals f of A. So this is where the idea of a graph comes in. And the significance of x and y here is that these are the default variables when we're talking about things that live in what's often written as R2. So R times R, right? So elements here are of the form x comma y, where x and y are real numbers. And the important thing here is that this is an ordered pair, so there is this notion of first and last, right? Y comma x is not the same thing as x comma y when you're talking about ordered pairs. And we have this visualization, right? So we have this Cartesian plane. Okay. So this is an idea that goes all the way back to René Descartes, and it was actually quite a revolutionary idea at the time. So before Descartes, geometry and algebra were very much different topics. They were somehow not unrelated, but people tended to kind of do one or the other. They didn't really see connections between the two. And Descartes realized that algebraic expressions like this, like setting y equal to f of x, could be visualized, could be viewed on a graph. And the Cartesian plane, this Cartesian coordinate system, is this grid system, which we all know and love, right? We draw a pair of axes. We label the horizontal axis as the x-axis. We label the vertical axis as the y-axis. And the kind of the big revelation, the big idea, the big realization that Descartes had, and the story is that he had this revelation while lying in bed watching a fly crawl along his ceiling, and he realized that he could describe the location of that fly if only he knew the distance from that fly to 2 of the 4 walls in his room, right? So we would have x being the distance measured from one side, and y being the distance measured from the other side. And typically we would mark these distances on the respective axes. So we would mark x here, and we would mark y there, right? So once you have this idea of the Cartesian plane, well, now you can visualize a function, you can visualize the graph, you can plot the graph, because for every ordered pair, for every xy that satisfies this equation, you can plot a point, right? And so the most elementary thing that you can do here is you can just start choosing x values and seeing what the corresponding y value is, right? So we could go through and say, okay, when x equals 0, let's see, if x equals 0, y is equal to 2, right? So I kind of mark off, 1, 2, and I plot a point, right? When x is equal to 1, I would have 1 minus 3 plus 2. I get 1, right? So when x is equal to 1, y is equal to 1. And I plot a point, right? And so on. Actually, sorry, that's not even correct, is it? When x is equal to 1, y is equal to 0, right? When x is equal to 2, 4 minus 6 plus 2. Oh, when x is equal to 2, again, y is equal to 0. Okay. When x is equal to 3, you can work that out. Y is going to be equal to 2 again. And, but then you say, well, it's not going to be this, like, you're not going to draw straight lines in there. Right? You want to get a better idea of the shape, so you start filling in more points. You might say, well, what happens at 1.5? You find out that there's a y value down here, and so on. And eventually, you can fill in all the points, right? And you produce your graph. You get this graph of a parabola, right? And you can't individually plot every point on the graph because, of course, there are infinitely many of them. And it becomes pretty inefficient to use this technique of just plotting points, right? So you want to develop techniques. You want to come up with methods for quickly producing these graphs so that you can use that graph to understand the function. You don't want to sit there generating point after point after point after point. Well, unless you're a computer, right? If you're a computer, you can quickly generate enough points, within the sort of pixel density of your screen to produce something that looks good to the human eye, but it's not a very practical process for humans, so we want to look at some other options. Most of those options are going to come later on once we get into calculus, right? In calculus, we're going to learn techniques for understanding graphs of functions. For now, we're going to look at a few basic examples and a few basic principles to understand graphs of some simple functions. All right, so in the next few videos, we're going to look at function arithmetic. So this is just the various ways that you can combine old functions to get new functions. Okay, so basic operations are addition and subtraction. Okay. And they're defined exactly the way you think they should be defined. So if I have two functions, f and g, and I want to add them together, well, as usual in calculus, if we want to specify a function, we just have to tell you what it does with a given input. So f plus g is the function that if you give it an input x, it's going to calculate f of x, it's going to calculate g of x, and then it's going to add them together. Simple enough, right? And subtraction, it's the exact same story, right? If I wanted to do f minus g, I do f of x minus g of x. Okay, so that's pretty simple. So for example, if f of x was something like the square root of x, and g of x is something like 1 over x minus 2, and I want to calculate f plus g. Well, it's just f of x plus g of x, so it's root x plus 1 over x minus 2. Simple enough, right? One thing that you should probably watch out for when you're doing these is there is a domain issue to be aware of, right? So the domain of f plus g, well, in order for the right-hand side to be defined, right, root x has to be defined, 1 over x minus 2 has to be defined, or in general, right, to define the left-hand side, you need to be able to define the right-hand side. The right-hand side is the sum or difference of two numbers, so both of those numbers have to be defined. So that means that x has to be in the domain of f, and it has to be in the domain of g, right? It has to belong to the domain of both. That means that we need to take the original domains and intersect them. Okay? So for the example that we have on the go here, we know that f of x has domain (0 to infinity). G has domain, well, everything but 2, right? So minus infinity to 2, union 2 to infinity. So if we intersect those two domains, what happens is, well, we basically have to remove 2 from the domain of f, right? So f plus g is going to be defined if x is bigger than or equal to 0, but not equal to 2. So the domain for f plus g will be from 0 to 2, and from 2 to infinity. Okay? All right, so that's simple enough. From here you could move on to looking at multiplication. Okay. So multiplication you define more or less the way you think you should, right? The product, fg, evaluated at x, is just the product f of x times g of x. Okay? And the same domain rule applies here as we had for addition, and of course this would also apply for subtraction, right? I want to multiply these two numbers, so I have to make sure that f and g are both defined. Fair enough. So if we were going to do our example here, if I did f times g at x, well, I'm going to take this, I'm going to multiply by root x. Probably we'd combine that as a single fraction and write it like so. Okay? And you'll notice there's the same domain issue that you had before. Okay? The last one is division of these basic operations. And as you might expect, f over g evaluated at x is just going to be f of x divided by g of x. But here we also, there's an additional domain restriction. Of course, you can't divide by 0. So g of x needs to be non-zero. Okay? All right. So if maybe this function g of x, this we could think of this as having come from the constant function 1 and the linear function x minus 2, right? Both of those have domain all real numbers, but when I divide those two functions, the one in the denominator has a 0, and so that 0 needs to be removed from the domain, right? So 2 is not part of the domain. Curiously enough, this is an interesting one. If I use our example here, and this is probably a good thing to mention, in the case where f of x is root x and g of x is 1 over x minus 2, so if you do f over g at x, so that's root x divide by 1 over x minus 2. All right? And when we divide, we multiply by the reciprocal. So we get root x times x minus 2. You might be tempted in this case to say that the domain now includes 2. The domain is just 0 to infinity because you're multiplying by x minus 2 instead of dividing by x minus 2. That's not the case, however, even though this simplified form here is defined when x equals 2. The way we arrived at this was we started with this function g of x and we divided by it, right? And g of x is undefined when x is equal to 2, right? So even though the final expression does appear to be defined at 2, if we are arriving at it through this division process, well, you can't divide by a number that's undefined, okay? So the domain there would still be the same domain that we encountered for addition or subtraction or multiplication. Okay, so we're going to look at one other way that we have for combining functions, which is function composition. Now, function composition is fairly complicated, and in some ways more complicated than it at first seems. So the basic idea, which I'm sure you've probably seen, is, well, if somebody hands you two functions, f and g, you define this new composite function, f o g, whose value at x is given by first evaluating g at x and then taking that output and using it as an input for f, right? So g is evaluated at x, f is evaluated at g of x, okay? Sometimes it helps to sort of think schematically about what's going on when you're doing a function composition. So if g is a function from a to b, okay, so then that means that we start with a, right? That's where x lives. X is in here. And we apply this function g. Now we're over at b, right? That's where g of x lives. Now I want to use g of x as an input for f. That means that f needs to have b as its domain. Okay? F should go from b to c. So then I can define f here. Okay? And f of g of x will make sense. And so the composition is really the one that kind of takes you from here to there, f composed with g. So you think of it as sort of the direct route that doesn't pass through b. That's the composition. Now, occasionally we can relax things a little bit here. F doesn't necessarily need to be defined on the entire codomain for G, but at minimum it has to be defined on the range, right? So one of the things you need, right, sort of a necessary condition here is going to be that the range, the range of G has to be a, if you like, a subset of the domain for f, right? So every output for G has to be an allowed input for f. That's what this is saying, right? In order to define the composition. So those are the basic ground rules, right? So as far as when is composition defined, if I wanted to write down the domain, so the domain is going to be, so if we're working over the reals, it's going to be all real numbers x that 1 belong to the domain of G, and 2, when plugged into G, give me something that belongs to the domain of f. Right? So you kind of have to think carefully about how to form these compositions. If we want to look at some basic examples, we could look at, say, f of x equals x squared. We could look at g of x equals, let's go with something like an exponential function. Okay, so we can do that. So then it makes sense to ask, well, what is f of g of x? Well, we can kind of think about it two ways. We can think about this as f of g of x, so f of e to the x. So that would be taking e to the x and squaring it. Okay? Or I guess you could also think of it as, here I've kind of told you ahead of time what g of x is, but not yet what f of x is. We could do it the other way around. We could also say that it's g of x squared. But then, of course, once you plug in that g of x is equal to e to the x, you're back at the same spot, right? Now, you might do one more step if you remember your laws of exponents. If you square a power, right, a power raised to a power, you multiply the exponents. So you get e to the 2x. Now, one of the things that's worth pointing out here is that order of composition is important, right? So going from A to B to C is not the same thing as if you did F first and then G, you'd be going from B to C and then trying to get to A. Well, I guess you'd have to hope that C and A have something to do with each other, right? Now, of course, we're in this situation where A, B, C, all these sets, they're always subsets of the real numbers. So generally we're okay. In this case, both of these functions are defined for every real number, so we don't have to worry about domain, we just have to worry about putting these things together. So in this case, if I'm doing g of f of x, well, this time I'm taking g of x, which is e to the power f of x, okay? Where f of x is x squared. So what I get is e to the x squared. Okay? And that's a very different result from e to the 2x. Those are not the same function. Okay? So order matters. If we do one more example, well, let's keep the same f of x. Let's take h of x to be the square root function. Okay? So now we could ask, what is f of h of x? Okay? So f of h of x would be, well, inside function is the root function, outside function is the squaring function. Square root of x squared, right? And of course, if you square a square root goes away. You're left simply with x. Now, you have to be a little bit careful. You don't necessarily want to leave it just at that, because if we do want to pay attention to domain, right, in order to define this composition, right, I first need x to be a valid input for h, and I have to make sure that h of x is a valid input for f. Now, everything is valid input for f, but h of x does not take negative numbers as input. So I have to actually put a little condition here that f of h of x is equal to x, but I can only consider x bigger than or equal to 0. Okay? So you have to be a little bit careful about that. If you do the other order of composition, there's also something interesting that happens. H of f of x. So now you're going to take x squared, and you're going to take the square root. And again, you might be tempted to say that the square and the square root should cancel and just leave you with x. Well, once again, that's actually only valid if x is bigger than or equal to 0. So if you think about what happens when you put a negative number in there, if I put in something like minus 2, I square it. Minus 2, if I square it, I get plus 4. If I take the square root of 4, I get 2. I get positive 2, not negative 2. So any negative number that I use as an input here will be made positive. All right? Same number, opposite sign. Well, we know a function that does that. This is actually the absolute value function. Okay? So those are some basic examples using function composition. You can look for more. Of course, choose any functions you like. You can always plug one function into another. Here's maybe one you could try as an exercise. We could take something like f of x is x squared minus 2x. G of x is going to be, let's say, x over x minus 1. And you can try doing composition in either order, right? The important thing to remember here is keep a good handle on function notation. If I'm doing f of g of x, right, that means I take g of x, and everywhere I see an x, I plug in g of x, right? So f of g of x, we could write that as, well, g of x squared minus 2 times g of x, right? Your next step would be, of course, to plug in g of x, and then if you want, you can simplify, and then you could try the other order if you want, right? But you got to make sure you slow down, do these things carefully. It's easy to make algebra mistakes if you're not being careful with these. All right. Before we move on from function composition, let's say a few quick words about inverses. We'll come back to inverses later on in calculus once we're looking at derivatives of inverse functions and things like that. But now is probably a good time to at least cover the basics, right? So if I have a function f going from, say, a to b, right? So I have some element x here, and x gets sent to some y, right? So y is f of x. The inverse, I want the inverse to go the other way, right? So the inverse should be something which undoes what f did. And so that means that the inverse, which we usually denote with this -1 superscript, maybe we should just call it g, it should go the other way. It should go from b to a. Okay? And if I start with f of x, I should get x. Okay? Simple enough. So what that amounts to saying is that if I do f inverse of f of x, I should get x. And similarly, if I did f of f inverse of, well, maybe we should call it something else. Maybe we should call it, what do we call it? Y. Right? Y was f of x. Right? So if I start with this element y here, I apply f inverse, right? That gets me x. Okay? So I apply f inverse to y, right? Remember that this is y. So f inverse of y is equal to x, but f of x, well, f of x was y. Right? So when you combine a function and its inverse, whichever order you choose to compose them in, notice that you end up where you started. Okay? So there's a name for this. There's something called the identity function. So maybe we call it, say, I, right? I of x equals x, right? Every set comes with an identity function that just associates every element with itself, right? It goes from a set to itself. And so what this amounts to saying is that f composed with f inverse is the identity function. If you like, this is the identity function on B, and f inverse composed with f is identity function on A, right? So they cancel each other out. So this is where the idea of the inverse comes from, right? They cancel each other out in the same way that a number and its negative cancel each other out if you're doing addition, right? They cancel and leave you with 0. 0 is sort of an identity element for addition, right? Because if you add 0, nothing happens. In multiplication, a non-zero number, and its reciprocal are viewed as inverses of each other, because if you multiply them, you get 1. And if you multiply by 1, nothing happens, right? A function and its inverse, right? These are, again, you use this word inverse. This time it's with respect to composition, because if you compose them, you get the identity function. And if you apply the identity function, nothing happens, okay? So that's where this notion of inverse comes from. That's where the word comes from. But the caution here is that if you want this thing to be a function, I think orange is done. Your function f must be what's called 1, 2, 1. Okay? So there's this property of being 1 to 1. And usually the way you characterize this is you say, well, if f of x1 equals f of x2 for some numbers x1 and x2 in the domain, well, the only way that can happen as if x1 and x2 were really the same thing. Another way of putting this is that if x1 isn't equal to x2, then f of x1 can't equal f of x2, right? So this is saying that you can't get the same output for two different inputs, right? For a regular function, that's allowed. You know, for functions are allowed to have this happen, right? You can have more than one input give you the same output. But if you want to reverse things, or if you want to undo, if there were two different elements of the domain that get sent to the same thing, and you're sitting there and you're staring at this y in B, and you want to get back to x, right? Well, if this y came from two different x values, how are you going to choose which one it should be, right? You don't actually have a function, right? It's not a function if this input for the inverse could be associated to more than one output, right? So there's this issue of being one-to-one that you have to check. We can do one example with this to show you how you check for a function being one-to-one. How do you find the inverse? And then we're going to move on to other types of functions. All right, so let's look at some simple examples of one-to-one functions and their inverses. Okay? So remember that one-to-one means that for any possible inputs, let's say x1 and x2, if f of x1 equals f of x2, then x1 equals x2. And this is a fancy way of saying that you can't have the same input for different outputs, right? So if I have two outputs, or sorry, same output for different inputs, right? If I have two outputs that are the same, then they came from the same input, right? So if we do something like, let's say, let's do something simple like a linear function, 3x minus 2. Now, you can almost work out what the inverse should be if you just think about, the function in the sense of it's a rule that tells you how to do something, right? So what does this function tell you to do? It tells you to take a number, multiply by 3, and then subtract 2. So if you were trying to undo that function, just like the undo key if you're working on a word processor or something like that, right? You always undo in the opposite order, right? You undo the most recent thing first. So first thing I'd have to do is I'd have to get rid of the minus 2. So I'd have to add 2. That would cancel out the fact that I subtracted 2. Then to cancel out the fact that I multiplied by 3, I'd have to divide by 3. Right? So that tells me that I should be able to reverse this function. The way I confirm is, we say, well, let's suppose that f of x1 does in fact equal f of x2 for some x1, x2. Well then, 3x1 minus 2 would have to equal 3x2 minus 2. And if I add 2 to both sides, 3x1 would equal 3x2. And I can divide both sides by 3. And I confirm that indeed x1 is equal to x2. All right. Now, how do you go about finding that inverse? Okay. Well, one of the things that you'll notice here is that one of the things that's kind of hiding in this is that this is x, right? So if y is equal to f of x, then x is f inverse of y. So what I should really do is let y equal f of x, which is 3x minus 2. then y plus 2 is equal to 3x. And that means that x is equal to y plus 2 over 3. Exactly as we said. To reverse this function, we should first add 2 and then divide the result by 3, right? So that means that f inverse of y is y plus 2 over 3. And if you want to write that as a function of x rather than a function of y, that's fine. Remember that the y is just some dummy variable. It's a placeholder. So if you want to put an x here, just put an x there, and you've got it, right? You can do it that way. Okay. I'll give you one more example. Let's go with x minus 1 over 2x plus 3. Okay? I'm going to leave it as an exercise to confirm that this is indeed a one-to-one function. It's not so bad. There's a little bit of work involved. You got to cross multiply. It's doable. So if we want to find the inverse, let's set that equal to y, right? Set it equal to y. Y is f of x. F inverse of y should be x. So we've got to take this equation, solve for x. So let's see. Let's cross multiply. X minus 1 is y times 2x plus 3, which is 2xy plus 3y. Okay, now let's think for a second, what are we trying to solve for? We're trying to solve for x. So let's get everything with an x on one side. X minus 2xy is equal to 3y plus 1. Okay, so I want to solve for x. Next thing I should do is I should factor an x out from this left-hand side. X times 1 minus 2y is 3y plus 1. And so if I want to solve for x, I just have to divide by 1 minus 2y. So f inverse of y, which is x, is 3y plus 1 over 1 minus 2y. And there you have it. All right, so in the next couple of videos, we're going to take a look at exponential functions. Now, earlier in the algebra review, we already looked at laws of exponents. We went over some of the basics there, so you'll remember that, for well, if k is a natural number, so if k is 1, 2, 3, and so on, when we write a to the power k, we just mean a times a times a, right? We think of this as repeated multiplication, so it's a times a times a, and you do that k times. And that works for a while, but eventually you want to generalize to cases where maybe k is an integer, so we allow for exponent 0, we allow for negative exponents, and then you want to move on to maybe allow for rational exponents as well. And so eventually, you come to the, your rules, right? So we have these rules. And I'm not going to repeat all the laws of exponents. We've seen some of them, but we know that, for example, a to the, let's say, m plus n is the same thing as a to the m times a to the n, right? And we say that a to the minus k is the same thing as 1 over a to the k. And you can make sense of these in terms of this basic idea that exponentiation is repeated multiplication, because if you think about division, right? If you're dividing, right? So for example, let's say I have something like 2 to the 4, and I want to multiply by 2 to the minus 2, right? Well, on the one hand, this rule here says that that should be 2 to the 4 minus 2, so it should be 2 squared, which is 2 times 2. On the other hand, if I'm doing 2 to the 4 times 1 over 2 squared, right, then that's, well, it's 2 times 2 times 2 times 2 over 2 times 2, right? And 4 on the top, 2 on the bottom. You can cancel. There's 2 left over. Again, you get 2 squared, and so on, right? You can make sense of something like, a to the 1 over n. Why is that equal to the nth root of a? Well, that's because if I do a to the 1 over n to the power n, right? Well, that's a to the 1 over n times a to the 1 over n, right? And again, we do that n times. So it's a to the 1 over n plus 1 over n, right? Again, 1 over n added to itself n times is a to the n times 1 over n, which is just a to the 1, right? You get a. So you can make sense of all these rules, and basically, you start with this idea of repeated multiplication. From repeated multiplication, you derive these rules, and then at some point you want to move on, right? You want to consider negative exponents. You want to consider rational exponents. We want to be able to define exponential functions as a function of a real variable, right? So if you want to define things as a function of a real variable, well, then you kind of have to generalize it. And the way you generalize is you say, well, really, ultimately, you just say that the rules of the thing, right? So we have this one. The other one that's missing, which we already sort of see in action there, is this one, right? So you take these rules and you kind of generalize and you use this to produce a function, right? And so for any positive real number a, right? So a here is a real number. You can define a function. So you define, let's say, f of x equals a to the x, right? So in this case, right, your input x is a real number, and you can actually do this for any real number. As long as a is positive, this will be defined for all real numbers x. And the output is just a raised to that power. And so you say, okay, well, do we know what we're doing here? Do we know how this works? Well, we know what to do if a is, if x, right? So we know this we know what this means if x is a natural number, right? If x is a natural number, then we have this repeated multiplication. Okay. We know what it means if x is an integer, right? Because we know how to handle negative exponents. And we know how to handle a to the 0, right? Because if n is equal to minus m, let's say m minus n, right, I get 0, right? But then you're just doing a number divided by itself, you get 1. So we know that a to the 0 should be 1, right? And so then you say, well, what about if we have a rational number? What if x is rational? Well, actually, we know how to handle that too, because we know how to deal with reciprocals, right? Things where you have 1 over an integer. We know how to deal with that. And we have this rule here. So if I wanted to do a to some rational number, let's say something of the form p over q, we know that we can do that as a to the 1 over q and raised to the power p. Or if you like, a to the power p and then to the power 1 over q, right? It doesn't matter whether you do the power first and then the root, or the root and then the power, right? Keeping in mind, remember that a is positive here, so we don't have to worry about, well, what if a is negative, right? That's not something that we're going to consider. So we know how to deal with rational numbers. And now the question is, well, how do you extend things? How do you deal with a real number? And here's maybe where a little bit of calculus comes into the picture. And so what we can say is, well, we'll deal with real numbers. Maybe we could say by continuity. And what do we mean by that? Well, what we mean by that is that you can, of course, plot an exponential function, right? So if we had, so here's some axes. And so I'm going to plot, let's say a is bigger than 1. So if a is bigger than 1, it's going to go up like this, right? So we know that a of 0 is 1, right? And then, we get that, and then, so we plot our integer values, right? Then you fill in the rational values. And you get something like that. And I mean, it's actually better than this because the rationals have this property of being dense in the reals, right? In calculus, we usually don't get into these technical details, but one of the things that you can prove is that choose any two real numbers you want. There's always a rational number in between them. So the rational numbers are packed in there really tightly, really close. But we know that the rationals aren't everything. There are irrationals. In fact, there are, in some sense, more irrational numbers than rational. But you the way you define it for a real variable is by just kind of, connecting the dots, right? So to get your exponential function of a real variable, you fill in the gaps, and the continuity just means that you fill it in so you get this continuous unbroken line, right? You're not gonna suddenly put a point up here. You're gonna follow the curve, right? And that's one way of thinking about how you might define an exponential function of a real variable. All right, so in the last video, we introduced exponential functions. So we said we can define f of x as a to the x, where x is a real number. We do have this condition here that a has to be positive, right? We can't define exponential functions for a negative base because we know that we run into problems with things like square roots of negative numbers, right? In fact, if a is negative, then the only values that are going to work for the exponent are going to be either integer exponents or rational exponents where the denominator is odd, right? And things are in lowest terms. So you can't define exponential functions if the base is negative, but for any positive value of the base, you can make sense of this, right? Here are a few of the graphs, right? So for a bigger than 1, you get something which kind of grows like this, right? And they grow very rapidly. You probably hear this term exponential growth, right? Referring to something that grows very, very quickly, gets very big very fast, and that's because these exponential functions do indeed grow very big very fast. So exponential functions grow faster than any of the other elementary functions that you're used to dealing with. As the base gets bigger, the growth rate is faster, right, at the positive x end. At the negative x end, they tail off towards 0. So they get closer and closer and closer to 0, but they never quite reach it, right? So the x-axis is a horizontal asymptote, but only on one side, right? So it's a horizontal asymptote as x goes towards minus infinity, if you like. Okay? If a is between 0 and 1, then you get this decreasing function rather than an increasing function, right? So it's big for negative values of x, and then it shrinks down towards 0. Of course, you could also put a equal to 1, but it's not very interesting because 1 to any power is just 1. And so you in fact have a constant function. So we're not so interested in that. One of the ones that's not pictured, which is the most common exponential function, is the natural exponential. And that kind of sits somewhere in here. Okay. So here is y equals e to the x. So this e is Euler's number. And it's around 2.7. Okay. It's an irrational number. In fact, it's what's called a transcendental number, just like pi. So it's it's in some sense a complicated number. In some sense, a simple number. It turns out that for a lot of reasons, the natural exponential, especially from the point of view of calculus, is the best exponential function to work with. E is the simplest base, despite the fact that it's an irrational number. It's a simple base to work with. We'll see that derivatives and integrals working with base e are much, much, much simpler than using base 2 or base 10 or one of the other log bases that you might have worked with in high school. Okay, so properties. What can we say about exponential functions? Well, for any base, the domain of my exponential function is all real numbers, so they're defined for every possible value of x, right? We saw that for a bigger than 1, we can say a couple of things. We can say that as x gets big, f of x gets big too. We can say bigger. All right, it grows very rapidly, and as as x gets big and negative, f of x gets close to 0, right? So we have this idea of an asymptote. Once we have the language of limits, we can state this much more quickly and much more precisely what we mean here. And for a between 0 and 1, it's just the opposite, right? So for every number between 0 and 1, its reciprocal is bigger than 1. And if you take the reciprocal of the base, you just reflect the graph across the y-axis. So you just get the behavior going in the opposite direction. Okay. What else can we say about exponential functions? Well, we have the algebraic properties that we've seen previously as properties of exponents. So we know that f of x plus y is f of x times f of y, right? We know that f of x times y is the same thing as f of x to the power y. And we know that f of minus x is 1 over f of x, which looks a little bit complicated when you put it in function notation, but these are just the familiar rules, right? That a to the x plus y is a to the x times a to the y. A to the x y is the same thing as a to the x to the y, and a to the minus x is 1 over a to the x. Okay. All right. So those are the basic properties of exponential functions. Okay. Going into calculus, the main things you need to be comfortable with for exponential functions is this kind of basic knowledge of what the graph looks like, right? The fact that there is this asymptotic behavior at one end and rapid growth at the other end. The fact that it's defined for all real numbers, and these algebraic properties, because certainly you'll find yourself working with these algebraic properties at various times, and you know you can sometimes get yourself mixed up on these properties. So some people will get mixed up and they'll think that maybe this should be x times y, or maybe they think that there should be a plus sign here. It's easy to get mixed up on some of these rules. If you find yourself getting mixed up, you could always kind of come back and remind yourself, well, if x and y are natural numbers, then this is just sort of repeated multiplication, and you can make sense of things that way, right? If you find yourself stuck and you're not sure of the rules, but that's mostly what you're going to need to be comfortable with is these algebraic properties and some good working knowledge of the graph. If you've got a handle on those, you should be okay as far as exponential functions go. Okay, next up, we're going to talk about logarithms. I've left this graph up on the board here for exponential functions, right? So remember, for a base a, where a is positive, we can talk about these exponential functions, right? If a is bigger than 1, we have these ones growing like that, right? 2 to the x, 3 to the x, in between we have e to the x, the natural exponential. So logarithms, the reason we're leading into logarithms from exponentials is that logarithms are defined as the inverse of the exponential, right? So if I give you y is equal to a to the x, and I want to take the logarithm base a of y, what I get is x. Okay. So in other words, you have this cancellation property, which we know we have in general for inverse functions, right? So we know that log base a of a to the x is equal to x, and we know that if I did a to the power log a of x, that also gives me x. Okay, so the logarithm is defined as an inverse. So another way that you could say this is that y equals a to the x if and only if x is equal to log base a of y. Or another way you might say this is if f of x is equal to a to the x, then its inverse function is the logarithm. So what a logarithm does is you feed it a number, right? So suppose you feed it some number, let's say this y that we have here, right? So you plug y into your logarithm. So what does the logarithm do? What the logarithm does is it gives you the answer to the following question. That question being, if I were to write y as an exponent, as a power, if I were to write y as a power with base a, what exponent would I need, right? So what power do I have to raise a to get y? That's what the logarithm is answering for you, right? So that means that, for example, if I wanted to know what is the base 2 log of, let's say, 16, I say, oh, well, how do I write 16 as a power of 2? And I say, okay, well, 16 is 2 to the 4. And the logarithm gives me the exponent, so my answer is 4, right? So that's the basic idea of a logarithm. Now, Most of the time, you don't get lucky, and the number you're plugging in there is not a perfect power for the base that you're working with. And so you're not going to get a nice round number out. You're probably going to get something fairly complicated, right? But it gives you a starting point. It gives you some idea of what you're working with here. The other thing you can do is you can now work out what the graph should look like for a logarithm, right? So if this is what the graph looks like for an exponential function, let's put it down here. Okay. So if we have some exponential function like this, so here is y equals a to the x. Okay. Here's the line y equals x, which you might reflect across. And so remember the basic idea with inverses is you're interchanging the role of x and y here, right? So if xy is a point on the graph of y equals a to the x, then yx is a point on the graph of the logarithm. And so everything kind of reflects across. So that means that, if we had, so this point here is always 0, 1, which means that 1, 0 must be a point on the graph of the natural log. Okay. As x gets small, as x goes to minus infinity, y gets close to 0. So we interchange those roles. As y goes to minus infinity, x goes to 0. So that means there's now this vertical asymptote along the x-axis. So you have that sort of behavior going down, and then it's going to come up and head off that way, right? So y equals log base a would look like that. And of course, if a is between 0 and 1, then we reflect everything across, right? That's going to go that way. The log is going to go that way. And we can deal with that as well. So that's the basic definition of a logarithm, log base a. Most of the time, and let's just add this in as our last point here for notation. And then in the next video, we're going to look at properties. So when you're working with the natural exponential, the log base e, in most calculus textbooks, we write ln for natural log. Okay, ln of x is the natural log. So ln of x is the inverse of the natural exponential e to the x. One word of warning, one word of caution. There are some notational discrepancies. In most calculus books that are sort of targeted towards science and engineering, this is the notation you're going to see almost universally for the natural log. In textbooks that are geared towards pure math students, like math majors who aren't planning to do anything in the sciences, sometimes if you see just log with no base indicated, the assumption is that that's the natural log, because for mathematics, for pure mathematics, base e is really the only base that you care about working in. You don't really care about other bases. So you just stick to base e. So you just write log for the log. You kind of treat it as there's only one log. But in the sciences, if you write log with no base, sometimes that's interpreted as base 10. So if you see log without a base, you really need to ask yourself what the context is. Am I in kind of a math context, and then it's probably base e? Am I in a science context, in which case it's probably base 10, right? If you want to avoid the ambiguity and you're working with natural logs, you can write ln to be safe. Okay, so we're ready to look at some of the properties of logarithms. Now I'm going to focus on the natural logarithm here rather than general base a logarithm, because once you understand the natural log, it turns out you understand every log. Every other log is going to be basically the same as the natural log. We'll go into details on that, explain why that's true towards the end of the video. Okay, so basics. the natural log is defined as the inverse of the natural exponential, okay? And so we can think a little bit about, well, what do we know about the natural exponential? We know that the domain is all real numbers. It's true for every exponential function. We saw from the graph that the range is from 0 to infinity, right? As x gets negative, the graph approaches the x-axis, but it never actually reaches it. So the range is from 0 to infinity. Domain is R. When you take the inverse, domain and range, they switch roles. So that means that over here, the domain is going to be from 0 to infinity. So in particular, that means that the natural log is not defined for 0. It's not defined for negative numbers. It's only defined for positive numbers, right? And the range, well, the range is all real numbers. So the range is from minus infinity to infinity, right? If you remember what the graph looks like, this makes sense, right? Let's just throw that in here. Okay. So the graph for your natural log looks something like this. Right, we have this intercept at 1, 0. So all the negative values in the range are attained for x values between 0 and 1. And the positive values are attained for x values bigger than 1. One thing to point out is that this is a very slow growing function, right? It's the inverse of the exponential. We said the exponential is very fast growing. The logarithm is one of the slowest growing functions, right? I mean, not as slow as, let's say, a constant function or something like a sine function, which is periodic and never gets bigger than 1. But it, as x gets big, the natural log will eventually get big. It will eventually go to infinity, but it gets there very slowly. Okay, and that's one of the reasons why people like using logarithms. Logarithms are useful when you're working with very large numbers. They sort of tame those numbers down. They give you smaller numbers that are easier to work with, right? Another reason that people like logarithms is they tend to take complicated arithmetic operations and turn them into simpler ones, right? So one of the properties that we have for the natural log is that the natural log of, say, a times b is equal to the natural log of a plus the natural log of b, right? So if you've got some collection of numbers that you're working with, and you've taken the natural log of all those numbers, then multiplication becomes addition, right? Addition is simpler than multiplication. It's easier to work with, right? Why is this rule true? Well, if we use this association here, right, so we can see why this is true. Okay. On the one hand, I know that the natural log of a times b would be the natural log of e to the x times e to the y. If I set a equal to e to the x and I set b equal to e to the y. But I have a property here for exponentials, right? We know that e to the x times e to the y is e to the x plus y. Okay, so I can write it like that. But I also know that if I take the log of the exponential of something, those cancel out, right? Because they're inverses of each other, right? The fact that f and g are inverses, right? This means, remember the definition of the inverse tells you that f of g of x is equal to x for any input x. So in particular for this input x plus y, we have that, right? So this is just x plus y, all right? But what's x plus y? Well, x is the natural log of a, y is the natural log of b. And that gives you the right-hand side, okay? So similarly, you could do this with division. Okay, so the natural log of a over b is the natural log of a minus the natural log of b. And why is that? Well, let's see. The natural log of a over b would be the natural log of e to the x over e to the y, which is, well, we know that e to the x divided by e to the y, right? Another property of exponents says that's e to the x minus y. So that's e to the x minus y. And again, the log and the exponential cancel each other out because they're inverses. I get x minus y. So I get log of a minus log of b. Right? The last property, which can be quite useful, is that the natural log of a raised to a power, let's say k, is the same thing as k times the natural log of a. Okay? So this can be quite useful, right? This tells you that again, right, logarithms are simplifying your arithmetic. It's taking a power, right? Exponents is a fairly complicated arithmetic operation, and it's just turning it into multiplication. So things are simpler, right? And the reason why on this one, well, if I do the natural log of a to the k, where a is e to the x, again, I have a property of exponents that says if I do e to the x and I raise it to some power, that's the same thing as e to the k times x. So this is the natural log of e to the k times x. And once again, I use the cancellation property of inverses to get k times x, and x is the natural log of a, right? So I get that property. Okay, so those are the three main algebraic properties of logarithms, right? Together with domain, range, this picture of the graph. The other thing that's probably useful to remember is this intercept. Log of 1 equals 0. This is actually true for any log, right? For any log, if you plug in 1, you get 0. Right? Any base, that's the result. Okay, now I mentioned that this is really all you need to know, is these properties, and you need to know them for the natural log. The reason that's all you need to know is there's a formula that lets you work with logs in other bases. There's this so-called change of base formula. I think we'll look at that in the next video. Okay, so in the last video we introduced the natural logarithm. We went over some of the properties. We showed how these properties followed from properties of exponents, right, from the exponential function and its properties. And I mentioned that, as long as you have these properties and as long as you kind of know what the graph looks like, you know pretty much everything you need to know to work with logarithms, right? Again, it's easy to make mistakes with these properties. There's always some wishful thinking that there should be a rule when you have addition inside the logarithm. Unfortunately, there isn't. So some people will get these mixed up. It's okay, it happens. You get the hang of things with practice. But the one thing that does come up is, okay, what if you have some other base, right? I did everything for the natural log. So what if you're working with, say, base A, right? So let's say, what about let's say we're doing f of x equals log base a of x. Okay? We want to understand how to work with this. So it turns out, once you understand the natural log, you pretty much know everything because every other logarithm can be written in terms of the natural log. To see how this works, let's let y equal to base a log of x. Okay? Now, remember what this means. Saying that y equals the base a log of x is the same thing as saying a to the y is equal to x. Right? Okay? Now, here's a trick that you can do. Remember that the natural log is the inverse of the exponential function, right? And that means that maybe not f. Since e to the x and ln of x are inverses, that means that if I did e to the log of x, they cancel each other out. They give me back x. So in particular, I could do a to the y would be the same thing as e to the natural log of a to the y. Okay? And that in turn was equal to x. Okay. Now, remember that we have this property down here, right? We can bring the k out front. Okay, so I can bring that y out front. So I can say that e to the y times the natural log of a is equal to x. Okay? Now, let's take the log of both sides and see what happens. The natural log of e to the y ln a is equal to the natural log of x, right? Natural logs of functions, so equal inputs have to produce equal outputs. Very good. But since these are inverses, it's also true that if I do the natural log of e to some power, again, those cancel out and just give me back the power. So that means that what I get is that y times the natural log of a is equal to the natural log of x. And remember what y is. Y was our original base a log. So I can solve for y here. And what do I get? I get that y, which is the base a log of x, right? And from there, I can see that y is the same thing as the natural log of x divided by the natural log of a. So I get this. Okay? This is the so-called change of base formula. Okay? And what it tells you is that a logarithm in any other base can be written in terms of a natural log. So if you understand the natural log, you understand every other logarithm. And again, from the point of view of calculus, we're going to see that once we get into derivatives, integrals, things like that, even limits, the natural log is easier to deal with than logs to other bases, and so we try to do everything in terms of the natural log. All right, we're going to finish our review of logarithms with a couple of quick examples. First, we're going to look at some of the graphical properties, and then we're going to play around with some of the algebraic properties. Okay, so here's a function. F of x is the natural log of 3x minus 6. We want to figure out the domain. So we come over here, and we notice that for the sort of basic natural log with just x as input, the domain is x has to be between 0 and infinity. So that means the input has to be bigger than 0, right? So when we come over to something like this, it's no longer the case that we just need x to be bigger than 0. We need 3x minus 6. The whole input has to be bigger than 0, right? That means that we need 3x to be bigger than 6. So that means we need x to be bigger than 2, right? So we can leave our answer like that if you like, x bigger than 2, that's your domain. If you prefer, you can write that as the integral from 2 to infinity. So that means that if you were going to try to plot the function, okay, well, the first thing you're going to need is you're going to need a vertical asymptote now at 2, right? So there's a vertical asymptote where the domain begins. Okay, right? So essentially we've shifted it over, right? One way to think about it is this is 3, if you factor out the 3, right? 3 times x minus 2. So if you think about it that way, what we've done is we've shifted to the right by 2 units, thinking in terms of transformations. We shifted to the right by 2 units, and then we've compressed horizontally by a factor of 3, right? And so all that's going to do is that's going to is going to kind of, rather than having it go like that, it's going to be a little bit steeper, right? The general shape is still the same, okay? We can still work out, if we want to know what the intercept is, we can say, well, we know that the intercept is going to happen when the input is equal to 1, right? We know that the natural log of 1 is always equal to 0. So if we set 3x minus 6 equal to 1, so 3x equal to 7. So at x equal to 7 over 3, right, which is what? Just 2 1/3. So it's around there, right? So you can see it's compressed by a factor of 3, right? Rather than the intercept being 1 unit over from the asymptote, it's only a distance of 1/3 from the asymptote, and then we can plot it in. So we're going to have something that looks like that. Okay, there's our graph. Notice that it's the same general shape, right? It's just a transformation of the original. Okay, now here's an algebraic problem. This is working with the properties. We're given 3 values for the natural log. Log of a is 2, log of b is minus 1, log of c is 3. We want to find the value of this ugly looking expression here. Okay, now one of the mistakes that people will make, this becomes a complicated question if you think that, well, if you think that this is telling you that your first step should be to solve for a, b, and c, you're going to have a terrible time with this problem. And yes, I could solve for them, right? A is going to be e to the 2, b is going to be e to the minus 1. I could do that, but the point is that I don't have to do that because I have these properties. The point is these properties let me break things down. One thing that you want to watch out for, I put square brackets around the one in the denominator to make it clear that that power applies to the logarithm and not to the input. This power rule here, log of a to the k, this applies when the exponent is inside the logarithm, not outside. One of the problems is that we sometimes encounter ambiguous expressions like this. Now, in this case, the intent is that that power is inside the log. Usually that's sort of the assumption if it's not clear. If you're ever unsure, you could always ask, right? Be like, hey, this is ambiguous, can you clarify? Okay, so with something like that, we can, on the top, we can use the exponent rule, right? And we can write the top as 3 times the log of a cubed b to the 5 over c to the 4. The other thing we could have done is we could have applied we could have used laws of exponents on the inside, right? A to the 9, b to the 15, c to the 4. It's going to work out the same in the end, whichever way we do it, but that's fine. And on the bottom, there's actually not much you can do, right? You just leave it as is. One of the things to be careful about here is there's going to be a temptation to bring that power down in front. But because that power is outside the natural log, it's outside the function, there's nothing you can do about it other than work out the value on the inside and then square. Okay, now what do you do from here? Well, with something like, I'm going to work over here because we don't have that much room. With something like log a cubed b to the 5 over c to the 4, we could apply the quotient rule and say, well, that's like the natural log of a cubed b to the 5 subtract the natural log of c to the 4, right? And then you could apply the sum rule to that first term, right? And you could write it as log of a cubed plus the log of b to the 5 minus the log of c to the 4. Once you get the hang of this, you'll realize that it's always going to be the case that terms in the numerator just come with plus signs, terms in the denominator come with minus sign, right? When you have things factored like this. And then finally, you can bring the powers down, right? So what you're going to have is, you still have that 3 out front. You're going to have 3 log A plus 5 log B minus 4 log C, okay? On the bottom, you can use that same reasoning to say, well, I've got 2 log A plus log B minus 2 log C, and that whole thing is still squared, okay? And from here you can put your numbers in. I'm running out of boards, so maybe I can put it just above. So what do we get? We get 3 times log A. So 3 times 2, 6. 5 times log B, so 5 times minus 1, 6 minus 5, minus 4 times 3, minus 12. And on the bottom, 2 log A, so 2 times 2, 4, okay, minus 1, minus 2 times 3, so 4 minus 1, minus 6, and I want that squared, okay? All right, so minus 33 over, what's that going to be on the bottom? Over 9, which I suppose you can simplify to minus 11 over 3, right? But the point is to use the properties of logarithms, break everything down, then put in your numbers, right? It's primarily an exercise in making sure you know these properties, making sure, so the other pitfall here, when you have a log divided by a log, there's going to be the temptation to try and apply this rule and subtract the 2. But that only works if the division is inside the logarithm, not outside, right? All these rules apply when the operation, right, the multiplication, division, or the power is inside the log, and then you can split it up into something simpler on the other side. All right, so we've been doing a lot of algebra. We're going to take a short break from that. We're going to talk about graphs for polynomial functions, right? So we've been looking at polynomials. We've been looking at things like how to factor them, right? Things like long division, all this stuff, algebra, manipulating polynomials. What about graphing, right? Later on, when we're doing calculus, there's going to be a fair amount of graphing involved. What do polynomial graphs typically look like? Well, it helps to first think about what do power functions look like? Okay, so what if I have a function that looks like f of x is equal to a times x to the n. Okay, so n here could be 1, 2, 3, and so on. Okay, well, depends somewhat on whether a is positive or negative. Okay, but let's do n equals 1, 2, 3, 4. We'll do a few just to get a feel for what's happening. Okay, so coordinate axes in each case. There we go. All right. Now, when n equals 1, of course, in that case, you're just dealing with a linear function, right? X to the 1, we get a straight line, right? A straight line with slope a, intercept 0. So it passes through the origin, right? If a is positive, positive slope. So we have something like that, let's say. If a is negative, negative slope, we're dealing with something like that. N equals 2, that's your basic quadratic, opening upwards. If a is bigger than 0, opening downwards. If a is less than 0. Okay. N equals 3, your basic cubic looks like this. It starts negative. It's going to flatten out as it passes through the origin and then head up. So it's going to look like this. Okay? And if a is negative, same thing, but flipped. Okay? Cubics are going to look like that. Degree 4. Degree 4 looks a lot like degree 2. It's just going to be a little bit steeper on the edges and a little bit flatter on the bottom. We get something that kind of looks like this. Okay? Something like that for degree 4. Okay? Degree 5 is going to look a lot like degree 3, except again, steeper out here, flatter in there. Degree 6 going to be like degree 4, but it's going to kind of be, again, a little bit steeper on the sides, a little bit flatter on the bottom, and so on, right? So in general, all the even degree ones are going to look something like quadratic. All the odd degree ones are going to look something like cubic, okay? Now, it's important to know what these power functions look like, because in general, right, you're going to be looking at a function of the form, say, an x to the n, right? It's going to be your leading term, plus maybe some lower degree stuff, right? General polynomial function. Now, that leading term, that's the dominant term, right? So this is going to be sort of the most important term when the absolute value of x is big. Okay, so are they large and positive or large and negative, right? So as you kind of head out, right, your polynomial is going to look a lot like one of these. So the so-called end behavior, if you like, what happens eventually, is determined by that leading term. Okay, everything else controls what's going on in the middle, right? So if you've got additional terms other than that leading term, that's going to sort of, spice up things here in the middle, right? You might have some roots, right? So we know what it kind of looks like when x is big and when x is small. So if we're kind of nearer to the origin, that's where we want to look at the roots. Okay? So as an example, let's say we have a polynomial, and I'm going to factor it for you. Let's say we have something that looks like x minus 1 times x plus 2 squared. Okay, that's our polynomial. What is that going to look like? Well, let's draw some axes. So first of all, we know that if we were to multiply this all out, and we don't have to multiply everything out, but we can see without doing all the work that the leading term, right, there's going to be an x squared here times x. So the leading term is going to be x cubed, right, plus some other stuff. So we know that eventually it's got to be doing something like that, right? It's got to look like n equals 3 because it's cubic, right? But you might have some other stuff going on in between. So that's where you look at the zeros. So this thing touches the x-axis twice. It touches it once when x is equal to 1. So let's mark off, say, 1, 2, 3. So there's a 0 there, minus 1, minus 2, minus 3. The other 0 is at minus 2. So what I know is that I'm going to come down, I'm going to hit that 0. So what happens at that 0? Well, one of the things that I can do is I can kind of on the side, I can do a little number line. I can mark off those two zeros, right? Minus 2 and 1. Those are the two roots for my polynomial, okay? I know that it's going to be positive out here. I know it's going to be negative out here, okay? Right, because the leading term is x cubed. I know it's got to look like that. These are the only places where the sign can possibly change, right? These are the only places where we might be crossing the x-axis, the only places where we might be changing from positive to negative. So this is either negative or positive in between. How do we decide? Well, one way we could do it is we just plug in something in between, like 0, and say, what do I get? Well, I get minus 1 times 4. That's negative. Okay. So I know it's negative in between. The other way to see it is to realize that because this term is squared, right, this will never be negative. You won't get a sign change at minus 2 because this can't be negative. This term, which has an odd power, that's going to change sign to 0, right? So we know we get a sign change at 1, but not at minus 2. So we get this sort of sign diagram. So what this tells me is that I should be crossing at 1, and now I maybe get rid of this because it might be hard to connect things up. So I want something that is going to cross. It's going to cross at 1. The other thing, and by the way, the other thing I can get is I can get that y-intercept, right? These are my two x-intercepts. What's the y-intercept? We work that out. When x is 0, it's at minus 4, so it's down here, right? So I know that it's going to go up like that. And I know it's got to come back up there. The one thing I don't know is I don't know exactly when that's going to turn it around. That's where calculus would come into the picture. Calculus will let us find the exact location of where this thing bottoms out. It's got to hit a bottom and it's got to come back up, right? It's got to come back up because it's got to hit that root at 2. Okay? But I don't cross at 2, right? Because this thing doesn't change sign, right? I have to be negative on both sides. So I just come and I kiss the axis and I come back down, right? And I've got most of my graph. The one detail I'm missing is here, right? So I need a bit of calculus to figure out exactly what's going on there. But you can apply these basic principles even once you're doing these, like you're doing curve sketching, you're in your calculus course, you're trying to figure out what the graph of some polynomial looks like, you're lost in derivatives and second derivatives and intervals of increase and decrease and concavity and all of this. Remember that you can get most of your polynomial graph just by finding the roots, if you can, looking at the leading term to get the end behavior, and all that calculus is going to do for you is fill in a few details in the middle that you can't quite get just by looking at the zeros and the leading term. Okay, so we've got our rational expression here. We talked about how to factor, simplify, determine domain, if we're thinking of it as a function. There are two different things that can go wrong as far as points that are left out of the domain in a rational expression or function like this. Okay, this 0 here, right? There was a 0 in the denominator, but I canceled it with a 0 in the numerator, and now it's gone. There's no longer, right? So once I simplify, there's no longer a 0 in the denominator when x equals 0. These sort of zeros in the denominator that you can cancel, these produce just simply a hole in the graph, if you think about the graph of your function, okay? So, we had this 0 over 0 thing, but once you cancel it, right, now I could plug in x equals 0, and in fact, I get, well, it almost looks like an intercept, except it's not quite an intercept because it's a hole, okay? What about at 2? Well, any 0 in the denominator that does not cancel with a 0 in the numerator, this produces what's called a vertical asymptote. Okay? So that's information that you can get out of the factored form for your rational expression as long as you keep track of the fact that, oh, there was that x that I canceled, right? We kept track of that. As long as you made that note, you have this information. The other thing that we know is that there is an x intercept, right? When x is equal to -1, y is equal to 0, right? So if we're thinking about graphing, we know that our graph crosses the y-axis, or crosses the x-axis rather, at -1, okay? At 0, so well, at 0, 0, we would have an intercept there. It would be both the x and the y intercept, except our original expression was not defined at 0, right? So instead of getting an intercept there, that's where we have this hole, okay? So we can get that information. There's one more piece of information that you can look for in a rational function, which is there's a second type of asymptote, right? Rational functions, they have both vertical and sometimes horizontal asymptotes, right? They don't always have vertical asymptotes because I could have like an irreducible quadratic in the denominator, let's say, right? Something that has no zeros. That could happen. This one does not have a horizontal asymptote. We'll do another example where there is one, and we'll talk about how the way you figure that out is you look up here. So what you can do is you can also, again, you can ask about, well, what's the end behavior? What happens when the absolute value of x is big? So when the absolute value of x is big, our function behaves roughly like, well, what happens is when the absolute value of x is big enough, you can ignore the lower order terms. They're not so important. You keep the top degree terms on the top and the bottom. And so you have x cubed over 4x squared. And again, we're thinking big absolute value of x here. So we're away from 0, so we don't worry about the fact that this is undefined at 0. If we simplify, This is just x over 4, right? So that tells us that the graph of this thing, once x gets big enough, it's going to look more or less like just simply the line y equals x over 4, okay? In general, when you want to know what's happening, for large values of x, this is what you do, right? You just look at the top powers. In this case, the degree of the polynomial in the numerator was greater than the degree of the polynomial in the denominator. If the degree in the numerator is less than or equal to the one in the denominator, you're going to have a horizontal asymptote. So it doesn't happen here, but it will happen in other situations. Okay? So all of this is information that you can extract just by sort of looking at the function, right? Again, we haven't done any calculus, anything like that. All we did was, well, we did one estimate by thinking about what happens when x is really big, and we did a bit of factoring. Okay? So we're going to take that information in the next video, and we're going to see how to put all this together and get some rough idea of what the graph of this thing might look like. Okay, so here's another example with a rational function where we're going to try to get out all the information that we can and see if we can draw a graph. So one of the things we might do before we even try to factor is say, well, when the absolute value of x is really big, this thing is approximately x squared over 2x squared, which is just 1/2, right? So that value there, that 1/2, this is a horizontal asymptote. Okay, so y equals 1/2. That's a horizontal asymptote. For vertical asymptotes, we need to factor. So we say, okay, top is the difference of squares. X minus 1, x plus 1. Bottom, x is a common factor. Actually, 2x is a common factor. So take out the 2x, we're left with x minus 2. Okay? So right away from here, we can see that x cannot equal to 0, and it cannot equal to 2. So that means that x equals 2 and x equals 0. These are vertical asymptotes. Okay? Right, neither of these zeros in the denominator cancels with something in the numerator. Okay, so we know that those have to be vertical asymptotes. We also know that that 1, 0 and minus 1, 0, these are x-intercepts, right? Those are places where the graph is going to cross the x-axis, because if x is plus or minus 1, y is going to be 0. Okay? There is no y-intercept because we can't put x equal to 0. There's a vertical asymptote there, right? So the y-axis is actually an asymptote in this case. Okay? So this is pretty much all the information that you can extract without doing calculus or anything like that. So at this point, let's see what the graph looks like. Let's draw some axes. Let's draw some asymptotes. So we have, so here is, say, 1. All right, so at 1/2, we've got that horizontal asymptote. Okay? The y-axis doubles as a vertical asymptote. So does x equals 2. So x equals 2 is a vertical asymptote. I know I have intercepts at 1 and at minus 1. Okay? So I have all that information. So the other thing I probably want to do is I probably want to look at the sign diagram. Okay, so we'll draw our number line. We're going to mark off intercepts at -1 and at +1, asymptotes at 0 and at 2. Once you've done enough of these, you start getting the hang of the fact that if none of the factors are even powers, then you're going to get a sign change at every single one of these points that you've marked off. So you really only have to test kind of out past 2, try say x equals 3. You see, okay, everything is positive. So we expect that we're going to get something that looks like that. Okay? So this is useful because it tells me what's going on at the 2 vertical asymptotes. It tells me that I've got to head down to -infinity on the left of 0, up to +infinity on the right, and same sort of thing at 2. Okay, I know I've got that going on. The one thing that I don't quite get from the sign diagram, and I may not be able to determine exactly, is am I going to approach this horizontal asymptote from above or from below on either sides? That's a little bit trickier to work out. But we have this bit of information here. So what we know is that we have to kind of head down to that vertical asymptote there. We have to pass through 1. We have to head up there. So it seems like the most likely scenario is going to be something like that, right? Okay. Probably looks like that in between. There's some possibility, well, not really. I think, that it could kind of go down and then back up, but I mean, we'd need to look at the derivative to rule that out, but chances are it looks something like that, okay? Now, here, I'm just coming down. Now, I know I don't cross the x-axis again because there is another intercept. So most likely, I'm going to come down and just approach that horizontal asymptote. Again, there's some small possibility that I dip down just below the horizontal asymptote and come back up. Calculus would tell me whether or not that would happen, because if that happened, there would have to be a minimum value. I would find that using calculus. Notice, by the way, you are allowed to cross horizontal asymptotes. Vertical asymptotes you can't cross because those x values are not in your domain. There's nothing stopping you from going across a horizontal asymptote. Okay, so the last one is -1. So now the only thing here is I know I've got to come up, I've got to pass through that intercept. And now the question is, do I go up, come down, and go like that? Or do I come up and just kind of go like that, right? I don't know which of those two possibilities it is. Again, that's where calculus would come into the picture. Taking the derivative would tell me that. Which one of those two is it going to be? I don't know yet, right? We won't know until we move on, we do a bit of calculus, we learn how to deal with that. But again, a lot of the shape you can work out, right? You can get some idea of the shape just by looking at the function, by factoring, looking at the sign diagram, looking for asymptotes, intercepts. You can get a pretty rough idea of the graph. In fact, if I really wanted to figure out what was happening here, I could probably just try, a couple of large x values and see, is the y value bigger or smaller than 1/2 when x is really big, right? That's one way that I could do it. If I find that things are a little bit less than 1/2, chances are it's the yellow curve. If I find that things are a little bit bigger than 1/2, chances are it's the pink curve, right? So I could figure that out if I had to. Okay, so we introduced the notion of a graph in the previous video. I left the definition up here on the board, right? So if somebody hands you a function, right, you can look at all the ordered pairs. AB, where A belongs to A, B belongs to B, right? All the ordered pairs where B is associated with A through the function, right? And sometimes this graph is not something that you can necessarily plot, right? If A and B are not sets of numbers, you can still talk about the graph even though you can't necessarily draw it. If A and B are sets of numbers, then you can visualize the graph using this idea of the Cartesian plane, right? So for this example here, right? Here's an example where I would just plot the points, and that's going to tell you what the graph is, right? So if I want f of 1 to be 3, so I go x is 1, right? This is my x-axis. This is my y-axis, or A and B if you like, and I plot a point at the coordinates 1, 3. F of 2 equals 2, so I go 2, 2, and I plot a point there, okay? F of 3 equals 3, so I go back up to 3 for my y value, and I plot a point. And f of 4 is equal to minus 1, so I plot a point down there, and I have my graph, right? It's not very exciting, but that's the graph. And this is indeed the graph of a function, right? Again, the way I would know that this was not a function is if there was more than one y value for one of these x values, right? So if I plotted another point, say here, at maybe 1, 1, or at 1 minus 1 down here, or at 1, 2, I would no longer have a function, right? Again, it's okay to have two x values that both go to the same y value. I just can't have two y values associated to a single x value. Okay? So that's a function. With that in mind, we can come to these sorts of plots that are more like what you might see in a calculus course, and you can ask, okay, which of these are graphs? And so one of the things you probably learned in high school is that the thing that distinguishes a function from all other similar types of objects, or all of the curves, if you like, if you think in terms of the graphs, is that the graph of a function passes this so-called vertical straight line test, right? So the idea is that if you draw a vertical line, it should only cut the graph once, right? So no matter where on the graph you go, you draw a vertical line and it only cuts once. There's this notation convention we use for graphs. If I fill in a point, it's included on the graph. If I leave it hollow, it's not included. So here, I draw that vertical line down, right, passing through those 2 points. And that still only cuts the graph once because that point is not included, right? So this one would be a graph. This one here clearly is not, because if I draw a vertical line here, I see that I cut it in 2 places, so it fails that test, right? Even though this graph comes in 2 pieces that are not connected, right? Standard example that people usually give for a curve that is not a graph of a function is a circle, right? Circle fails this vertical line test. But in fact, if I had even one sort of extraneous point, if I plotted a point here and said, oh, that's part of the graph as well, this point and the curve, I'm not dealing with a function, right? Something like this. So this one is not. This one down here, also not a function. At least if all of this is supposed to be 2 parts of a single graph, it's not a function, right? Because even though this part here looks like a line, lines are fine, lines are graphs of functions. This bit here, again, it fails the test. So we don't have a function, right? Maybe I could have modified this one so that I only include, say, the top half of this parabola, not the bottom half. Then maybe this is a little bit ambiguous because you'd then have to start wondering, like, oh, does this line keep going? Because if it keeps going, eventually it's going to overlap that, and again, I wouldn't have a function. So sometimes, the picture that you draw, the graph might be an incomplete picture, right? Maybe it's not telling you everything you need to know about the function. You might have to go back to the formula, right, to know for sure whether you're dealing with a function. But But the way to know whether or not you're dealing with a function is really just, you look at the formula, you look at the graph, you look at whatever information you have that's defining your function, and you ask yourself, is there any input, is there any element of the domain for which I can get more than one output? If there is, you don't have a function. Okay, so in this video we're going to look at some common graphs that we might encounter, okay? Just to give us an idea, right? And basically, the principle is you start with the simple examples and you learn how to build up from them to more complicated ones. So common graphs. Well, we have lines, right? So one of the ways you often see lines written, y equals mx plus b, this slope-intercept form, right? So the graph of the line tends to look something like this. Right? This point here, the b, right, is that y-intercept, right? The place where it crosses the y-axis. M, the slope, rise over run. And again, with graphs of lines, right, visually you can pretty easily tell a line with positive slope apart from a line with negative slope, or a line with zero slope, which is just a horizontal line, right? But from the graph, you probably can't look at it and read off the exact value for the slope. For that, you're going to have to either get a couple of points, calculate rise over run, or maybe you have the formula handy and you can look at that, right? So we have lines. We have basic quadratic, right? So this is a parabola opening upwards, vertex at 0, 0, something like that. Okay. We could go to the cubic. The graph of the cubic looks something like this. Starts down here, comes up, flattens out as it goes through the origin, and then it heads up. Okay, with the cubic. And then other power functions, integer power functions, tend to look like variations on these. You could also look at, say, root functions. So we could look at, say, y equals the square root of x. Now, of course, here there's a domain issue, right? This is only defined when x is bigger than or equal to 0. So we can't plot it for negative x. For x bigger than or equal to 0, it looks like this. In fact, that root function is just 1/2 of a parabola, but turned on its side, right? And again, this is related to this inverse relationship, right? The square root is sort of a partial inverse for the squaring function, and this is one of these places where domain does come into play, right? This function here, if you set the domain to be all real numbers, does not have an inverse. But if you were to restrict this to only x bigger than or equal to 0 for inputs, so you only took this half of the parabola, then this graph and that graph, they would be inverses of each other. We probably won't deal with inverse functions in the review. I think this is something we'll probably leave until we get through a bit of calculus and we want to talk about derivatives for inverse functions. We'll deal with inverses when we come to them. Okay, so we have some of these basic algebraic functions. I guess maybe one more we could put in here before we move on. Might be this basic hyperbola, y equals 1 over x. Which looks something like this. Has two pieces. Okay. And it has both horizontal and vertical asymptotes. This is sort of it's both a good and a bad example. It's good in that it has some interesting behavior that you don't encounter with things like power functions. The bad thing about this example is that some people will, if you spend too much time on this, some people will kind of get the impression that whenever you have asymptotes, they're always the axes. This is not always the case, right? A horizontal asymptote could be any horizontal line. A vertical asymptote could be any vertical line. When we get to graphs of rational functions, that's something that we're going to encounter. Okay. Other functions that you will encounter in this course. There are the trig functions. Maybe I shouldn't try to do all the trig functions. Let's do sine. So sine is this function which oscillates between -1 and 1. So this is an interesting property that we don't see with any of the ones over here, right? With all of these graphs, the y value tends to either increase or decrease with the x value. And it tends to be that the y value will get arbitrarily large if you go out far enough one way or the other. For a sine function, the y value is always between -1 and 1. So you get a curve which just goes back and forth forever. And it repeats itself. What's also interesting, and this is true of all the trigonometric functions, the sine function is what's called periodic. The graph repeats. Once you know the graph from, say, we could go from let's say from minus pi all the way to pi. This is minus pi over 2. That's pi over 2. Once you know that bit of the graph for the sine function, you can just copy paste to get the graph of the sine function for all other values of x, which again is not something that you see with any of these over here. And so we could get into cosine, tangent, cotangent. We could get into all the trig functions, but we'll probably deal with that when we go over trigonometry. Another one. The exponential function. I'm going to do e to the x, but you can do other bases as well. Okay. So the graph of y equals e to the x looks something like that. Okay. The intercept is 0, 1, right? Because anything to the power of 0 equal to 1. So pretty much, I've done this for base e, but for any base bigger than 1, this is what your exponential graph is going to look like. If the base is between 0 and 1, it's going to go the other way. Okay, but it's something which grows very rapidly towards infinity as x gets big and positive, and it slowly decreases towards 0 as you feed in negative values for x. And the last sort of common function, whose graph you should know, is the natural log. And the natural log is the inverse of the exponential function. And again, if you're doing a log to another base, the graph is going to look the same, just kind of stretched a little bit, stretched or shrunk. So because of the inverse relationship between these two functions, the y-intercept for the exponential function, we flip the coordinates and we get an x-intercept for the natural log. This horizontal asymptote becomes a vertical asymptote, and we get something which looks like that. Okay? And again, the natural log has this domain issue. It's only defined for positive numbers. It's undefined if x is 0 or negative, so we only get a piece of the graph that looks like that. If you wanted to do the absolute value of x, and actually we should throw the absolute value function in there. If you do the natural log of the absolute value of x, then you get sort of a mirror image on that side, right? You get that piece and you get that piece, okay? If we want to just plain old y equals absolute value x, let's squeeze that in right here in the middle. The absolute value function has this sort of V shape, right? When x is bigger than 0, it's just the line y equals x, so it's just a straight line going up like that. When x is less than 0, y equals minus x, so it's a line with negative slope. You get this V shape. The absolute value is interesting. It's an interesting function. It's kind of the simplest example that most people come up with for a function which is continuous at every point, once we define what it means for a function to be continuous, but does have a point where it does not have a derivative, right? At the origin, there's no well-defined slope for that function because the slope abruptly changes from -1 to +1. Okay, so these are some of your common graphs that you're going to encounter throughout the course. In the next video, we'll talk a little bit about how to take some of these basic graphs and turn them into things that are slightly more complicated. All right, so in the last video, we looked at some of the basic graphs. I left a couple of them up here on the board, right? Basic parabola. This one is also a parabola. Coming from the root function. It just happens to be half of a parabola opening horizontally rather than vertically. There are a number of basic transformations that you can apply to graphs, and you can, of course, you can consider these in combination. So you can start with a simple graph, and you can apply some number of these in sequence to produce a new graph, right? So one of the things that you will notice if you kind of compare what's going on, right? I've given sort of what happens to the function in each case. You'll notice that for horizontal effects, you're applying something inside the function, right? You're subtracting a number from x. You're multiplying x by a number. You're putting a minus sign in front of x. For vertical transformations, it happens outside the function, right? You do f of x and then you add b. You do f of x and then you multiply. You do f of x and then you apply the minus sign, okay? So horizontal is inside, vertical tends to be outside. So the translations, if a is a positive number, something like x minus 3, for example, that's a shift to the right. If a is negative, you're shifting to the left. If it's a stretch, you want to look at, so let's focus on a bigger than 0. You want to compare if a is between 0 and 1, or is it bigger than 1, okay? If a is between 0 and 1, then what tends to happen is you stretch it out like this. If it's bigger than 1, you kind of squeeze it in, okay? Reflection, if you put the minus sign in there, you're reflecting across the y-axis, okay? And then same idea for vertical translation, you're shifting up or down. For the stretch, if b is bigger than 1, you're making it bigger. If it's smaller than 1, you're squishing it down. And reflection, you're reflecting across the x-axis. So for example, if I did something like y equals x minus a, well, let's put a value in, x minus 9 squared, and I plotted that, what I would do is I would take my usual parabola and I would go 9 units out and I would draw the graph there. I'm going off the screen, but that's okay, you get the idea. So you just take the usual graph and you'd slide it over, right? If I did something like y equals, now here's one where maybe you got to be a little bit careful with the stretches, because let's say we do something like 2x squared. So this is one of these kind of odd situations where a horizontal stretch kind of becomes a vertical stretch, because you square the 2, you get 4x squared, right? So it'd be similar to if you just took the x squared and multiplied by 4. But what tends to happen in this case is you kind of get the same graph, but now it's kind of narrower, right? That horizontal stretch, it kind of took this and it squished it in a little bit to get a narrower version of the original graph. Now, if I do f of minus x for x squared, nothing happens, right? Because you square minus x, you get x squared. This happens to be an example of what's called an even function. F of minus x is the same as f of x. So you don't see any effect in this case from a horizontal reflection, right? Reflecting that across the y-axis, nothing happens. But I could do, if I use the root function instead, if I did say y equals the square root of negative x, well, now I can't use any positive inputs because the minus sign out front makes it negative. I have to use negative inputs. And what I get in this case is something that looks like that, right? It goes the other way now instead. If I wanted to, in this example here, maybe we do another example. If I did something like y is the square root of x plus 1, well, that's going to take my usual square root function, shift it 1 unit to the left, and give me something going up like that, right? And for the vertical translations, I could do something like, I could do y is equal to, say, x squared minus 1, or I could do y is equal to, let's say, root of x plus 2. And if I were to plot those, this one, I'm taking the regular parabola and I'm shifting it down by 1 unit. So I get something like that. I'm taking the square root and I'm shifting it up by 2 units. So I get something like that, right? Starting at 2. So with some basic translations, stretches, reflections, you can start with some basic graphs. You can turn them into new graphs. And of course, you could do combinations of these. So I could do something like this. I could do something like y equals 2 times x plus 1 squared minus 3, right? So this is now several transformations all in one. In fact, let's even do minus 2. So what would I get if I had that? Well, I would start with my basic parabola, my basic squaring function. The plus 1 shifts me 1 unit to the left. The 2 is going to stretch it by a factor of 2. The minus sign is going to flip it over. And then that minus 3 is going to shift everything down by 3 units. So if I were to plot that, let's say, over here, so now my vertex moves over, right? It's going to move over 1 unit, right? And then it's going to move down by 3 units. And I would get something like that if I were to plot that function, right? So if you understand the effects of these basic transformations and you know some basic graphs, then somebody can hand you a complicated function like this, or looks a little bit more complicated, and you still know how to plot it without having to do any calculus or really all that much work, other than knowing some basic examples and knowing what happens when you apply these transformations, what the effect of those transformations are on the graph. Okay, so we're going to look briefly at the graphs for the 6 trig functions. Primarily sine and cosine. We'll try to get tan done, maybe cotan. We'll see how we do at secant and cosecant. To be honest, if you don't remember what those graphs look like, it's probably not going to affect you in any way. But let's start with sine. So we know that sine has zeros. at all the multiples of pi, right? We know that it hits its maximum value at pi over 2, right? Sine of pi over 2 is 1, right? At 3 pi over 2, it's down at minus 1. Same thing at minus pi over 2. Minus 3 pi over 2, it's back up at 1. Okay? And the sine graph is often referred to as a sine wave. It sort of gently oscillates back and forth between these values. So you get something that looks sort of like this. Okay, and then that graph just keeps repeating forever. So it just keeps oscillating up and down. Okay, so this is the graph y equals sine x. Okay, if we're taking this as our x-axis and this as our y-axis, right? On the same set of axes, we can plot cos, right? So cos has its zeros at the odd multiples of pi over 2 rather. Cos of 1, or cos of 0 rather, is equal to 1. Cos of pi is negative 1. At 2 pi, we're back up to plus 1. At minus pi, cos is at negative 1. And at 2 pi, we're back up to plus 1. Okay? And the cosine graph goes in much the same as the sine graph. Okay? Like that. Okay? So that's y equal to cos x. Okay? In fact, one of the things you might notice is that the graph for cosine is just a translation of the graph for sine, right? The sine graph is just shifted over by pi over 2. And that's no coincidence, right? So one of the things that you'll notice is that sine of x is the same thing as cos of x minus pi over 2, right? So that's one of the things that you might notice, right? So when x is equal to 0, right, cosine is equal to 0. When x is equal to pi over 2, we're at 1. Yeah, so that works out. Okay, so you do have this kind of translation property between the two of them. We have this relationship. All right. Now let's look at tan theta. So tan theta, we notice that there are these gaps in the domain, right? And I mentioned that those gaps are vertical asymptotes. So for tan, first thing we have to do if we're going to plot tan is we got to mark off those vertical asymptotes. Okay? Okay, so there are those asymptotes for tan. Zeros at the integer multiples of pi. Okay, and the other thing you got to work out is which way is tan going on either side of those asymptotes. And so we know that it's positive in the first quadrant. You can work out that it's negative here in the fourth quadrant. And in fact, what you're going to get is that it looks something like this. So from minus pi over 2 to pi over 2, you get something that looks like that. And then this graph just repeats. Okay? Okay. So that's what the graph looks like for the tan function. Okay. For cotangent, you're going to get a graph that's similar, but because you're flipping things over, the asymptotes and the zeros, those are going to trade roles, right? So now you're going to have asymptotes at multiples of pi. You're going to have zeros in between. And I think maybe just to keep this video from getting overly long, we'll skip graphing cotan. If you're curious, you can always pull up, GeoGebra or Desmos or any online graphing calculator and just fire it in and see what it looks like. And you'll see that it is, again, very similar to the graph for tan. Now, for secant and for cosecant, let's take a look at secant, let's say, and then again, for cosecant, because of this relationship between sine and cosine, there's a corresponding relationship between secant and cosecant. So if I'm doing secant, let's say, so one of the things I want to do if I'm doing secant is I want to notice, first of all, there are going to be these asymptotes, again, because I'm dividing by cos. Okay, right? There are no zeros. There are no zeros. Secant is always bigger than or equal to 1 in absolute value. Okay, so what you're going to get is you get a point here. Okay, so when cosine is equal to 1, secant is equal to 1 over 1, and then as we approach those asymptotes, cos gets closer to 0, and so it's going to head up to infinity because you're dividing by 0. Okay. Then over at 3 pi over 2, you're at minus 1, and it heads down. Then at 2 pi, you're going up. Okay. And same thing here. Down. Then up. Okay, so you get a graph that looks something like that. So this would be y equals secant x. I guess I forgot to label this one. This is y equals tan x. Okay. Another thing that you might notice, worth pointing out, cosine and secant are even functions, right? The graph to the left of the x-axis is just the mirror image of the graph on the right, right? You can reflect across. If you do this reflection like that, nothing happens. The other four are all odd functions. So if you reflect, so if you take, say, the graph of sine, if you reflect across and then you flip, so if you reflect across both axes, you will get the same thing, right? So you'll see that things are kind of opposite on either side, right? Here they're the same. Here one's above, one's below. But you have these mirroring properties for these. So those will come in handy. Those properties might come in handy for various problems that you're trying to solve. It's quite frequently useful to be able to remember that cos of minus x is the same thing as cos x, and that sine of minus x is, in fact, minus sine x. These, if you want, you can take these as identities, and they're the first of several identities that you might need to use in your calculus course. And we'll look at a few more in the next video. Okay, so we're going to start a review of trigonometry with right triangle trigonometry. So this is usually where people start. It's sort of the simpler way of looking at things, looking at right-angled triangles. And so you probably have seen definitions of trigonometric functions as ratios of the size of this triangle, right? So typically what you see is you see things like, for that given angle there, that interior angle, you see things like sine of theta. And sine of theta is given as the ratio of the side opposite the angle over the long side, which is called the hypotenuse, right? So this C is your hypotenuse. Okay. Cosine is the adjacent side, A, over the hypotenuse. So it's the ratio A over C. And there's also tangent, tan theta. And tan theta is the ratio of the opposite side over the adjacent side. And one of the things that you'll notice is that's the same as doing sine theta divided by cos theta. Okay? Those are the three basic trigonometric functions. Okay? But there's one other character that usually comes into the play, and that's Pythagoras. So we have the Pythagorean theorem. And the Pythagorean theorem is the statement that a squared plus b squared has to equal c squared. Okay? That's the Pythagorean theorem. And there are lots of so-called Pythagorean triples, examples of integer values for a, b, and c that fit this equation. The most commonly known one is your 3, 4, 5 triangle, right? So 3 squared plus 4 squared is 9 plus 16, which gives you 25, which is 5 squared. Some of you may have heard of Fermat's last theorem, which says that if you go for any higher integer powers here, cubes or greater, it's impossible to find integer solutions to this equation. So something special about the second power. Pythagorean theorem, there are lots of examples of these triples of integers that fit the equation, which is interesting. But of course, most of the time, if you choose two integer values, let's say you choose integer values for a and b, chances are c is not going to be an integer. It's probably not even going to be rational. It's going to be some square root. This was apparently something that was a little bit troubling for the Greeks, who really wanted to believe that everything could be expressed in terms of integers and ratios of integers. One way to think about the Pythagorean theorem, you can think of it as a relationship between areas, between the area of a square of side length b, a square of side length a. If you add up the area of those two squares, you should get the area of a square with side length c. Okay, and if you're curious about this sort of thing, you can do a little bit of poking around online. You can look for various proofs of the Pythagorean theorem. These sort of traditional proof, I'm not going to get into the details of the proof, but if you're at all curious, I think one of the ways that you would prove it is you would, from this corner here, you would drop a perpendicular onto the hypotenuse, and then you would make some arguments involving similar triangles. And so, in fact, this small triangle is indeed similar to the original big triangle. And with a bit of playing around and using the fact that for similar triangles, side lengths have to be in proportion, you can derive the Pythagorean theorem. Our point here is not to try and derive the theorem. If you're curious, there are lots of sites online that'll do it for you. But one thing that we should mention before we move on is that the Pythagorean theorem is quite important for analytic geometry, right? For working on the Cartesian plane and translating equations into graphs, the Pythagorean theorem is quite essential because the Pythagorean theorem gives us a notion of distance. So if you have 2 points in the plane, so let's say you have a point here, x1, y1, and somewhere else you have a point x2, y2, right? And you want to know how far it is from point 1 to point 2, point A to point B. You want to know that distance. Well, you can construct a little right-angled triangle where this side, so we put in that side, right? There's our length. This side length here, delta x, is x2 minus x1. This side length here, delta y, y2 minus y1, right? And the Pythagorean theorem says that if you're interested in this distance d, that d squared should be delta x squared plus delta y squared. And so this gives you this familiar distance formula that you probably saw in high school, that you take x2 minus x1, you square it, you take y2 minus y1, you square it, add those together, take the square root, and that gives you the distance. Okay? So that's where that distance formula comes from. The distance formula comes from this Pythagorean theorem, which is really a statement about triangles. Now, interestingly enough, the distance formula comes from kind of understanding triangles. Sine, cos, tan, they're all defined in terms of these side length ratios from triangles. Despite that, we're now going to pretty much forget about triangles, and we're going to move on, and we're going to Okay, so in the last video we introduced trigonometric functions in terms of ratios of side lengths for a right-angled triangle, and that's typically where most people first learn about the trigonometric functions. And of course these come up frequently. They're useful in a lot of applications, used constantly in things like surveying, right? Mathematically, we tend to not really think so much in terms of triangles as we do in terms of circles, and in particular this unit circle. So the unit circle is a set of all points in the xy plane that have length or distance 1 from the origin, from 0, 0. Thanks to the Pythagorean theorem, thanks to the distance formula, right, we know that our delta x is just x, our delta y is just y. We want d to be 1. And so we get a formula for this unit circle, right? So the unit circle is a set of all points in the plane satisfying this equation, x squared plus y squared is equal to 1, okay? And this angle theta that we see here is the angle between this radius that I've drawn and the positive x-axis. Okay, so we can maybe pencil that in. Okay, so it's that angle. Now, you'll probably notice that just like we had here, there is a right-angled triangle hiding in this picture if we drop this perpendicular down. All right. So there's a right-angled triangle sitting there. This side has length x. This side has length y. And so if you refer back to how we define sine, cos, tan in this context here, sine and cosine in particular, as these ratios of side lengths, well, then right away you can see that x is going to be, well, x is the adjacent side, right? Adjacent over hypotenuse, which is just 1. So x over 1 is cos theta. Y, opposite over hypotenuse, is sine theta, right? Now, you can think of those as consequences of the right-angled triangle definition, but in fact, when we're doing calculus, we take these as definitions. So So from the mathematical point of view, this is the definition for sine and cosine as functions, okay? As functions of this angle theta. Now, there's one thing that we have to add, okay? Sort of an important thing. Theta, whenever we're doing calculus, theta must be measured in radians. So this is important. You might be used to measuring angles in degrees, and degrees are convenient for certain things, surveying perhaps. They're nice when you're doing right-angled triangle trigonometry. But if you want to do calculus, you have to work in radians. And one of the reasons that we want to work in radians is that if you work with radians, it means that you can treat theta as a real number. Now, why? It's still an angle. How do you get to treat theta as a real number? Well, the reason is that for any angle theta that you pick, there's going to be, starting here at the point 1, 0, there's going to be a little segment of the circle starting at 1, 0 and ending at this point, right? Like so. Let's call that S. Okay? So S is this little sort of segment, this arc. Okay? So one of the basic formulas that you have from sort of circle geometry is that as long as you're working in radians, that length S is just, it's the radius times the angle. So S is R times theta. Okay? And because we're on the unit circle, R is just 1. Okay? So S equals theta. So that means that every angle gets identified with a length. Lengths are measured in using real numbers. So what that means is that these quantities here, sine theta, cos theta, which were given before as ratios of lengths, we can now treat them as, well, I mean, they were already always numbers. But theta was this, it was measured in degrees, right? So we don't, you know, when we're measuring theta in degrees or even in radians, we're thinking of it as an angle, not as a number, right? But this gives us an identification that every angle produces a number, right? And in terms of the quantity, they're equal. So now we can think of these as functions. We can think of the sine and cosine as functions, and functions of a real variable, just like we have exponential functions and logarithms and polynomial functions. These are now functions of a real variable, so we can do calculus with them. That's kind of the whole point of moving to the unit circle is now we have functions of a real variable, right? We think of theta as a real number. We'll find later on, once we get into doing calculus, once we start talking about limits, derivatives, things like that, if we want any of the formulas that we derive to work out, we definitely need to be working in radians. If you work in degrees, you're going to be off by a factor of like pi over 180, something like that. Okay? So it's essential that you view theta as measured in radians. The other kind of nice thing that happens now is there's a lot more freedom in terms of angles that you can choose. In fact, theta is going to be a real number, and we could in fact say it can be any real number. This is a surprising thing, right? If you're here working with a right-angled triangle, then theta, if you're measuring in degrees, it's got to be somewhere between 0 and 90 degrees, right? It has to be an acute angle in this context, right? Or if you're working in radians, somewhere between 0 and pi over 2, let's say, okay? So, but now you're not limited to acute angles, right? You can let this point go anywhere on the circle, and so you can still define sine and cosine for points, right? So sort of your first quadrant angles, those are the ones that correspond to right-angled trig. But there's nothing stopping me from putting a point, let's say, out here, right? Drawing that line, my angle now goes around all the way around like that. That's my theta. But I still get a point on that circle. That point still has x and y coordinates. I'm in the third quadrant now, so they're both negative. But I can still assign those values, right? I can still figure out what the x coordinate is. That's still going to be cos theta. The y coordinate, that's still going to be sine theta, right? And in fact, I can even go around more than once. I can go 10 times around the circle, right? That's going to define an angle. I can figure out what cos of that angle and sine of that angle is. I can also go clockwise rather than counterclockwise. I can go the other way around the circle. I can get negative angles, right? So now you have a lot more freedom in the sorts of angles that you can consider. You can still define sine and cosine for those angles, right? Now for any real number angle, not just for angles measured in degrees between 0 and 90. All right, so let's dig a little bit more into this radian measure, just to go through the details there in case you're not too familiar with how do you measure angles in radians. The key is to remember that radians are defined so that this arc length formula works, right? So that the length of a sector of a circle is just the angle that is spanned by that sector times the radius. And since we're working with a radius of 1, right, that means that a given length, a given segment of the circle is just equal to the angle that's spanned. So that means that 1 revolution in radians is equal to the circumference. Okay? And we know that circumference is given by 2 pi times the radius, and our radius is 1. So the circumference is 2 pi. Okay? So that means that 1 revolution is 2 pi radians, which is, as we know, 360 degrees. Okay? So all the way around, starting here, so by default 0 is when we measure angles from the positive x-axis. So here we're at 0. 1 trip around, we've gone through 2 pi radians. So that means that at half a trip around, we've gone pi. Okay? Pi radians. Okay? A quarter trip is half of that. So half of pi is pi over 2. Right? And so we started at 0. If we go all the way around, we're at 2 pi. Right? 3/4 of a trip, 3/4 of 2 pi is going to be 3 pi over 2. Then you get to 2 pi. And then you can subdivide further, right? So what you might have referred to as a 45-degree angle is now, well, it's half of a right angle, so pi over 4. Okay? So this is a 90-degree angle, right? So a third of that, a 30-degree angle, would be, we divide that by 3, we get pi over 6. So pi over 6 is going to be somewhere around here. Okay. On the other side, you have pi over 3. In degrees, that would be a 60-degree angle, right? So we have 30, 45, 60, 90, right? And now you can keep going around the circle. So here, you're going to have 2 2 pi over 3, also known as 120 degrees, right? Then, 3 pi over 4, then 5 pi over 6, right? And then down to pi. And you can continue those all the way down. We can go the other direction here. So extend these to diameters. Like so. 7 pi over 6. This is going to be 5 pi over 4. This is going to be 4 pi over 3. 3 pi over 2. This is 5 pi over 3. 7 pi over 4. And finally, 11 pi over 6, right? That completes your unit circle. Right. Now, of course, there are lots of other angles that you could mark. The reason that I've gone with these ones is that these are the angles for which we can compute exact values for the sine and cosine functions, right? At least the ones that we can easily compute exact values for. A lot of people get concerned because we've marked so many angles around the circle that, you know, oh my God, I'm going to have to memorize all these things. It's not so bad. The only ones you really have to remember are the first quadrant angles. And this is one of the nice things about working with radian measure, okay, is that if you look at the denominators, it's going to tell you what is kind of the corresponding first quadrant angle, right? So if somebody hands me like 7 pi over 6, right? I say, okay, 7 pi over 6. Well, I see a 6 on the bottom. So the angle in the first quadrant that matches it is pi over 6. Or if I see like 7 pi over 4 or 3 pi over 4, right? These ones with 4s on the bottom, they correspond to pi over 4. And it turns out that once you know the coordinates for these ones, the other points are just reflections, right? So this point for 7 pi over 6, right, it's opposite that one. So if I know the coordinates for this point, I know that in quadrant 3, I change the sign on both coordinates, right? Both coordinates are negative down here. So if I know that point, I just put minus signs in front of the two coordinates, and now I have that one, right? Same thing for all these ones down here. I just take these ones, I put minus signs out front, right? If I'm in quadrant 4, I know that x is positive, y is negative. So again, I reflect across, right? If I have the pi over 3 one, switch the sign on the y coordinate, and I have the values for 5 pi over 3, right? So these are the basic ideas that you use, right? So you don't have to memorize the whole circle. You don't even have to remember, you know, these like cast rule or anything like that you might have learned. As long as you remember in each of the 4 quadrants which coordinates are positive, which are negative, and you remember these values, you can work things out for any of these points on the unit circle. The other thing that of course might come up is somebody gives you something like, I don't know, 31 pi over 6 and asks you to calculate sine or cosine of that angle. And you're like, well, 31, that's not on my circle. Like, what do I do with that, right? And so what you do is you have to kind of think in terms of 2 pi. So you have to say, so 2 pi would be, if I multiply by 6 over 6, that's 12 pi over 6, right? So this would be, I could do 12 pi over 6 plus 12 pi over 6. I'm up to 24, and then I'd need 7 pi over 6, right? So you can kind of break things down like that. So this is a full revolution, right? That's a 2 pi. That's a 2 pi. And so this angle is starting here, going once around, twice around, and then around to 7 pi over 6, right? So if you're dealing with angles that are outside that range from 0 to 2 pi, you just simply add or subtract multiples of 2 pi until you get something that's one of these, and then you can work out the answer. So in the next video, It will tell you what some of those coordinates are so that you can start assigning values to the sine and cosine functions. Okay, so in this video, we're going to try to derive values for sine and cosine for these special first quadrant angles, right? Now, there's a couple that we can get right away, because we know that for any point, right, for any point on the circle with coordinates, if this point has coordinates x and y, we know that x is cosine of my angle. We know that y is sine of the angle. That's how sine and cosine are defined, right? As the coordinates, where theta is this angle measured from the positive x-axis. All right, so when theta is equal to 0, we can see that we're at the point 1, 0. So that means that cosine of 0 is 1, sine of 0 is 0. When theta is equal to pi over 2, well, then you're at the point 0, 1, right? And so that means that cosine of pi over 2 is 0, and sine of pi over 2 is 1. And similarly to the other four intercepts, you can read off the answer, right? Cosine of pi is -1, sine of pi is 0, cosine of 3 pi over 2 is 0, sine of 3 pi over 2 is -1. And by the way, for these, the ones below the x-axis, a lot of people will tend to measure those going clockwise. So rather than 3 pi over 2, write it as minus pi over 2. You can do it that way as well. All right. Now, what about when theta is equal to pi over 4? Okay. Well, pi over 4 is right in the middle, right? It's this one that splits it in two. And so there's some symmetry there. You have the same amount on this side as you do on that side to say that in this case, x is equal to y. So we have a right-angled triangle, which is in fact an isosceles right-angled triangle, right? And we can work it out. I mean, the other way you know it's isosceles is that those two angles have to be the same, right? And we know that for triangles, the angles also influence the ratios of the sides. So if those two angles are the same, the side lengths have to be the same. We know that the hypotenuse has length 1. And we know from Pythagoras that x squared plus x squared, well, that has to give me 1. So that means that 2x squared has to give me 1, right? That means that x squared is 1/2. I'm in the first quadrant, so in the first quadrant, x and y are both positive, so I can take the positive square root. And that puts me at the point 1 over root 2, 1 over root 2. If you feel compelled to rationalize the denominator here, go right ahead. You could also write this as root 2 over 2. It really doesn't matter. Nobody in university is going to care if you rationalize your denominators. So I wouldn't worry that much about it. Cos pi over 4 is 1 over root 2. Sine of pi over 4 is 1 over root 2. In fact, one of the reasons that you have to rationalize your denominator, historically this was necessary because it used to be that you would calculate these values on as like a slide rule, pre-calculator days, and so you could work out what root 2 was on your slide rule, and then you could divide by 2, and that you could do, but you couldn't actually do 1 over root 2. That was not an operation that you could do. So everyone had to learn to rationalize their denominators. Now we have calculators. It's not really necessary anymore. Okay? So you can leave it like that. Now, pi over 6. So there's a trick with pi over 6, which is you take your triangle here, and you double it. So you put the mirror image down below. And one of the things you can work out is if this angle is pi over 6, that's a pi over 2, right? It's a right angle. You can work out that the remaining one has to be pi over 3, right? If you want to switch to degrees for a second, right? We know that the interior angles for a triangle have to add up to 180 degrees. If we have 90 and 30, the leftover one has to be 60 degrees, right? So if we reflect that across, symmetry says that this is also a 60-degree angle. And if you look at the big triangle, well, two 30-degree angles add up to a 60-degree angle. So this is an equilateral triangle, right? If all three angles are the same, all three sides are the same. And we know that this side has length 1. So that side has length 1. And that means that, again, because of symmetry, those two sides have length 1/2, because you take a side of length 1 and you're splitting it in 2. Okay? So now I know that my y-coordinate here is 1/2. And I know that x squared plus y squared has to equal 1. So x squared, so squaring a half gives me a quarter equals 1. So x squared, if I subtract a quarter from both sides, x squared is 3/4. So to take the square root, you take the square root top and bottom. Pi over 6 is at coordinates x is root 3 over 2. Y is 1/2. Okay? So that means that cos of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. Okay, very good. All right, so that's not so bad. The only one that's left over is pi over 3, but you can kind of use some symmetry here that if you can exchange roles, right? Or you can go back to your right triangle trig, right? For this angle, opposite and adjacent kind of switch roles, right? So sine and cosine switch roles. And so you can work out that the last angle to deal with in the first quadrant, pi over 3, well, that's when x is 1/2 and y is equal to root 3 over 2. And so that means that cos pi over 3 is 1/2. Sine of pi over 3 is root 3 over 2. Very good. Okay, so those are the basic sort of first quadrant values that you want to know when you're doing trig, working with the unit circle. Pretty much everything else you're going to have to either rely on either trig identities or use your calculator to get values for other angles. These are the only ones that are kind of easy to work out. Everything else takes a little bit more effort. Now, the reason that I didn't bother with anything else here is that, like I said, all the other angles, they're related to the ones in the first quadrant through some sort of reflection. So if I go to something like 5 pi over 6, right? Well, that is directly across from pi over 6, right? Y coordinates are the same, x coordinate is opposite. So if I know that this is at root 3 over 2 and 1/2, I immediately know that this is at minus root 3 over 2 and 1/2, right? And so if I'm doing cosine of 5 pi over 6, I know it's minus root 3 over 2. If I'm doing sine of 5 pi over 6, I know it's 1/2, right? I'm just reflecting across, so I change the sign of the x coordinate. Same thing if I'm down at, say, 7 pi over 4, right? X is still positive, so cosine of 7 pi over 4 is going to be 1 over root 2. Sine of 7 pi over 4 is going to be minus 1 over root 2, right? Once you've got the first quadrant, you know everything else. You just have to pay attention to signs for the quadrant you're in. Remember that cos is always the x coordinate, sine is always the y coordinate, and you'll be okay. Okay, so next we're going to look at the six trig functions. Some will refer to these as the six circular functions, since really we define them in terms of the unit circle. Okay, so we have sine theta, we have cosine theta, and again remember that sine and cos, they're defined in terms of the unit circle, right? So they're the primary functions. All right, there's a bad unit circle. Okay. So cosine is the x-coordinate, sine is the y-coordinate on the unit circle. So we have these primary ones. So if we start thinking of these as functions of a real variable, and maybe we'll think of them as sine x, cos x. It's a little bit confusing because we have x, y on the circle. Domain is R. And let me just, for reference, we're going to point out what are the zeros of the sine function. The zeros are at 0, plus or minus pi, plus or minus 2 pi, and so on. So any multiple of pi. Cosine, the domain is also R. The zeros, right? So sine is equal to 0 when the y-coordinate is 0, so at the x-intercepts. Cos is equal to 0 at the y-intercepts. So at plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so on. So all the odd multiples of pi. Okay. Now, we'll get to tan theta. So tan theta is defined as sine theta over cos theta. One way that you might want to think about it, it's really, it's really slope. Right? It's the slope of this line segment, right? Because it's y over x, it's rise over run. So tan is sort of measuring the slope. And the reason that I mentioned the zeros for cosine is that, of course, tan is given by dividing sine by cos, and that means that the domain for tan is got to be, well, x can't equal plus or minus pi over 2, plus or minus 3 pi over 2, and so on, right? It can't equal the places where cos is 0. But it's equal to 0 at all the places where sine was equal to 0. So at x is equal to 0, plus or minus pi, plus or minus 2 pi, and so on. Okay. Now those are the three main trig functions, but you can also look at their reciprocals. So there's also cosecant theta, which is 1 over sine theta. There's secant theta, which is 1 over cosine theta. And there's cotangent theta, which is cos theta over sine theta, which is the same thing as 1 over tan theta. Okay? All right. Now, a couple other things that we can say about these. sine theta and cos theta, they're always between -1 and 1, right? Because they are coordinates on the unit circle, right? And the y range for the unit circle and the x range for the unit circle is -1 to 1. All right. So these two are what's called bounded. They also have this property of being periodic, right? Because once you go once around the circle, you're back to where you started, and the values start repeating. And that periodic property is inherited by all 6 of the circular functions, right? But the other ones are not bounded. All the other ones have vertical asymptotes, right? All these places where these are undefined are vertical asymptotes for these functions, right? So cosecant is going to have vertical asymptotes at all the integer multiples of pi. Secant is going to have vertical asymptotes at all the odd multiples of pi over 2, right? Cotan is going to have vertical asymptotes at all the multiples of pi, and so on, right? And of course, since these ones are always less than or equal to 1 in absolute value, cosecant and secant are always bigger than or equal to 1 in absolute value. So I mentioned this because in the next video, we're going to briefly look at graphs for these 6. So we're going to change gears, right? We're going to, rather than thinking of these as functions now of an angle, we're going to think of them as functions of a real variable. We're going to plot them in the Cartesian plane. So what we're kind of doing is, you imagine as you go out along the x-axis, if you imagine that's your angle varying, you're going to watch, what happens to the x-coordinate, what happens to the y-coordinate, and you're going to plot those, right? And this is going to generate the graphs for these. So we're just going to give you a rough idea of what the graphs look like, because they're going to come up, and it's useful to have that picture in your head for these functions. Okay, so we've got 2 videos left on trigonometry. In those videos, we're going to look at some of the identities that you might need to use on a day-to-day basis in calculus. They come up less often than you might think, so you don't have to worry too much about playing around with identities, but they do come up from time to time, so it's something to be aware of. Now, basic identities are some of these ones that we observed when we were pulling up the graphs, right? We saw this sort of translation identity, right, that sine x is the same thing as cosine of x minus pi over 2. Okay, so we have this sort of shift that relates the sine and cosine graphs. We have the sort of even-odd identities. Right, let's label those. So we have the even-odd identities. So sine of minus x is minus sine x. Cos of minus x is plus cos x, right? So sine is odd. Cosine is even. Among the other 4 trig functions, secant is the only other even one. The other 3, tan, cotan, cosecant, they're all odd as well. Okay, and then we also have these identities coming from the fact that the trig functions are all periodic. So sine of x plus any multiple of 2 pi is the same thing as sine of x for k. K could be any integer. So 0, 1, 2, 3, minus 1, minus 2, minus 3. And the same thing for cosine. Adding any multiple of 2 pi. Gets you back to where you started. Same is true for secant and cosecant. For tangent and cotangent, you'll notice that, in fact, the period is a little bit shorter. the period for tan is in fact just pi. Okay, and that's valid for any x, right? For all these identities, they hold true for any angle x that you want to put in. Now, the fundamental identities, there are the Pythagorean identities, so-called, because, well, they come from the Pythagorean theorem. Remembering that sine and cosine are the x and y coordinates on the unit circle, and remembering that the unit circle is defined as x squared plus y squared equals 1, we get that cos squared x plus sine squared x is equal to 1. Okay, so that's this primary Pythagorean identity, right? Tends to be the one trig identity that everyone remembers. The ones that are a little bit tricky to derive, we're not going to try to prove the addition identities, and I guess also subtraction. So these addition subtraction identities, they're the most difficult trig identities to derive, and they're probably also the most difficult to remember. So for cosine of x plus y is cos x cos y, and then it's the opposite sign, minus sign, sine x sine y. If you were doing subtraction, if it was x minus y, that minus there becomes a plus. Okay? And for sine of x plus y, you get sine x cos y, same sign, plus cos x sine y. Okay? And if it was a minus sign here, it'll be a minus sign there. Okay? So these three identities here are kind of your go-to identities. These basic identities, they'll come up from time to time. But these ones you kind of tend to internalize and you don't think about them too much. Maybe this shift one, you don't remember which way it goes. But the shift one isn't super important anyway. These are going to be the primary ones that you rely on quite frequently. And hopefully you'll use them often enough that you don't have to sit down and memorize them, because they'll sink in once you've used them, enough times. Okay, so these identities here I've given to you as the fundamental identities, because pretty much every other trig identity you can think of can be derived from these. Right? So everything else is derivative of these ones. I'll list a few of the most common identities that you can derive from these. I'm not going to do them all, because there's you can come up with hundreds of identities. You just play around. You can come up with all kinds of identities, right? And you might have done a unit on this in high school, where you spend time, you're given all sorts of different identities, and you're asked to show that the left-hand side equals the right-hand side. You probably won't have to do very much of that in your calculus course, but you might need to make use of identities to simplify certain problems, right? You might have equations with trig functions in them that you need to solve, or you're just trying to simplify things because it makes it easier to evaluate a derivative or an integral or something like that. So some of the ones that you're going to run into, there are the ones that are derived from the Pythagorean identity that give you relationships between the other trig functions, right? So if you take the Pythagorean identity and you divide everything by cosine, you get, well, cos squared over cos squared, you'll get 1. Sine squared over cos squared, you get tan squared. Okay, and then 1 over cos squared, well, 1 over cos is secant squared, so you get secant squared x. Similarly, you could divide everything by sine squared. Cos squared over sine squared gives you cotan squared. sine squared over sine squared is 1. And 1 over sine squared is cosecant squared. Okay. Probably won't see these too much in Calc 1. Once you get to Calc 2, when you're doing some techniques of integration, you're looking at trig substitution and things like that for integrals, you're going to see these quite a bit. They're going to pop up all over the place. Okay. The ones that show up throughout calculus quite frequently are these double angle and half angle identities that you can derive from the addition formulas, usually by, say, setting x equal to y or something like that. So we have ones like if we do sine 2x, well, keeping in mind that sine 2x, right, what is 2x? 2x is just x plus x, right? So if you put x equal to y in the identity for sine of x plus y, you're going to get sine x cos x plus cos x sine x. So you just get sine x times cos x twice. So what you get is 2 sine x cos x. And this identity is a good reminder that you can't just take that 2 and bring it out front. There's a lot of people that are always tempted to do that, especially once you get to things like limits involving trig functions. A lot of people want to bring that 2 out. The 2 doesn't come out. It's stuck inside the sine function. If you want to bring it out, you can, but it's going to cost you a cos x. And for other multiples, 3x, 4x, 5x, it gets a lot more complicated. You can keep using this addition formula repeatedly and keep expanding, and get more and more complicated formulas. But generally that turns out to not be all that worth your time. Okay, now using that same idea in the identity for cosine, we're going to get cos x times cos x, so cos squared x minus sine x times sine x. So cos squared x minus sine squared x, right? With a plus sign, you just get 1. With a minus sign, it's not quite as simple. You get cos 2x. Cos squared minus sine squared, same thing as cos 2x. But there are a number of different ways that you can sometimes write this identity, right? So if you write this cos squared as 1 minus sine squared, if you plug that in, right? Solving for cos squared there, I get 1 minus sine squared. If I substitute that in, another way to write cos 2x is 1 minus 2 sine squared x. If instead I leave the cos alone and I say that sine squared is 1 minus cos squared, and I remember to push the minus sign through the brackets, then I can also write this as 2 cos squared x minus 1. And these can be useful because these lead to these so-called power reduction formulas. There are times where you're dealing with an odd power, an even power of sine or cosine. You got a sine squared or a cos squared in some equation. You want to lower things down a bit, especially when you're getting to integration. In integrating even powers of trig functions, the only way you can deal with them is by playing around with some identities. So if you take this equation here, cos 2x equals 1 minus 2 sine squared, and you solve for sine squared, you get that sine squared x is going to be, so I'm going to move the sine squared to that side, move the cos to that side, 1 minus cos 2x. I've got to divide by that 2. Similarly, cos squared x, right? If I move the 1 to the other side, cos 1 plus cos 2x, divide by 2, 1 plus cos 2x over 2. Okay, so these so-called power reduction formulas, those come up again when you're getting to integration problems. You'll use those quite frequently. They come up more often than you might think. The other place where you might use them is simply that you're trying to calculate, let's say you know sine of pi over 6, and you're trying to come up with sine of, let's say, pi over 12. Well, if x is equal to pi over 12, then I would have a cosine of pi over 6 over here, which I know, right? And I can take the square root of both sides to work out the value for sine of pi over 12. So sometimes you're using these identities just to get values of sine and cosine for angles that are not those standard angles on the unit circle. They can come in handy for that as well. Probably most frequently where you're going to see these is once you get into integration. You might have to do these to simplify integrals. In Calc 1, maybe you're going to use them to try and simplify some equations involving trig functions, like you're trying to figure out where a derivative is equal to 0. Maybe it's going to come in handy to be able to write sine 2x as 2 sine x cos x to try and simplify an equation. You might see something like that as well. That's it for our pre-calculus review material. From here, we're going to move on to calculus videos.